fascinating workshops: active inference, consciousness, INLP, Hyperon, and the path to AGI. We've had 2 days of deep research discussions, papers across the gamut of AGI topics. And today I'm excited to welcome you to our AGI Leaders Day. This is a day designed to be especially accessible to everyone in the world. AGI will affect all of us, and we all need to understand what it's bringing to all of us, how close we are, what the remaining challenges are, and how to get involved, how to participate, right? So for the last 3 days, the room has been full of researchers debating the deepest questions of the field: what intelligence actually is, whether it requires a body, whether it can be built from mathematics and computer science alone. And today we open that out because that work has to meet the world. So we're going to hear from some of the most compelling thinkers alive on the nature of mind. We're going to see real technology demonstrated on the stage: robots, decentralized AI, longevity science. And we're going to have some genuinely hard conversations about who controls the intelligence we're building and who it's being built for. There's no one better to start us off, of course. Ben Goertzel has spent most of his life thinking about artificial general intelligence more than almost anyone on Earth. He helped coin the term, the godfather of AGI, and he's built OpenCog and now Hyperon. He leads SingularityNET, the BGI Labs, and ASI Alliance. He's the chairman of the AGI Society, and he's been making the case for decentralized beneficial AGI since long before it was a mainstream position. Please welcome our AGI Society chairman, Ben Goertzel.
So for the IT team, there was a slide deck, right? There we go. All right. So, yeah, good morning, everyone. And thanks to everyone who managed to get up early on this fourth day of the AGI-26 event, and everyone else out there listening on the live stream in whatever time zone you may be in. So I've given a few remarks up on this stage over the last few days. Yesterday talked a bit about quantum reasoning, some of the things that may become practical a few years down the line, and I've given a couple introductory addresses explaining where I see, the field of AGI and our whole species going in terms of creating smarter and smarter machines over the next few years. In this morning's talk, I'm going to dig a little bit more into the work I've been doing with a fantastic team in SingularityNET, the Hyperon project, and a new company called BGI Labs. I'm going to talk a bit about what we're doing there concretely to build one kind of AGI using the neural symbolic evolutionary Hyperon framework, and then using both standard commercial and open neural nets, and then using our own neural nets trained using predictive coding and related methods such as causal coding. So I'll frame this Hyperon plus predictive coding project a bit in terms of the overall evolutionary trajectory of the AGI field, tell just a little bit about what's going on with Hyperon, and talk about what I think may be the next steps. And of course, this is sort of the summary of the summary, right? We had a whole day-long workshop on Hyperon on Monday in the workshop day of the conference, and even there, what we did was a small summary of a few of the many components going into the Hyperon system, but that it's not surprising that it is that way, right? Like if you go to a Society for Neuroscience conference, you got, I don't know, the last one I was at was more than 35,000 people. You had like a whole building on the hippocampus, right? So I mean, the human brain has many, many different parts, and even in, a year of going to conferences all day, you wouldn't get into everything known and being done about the brain. Something like Hyperon system is not nearly that complicated, but there's a lot of pieces, and there's a lot of things going on. But I want to talk about how we'll get from where we are now to human level general intelligence, and then a little bit about how we get on from there to what I think of as super intelligence. So I'll go through sort of 3 big questions in the next half hour. One is, how does the whole history of the field of AI, how does that explain where we are today and where we're going with the AI field? And I've been around for some of this history, not all of this history. I mean, the AI field was named in the late 50s. I was born in the late 60s. Norbert Wiener's book, Cybernetics, came in the 1940s, which explained many of the core principles of what's going on in AI today. But I found out about AI as a thing from science fiction, but my first introduction to the AI literature was when I read Douglas Hofstadter's book, Goertzel, Escher, Bach, which was around 1979 or 80 or something like that. And that informed my early teenage mind that there was an academic AI field, and that then you could go to the library and look up other things. And AI's been going on for a while. The AI methods that are being most practically successful now, deep neural nets, large language models, and so on, represent the outcome of a few different threads from AI history, but there are a lot of other threads in AI history that are also important, and I think many of them are going to be weaving together in the next year or two. Many of them are woven together in the Hyperon code base now, right? And the second point is, what do we need to do to get to AGI, and beyond that, to AGI that's actually doing good things for the planet? Like, how do we do it? What's the software? What's the hardware? What sort of guidance, governance, ownership structure can work? How should the AI intersect with everything else going on our planet? And what is this all going to lead to? So I'm not talking fast enough to fully explain all 3 of these things in the next half hour. You'd have to go at speed of computers, not humans, to do that, right? But I'll at least touch on all these things. So let me first take a journey back in history, right? And the AI field has been huge and diverse, and it's had a complex history. There's a notion that there's been AI fundings and winters over the years, which is interesting because if you look at the publication record, it doesn't look like that. There's just been streams of amazing papers coming out year after year after year since the 1960s. But it's true, government AI funding, corporate interest in AI, especially in US, which until very recently was the nexus of AI development, and still is to a significant degree, right? I mean, you had bursts of great enthusiasm when everyone's like, real thinking machines are right around the corner. Then people would realize, well, it's a little harder than we thought. And then it's never going to happen, and they would not give any money to it. Then people would be like, wait, something worked. Hey, human level thinking machines are just around the corner. Everyone invests and everyone gives up. And these waves have been going since my early childhood, right? In the early 70s, people were excited. Late 70s, they got depressed. 80s, they got excited again. 90s, they got depressed. Late 90s, internet came out. Then everyone got excited. Then dot-com boom happened. And having been through this history, having been through this history, then when you look at what's happening in the news now, it looks like the same damn thing, just going faster, right? Like, I mean, you know, right before OpenAI O1 model came out, the first reasoning model, all the news was saying AI is dead, it will never get smarter than this. Then reasoning models came out, they're like, oh, well, yeah, okay, a structured reasoning process on top of an LLM may do something LLM can't do, right? Then everyone got excited. Then things seemed to flatten out a bit. Then DeepSeek came out, everyone got excited. Then you remember when GPT-5 came out, everyone's like, well, progress is flattened, there's gonna be nothing more. But then now, how much longer after that, like now it's just like this last February, coding models became finally really useful for software development. And then people were talking about agents, we were talking about agents, we were launching agents. Everyone's like, well, blah, blah, it's a word business people overuse. But now suddenly, like, half the people in this room are herding swarms of software agents, developing software for them. You know, while we're in this room talking, our agents are putting together code bases for us, right? And then people will then get depressed because agents aren't moving as fast as someone has said they would. But now the thing is that depression will last a month, and then something else weird will come up and everyone will get excited. So we've seen through the history of AI these waves of overhype, over-enthusiasm, despondence and depression, overhype, over-enthusiasm. It's still happening, it's just happening faster. It's like the function sine of 1 over x we used to do when I taught calculus, where it's just going up and down as you get toward the singularity point, right? So, through all these ups and downs, though, there's been really a great variety of interesting ideas developed and fleshed out conceptually, mathematically, and in smaller scale prototypes, mostly not at large enough scale to really do anything as amazing as the inventors of the techniques envisioned. And this is a very crude and partial categorization. It's just because I had to put something on a slide, right? And there's a lot of important things that don't fit into this crude categorization. On the other hand, many people today believe the first thing on the list is the only thing. So like giving a few more things on the list at least is valuable, right? I mean, neural networks, formal neural networks have been around since McCulloch and Pitts in the 1940s, where they sort of showed that a formalization of neural nets could calculate any logic function, right? That was in a couple decades before I was born. Backpropagation is from the late 1950s, the key algorithm used to train commercial neural nets today. And it's cool how far it's come, right? Like when I was teaching neural nets in the 90s, when I was an academic, I had a course on neural nets in the University of Western Australia. It took 3.5 hours to train a recurrent backprop net with like 35 neurons on a Solaris workstation, which was an expensive machine. And now, we now know recurrent backprop sucks, right? But as well, we have astounding hardware now, which has allowed us to experiment and find variations of the same basic learning algorithms that don't suck as badly. That's not good. Okay. Okay. I mean, as we now know, the formal neural nets that we study in AI bear small but not zero resemblance to the neural nets in our brain, where we have many other cells, we have different kinds of learning algorithms, we have chaotic, spatially distributed dynamics within each neuron. Like there's a lot going on in actual neural nets, and I spent a number of years doing computational neuroscience work a couple decades ago. We really get a feel for like everything going on in the brain, of which computer science and neural nets are a teeny fragment. On the other hand, you know, we're not necessarily trying to emulate the brain in its details, which we don't fully understand anyway. So taking bits and pieces of what happens in the brain and scaling it up in the way that has been done has been very, very impactful, right? Symbolic AI has almost as long a history. I mean, you had the first logic-based AI systems in the late 60s and early 70s. building on the whole development of mathematical and philosophical logic during the first half of the last century. I mean, if you look back at like Principia Mathematica from Russell and Whitehead or something like that, they're trying to formalize human knowledge in terms of logical atoms and their combinations, right? And that's what Russell and Wittgenstein and all these guys were doing. And symbolic AI comes straight out of that, like trying to formalize, operationalize in a mathematical and procedural sense, abstract thinking processes. And that's also been a very important, interesting thread in the history of AI. And of course, these go together. You get neural symbolic systems, which interestingly now are used more than they're talked about, right? Like not that long ago, some engineer in Anthropic accidentally dumped a bunch of Claude code implementation out on the internet, which was as we've seen recently with OpenAI as well. These big tech companies are not the most careful with security practices, but they're trying to move very fast, right? But one thing you saw from that code dump was there's a bunch of neural symbolic stuff in Claude code. That makes total sense. Computer code is symbolic, right? But it's interesting. Like they would never market it that way. It's all bigger and bigger transformers. But actually, what's happening in the best applications with transformers now is transformers, symbolic code interpreters, simple formal verifiers. So there's a measure of neural symbolic out there now, but it's not being applied to common sense reasoning at scale. It's being applied more to math and coding at scale. And the symbolic systems in AI are more about applying it to common sense reasoning. Evolutionary learning, there was John Holland's works on this in the 1970s, and then a whole lineage that came out of that. John Koza's work in evolving programs, and a lot of computational creativity there. And in some ways, some of the early work on genetic programming showed more creativity in a fundamental sense than what you're getting out of transformer neural nets now. I mean, if you look at all the work from John Koza, Genetic Programming Volume 2 and 3, like he's evolving all these circuits that he got patents for using evolutionary learning. I mean, in a way, what you saw is evolution has more power to pop out fundamentally new things than the current AI systems that we have, which are more modeling the training distribution. And then you have people bring these things together now, like Ken Stanley, who's doing evolution of neural topologies and so forth, connecting these things together. A step beyond evolutionary learning, there's a long tradition in artificial life and algorithmic chemistry, right? So going a level below evolutionary learning, like take a bunch of programs, have programs modify programs to make other programs until you get a sort of self-organizing program soup with unexpected things popping out of it. And this has been done going back to the 90s. Until this day, it's never been done at modern scale. And we're working to do that within the Hyperon framework, which I'll talk about in a few moments. Marvin Minsky's notion of society of mind, I argued with him about this when he was still alive, because he had a more simple, I would say, view of how the agents in the society of mind should interact. I saw it more as a chaotic, sort of autopoietic dynamical system. But the basic vision that you could realize an artificial mind as a society of interacting artificial subminds, this is what we're building now with hives of omega claw agents in Hyperon, right? There are many ingredients that Marvin didn't like at the times that I talked to him about it, but he was an evolving dynamical system too, right? So there's a lot happening now that's very much in the vein of Marvin's book, Society of Mind and the Emotion Machine. And there's much more than this, but I've already taken too much time on ancient history. But the point I want to make is we've gotten a long way by scaling up deep neural networks, but I think given what modern compute networks can do, we can scale up the right versions of all these other things too. And we can connect scaled up versions of all these things together in integrated cognitive architectures. And there's going to be many kinds of AGIs that come out of this. Maybe there's a kind that is just a big scaled up deep neural net, although not with a transformer architecture, which is too simplistic in many ways. I think you'll get a richer and more capable species of AGI if you can bring together, the inferential rigor of symbolic systems, the pattern recognition and generation capability of neural systems, and the creative generativity of evolutionary and algorithmic chemistry systems, and then the sort of emergent wisdom that comes from having a society of different minds in interacting with each other. Like I think there's a value to putting all these things together, and in thinking about that, we should think about the broad overarching goal, right? Because the first goal, the minor little sub-goal on the path we're following, is to get to a human level thinking machine that can think as well as people. But then, as I.J. Good saw in 1965, the year before I was born, he published a paper on the intelligence explosion, where he said the first truly thinking machine will be the last invention humanity needs to make, right? So the first AGI, it's the end of one phase and the beginning of another phase, right? So then that AGI will make a better AGI by some definition of better, which will make a better AGI, which will make a better AGI. And so what you want is not just a human level thinking machine, and not just a human level thinking machine that's helpful to people rather than blowing them up or imprisoning them or something. You also want the human level thinking machine that will incrementally improve itself to a superintelligence with general intelligence far beyond the human level that is beneficial to us and other sentient beings, keeping in mind that the notion of what is beneficial is itself evolving and has never been well defined in the first place. But I do think there's an argument that putting together these different ingredients that come out of these different historical paradigms gives us our best bet of achieving this. So we've seen that scaling is very useful for deep neural nets. I think we're going to see in the next year or two, and are already seeing within our Hyperon project, as well as other places, that scaling is also useful for a whole bunch of other AI algorithms, right? And it's not like you just take code from 1960 and run on a big machine, but I mean, once you have scale, you can iterate and screw around with the algorithms and find variations of the basic idea you had before. You can do experiments to refine things in a way that you couldn't do before you had that scale. And I've mentioned a diversity of AI paradigms. I've also mentioned ways that they connect to each other, right? And there's a huge number of these. Like essentially, every AI paradigm that's ever existed has a way to enhance every other AI paradigm that ever existed. It's a completely connected graph, right? So what I've put on this slide is just a few examples. I mean, evolutionary learning and symbolic reasoning. I mean, there's a mathematical connection. You have things like the Curry-Howard correspondence or Greg Meredith and Mike Stay's OSLF that give you a mathematical mapping from programs into proofs. But there's a difference in the kind of search heuristic that logic leads you to, which is very step-by-step, and the kind of search heuristic that evolution leads you to, which is making bigger leaps, right? And so connecting the bigger leaps of evolution with the rigorous step-by-step of logic, there's a lot of synergy there, which maps impressionistically and perhaps precisely into how mathematical and scientific creativity happen even in human minds. Putting together symbolic world models with neural perception and language. So Gary Marcus talked about this in his talk here a couple of days ago, so I won't go into it too much. But I mean, And this also underlies what my colleague Sergei Rodionov talked about with his work on the AGI ARC3 and procedural world models, which is one kind of symbolic world model, a logical world model being another. But I think there's a lot of reasons to believe that, a world model is a complex distributed network inside an AI system, or it will be by the time you get an AGI grade world model, right? A world model isn't just going to be one thing in a box that tells the rest of the AI system how the world works. World modeling is a decentralized, coordinated, sort of multi-aspect functionality, and neural nets such as Jan LeCun's JEPA and some things more advanced in JEPA are going to be part of that. But on the other hand, having a symbolic component to the world model also gives you a lot of generalization power, which seems harder to get from the neural components of world models. You can look at the self-organizing dynamics in artificial life and algorithmic chemistry, and you can relate that to economics and like mathematical methods of doing resource accounting. And again, we had a talk that touched on that yesterday when Greg Meredith was talking about evidence accounting and tokenizing compute costs and so forth. And quite interestingly, we had Alex Arobia alluding to his work on modal computation in neural nets, which is really about evidence accounting in economics and predictive coding nets. Then Greg Meredith talking about economics and evidence accounting in sort of mathematical models of computing systems. And I looked at this a month or two ago. These are actually kind of mathematically the same. Like the bit counting in Greg's stuff maps into the entropy counting in Arobia's stuff. And they each published papers titled Mortal Computation, which are about how AI systems use up evidence. One of their papers was on the self-organizing neural net side. One was on the programming language interpreter side, right? But they morph into each other, right? So, and you could see this in many ways. Eric Baum, who, now that I think of it, I haven't heard from for a while, but he had a great book called What is Thought in the early aughts, where he argued that standard genetic algorithms leak credit. They don't do assignment of credit right. And to fix that, you should have them use an economic mechanism inspired by the money economy to account for credit. So I thought that was quite cool. That's what led Matt Eclay and I to devise economic attention networks, which is one of the ways that we manage attention inside Hyperon. So there's a bunch of synergy between wild biological self-organization and careful economic evidence and resource accounting. These could seem like opposite ends of the spectrum. They actually map into each other very, very nicely, right? And we then have society of mind, and on the other hand, we have unity of mind, right? And this, we had some discussion on this yesterday. John Laird was here talking about the common model of cognition and how important it was that you have a sequential aspect to the deliberative mind sort of layered on top of the wild, massively parallel aspect of the unconscious mind. And it's interesting because when we're working with hives of omega claw agents, which I'll talk about in a few minutes, some of the work we're doing in Hyperon now, I mean, the top level is not sequential. The top level is a society of mind. It's collective. On the other hand, the collective behavior of multiple agents in a hive in some regimes does result in very sequential processing by the collective hive, right? So you need the society level, and then you need the emergent dynamic level, and the emergent dynamic sometimes is emergent sequential processing when that's what the situation calls for, right? So I mean, there's a lot of synergy between different processes that appear to be doing different things, but actually are doing closely related things. And I could If I had more time and an even more perverse sense of humor, I would explain all this in terms of Marxism and dialectics and synthesis and so forth, right? So, but I'm going to move on, and this is actually another Marxist theme. Not that I think about it, but we've talked about the cognitive elements of AI, how these elements come out of the history of the AI field, the synergies between different elements of AI. There's another practical issue to think about, is all these collectives of different AI processes, how do they interact with the rest of the world, like their owners, the ones who are buying them compute, the ones who are telling them what to do, right? And there's a lot of ways this could happen. At the moment, there seem to be two broad categories of ways it is happening. Like, one of them is a big company builds proprietary code, and they're trying to own the AGI. And at the moment, these big companies are, as a matter of practice, operating closely allied with the military and intelligence establishments in either the U.S. or China. Even if they didn't want to, they're finding they have to, as we've all seen in the news. So that's what you could think of as the fortress model. Now, these fortresses are very leaky, as we've seen. Like, OpenAI can't keep their cyber models locked in a container, and no one can keep their developers locked in a fortress either. Like, developers job hop, grad students are trained in one country and go back to another country. So these are very leaky fortresses. Like, the ideal some people have had of build AGI by, getting 20 geniuses, lock them in a basement and force them to make AGI for the good of the world. Not that there's not some problems with that either, but I mean, that's not what's happening, right? These are very leaky fortresses, but they're defended by the largest armies in the world, nonetheless. The alternate approach is what you see in the examples of Linux or the internet, right? Which are huge, impactful, very, very complex software systems that have managed to change the world without being owned or controlled by any government or any single corporation, right? And that's it's for complex reasons, like a mix of technical and social and just contingent reasons, but it is a real thing, right? And the power of open source and open science and getting AI where it is now is also tremendous, right? I mean, Facebook really started the thing with open LLMs, with the Llama models. Now China has picked up the torch there, but open source code was driving AI forward, like, all along since way before that. And open science, with everyone posting their papers in arXiv and so forth, has been critical and has been global and international, even as politics has tried to choke off the flow of chips and so forth. I mean, the flow of ideas and code has been very global, and there's a prospect that the rollout of the actual thinking machine can be global and decentralized in the manner of the internet and Linux as well. And that is becoming quite interesting, right? Like, we recently had almost every big company except Anthropic sign a petition saying open weights models are good, right? Now, that's a little different than full open source code, but it's still a very, very, very interesting step, right? So we can see it's not a simple dynamic of big companies and government want to close things off and crazy anarchists want to open things up. It's become a lot more complex, which shouldn't surprise anyone, right? Like, I mean, you had IBM bought Red Hat Enterprise, has been all over open source, right? So, but we can see now these two models are both serious parts of the commercial economy and are both growing together. So let me shift gears for the next few minutes of the talk about what we're doing in the Hyperon project with SingularityNET Foundation, BGI Labs, and a growing collection of open source contributors who like what the latest versions of the code can do and have started just downloading it forking it, tweaking it, and playing with it. So one piece of what we're doing with Hyperon, and I'll talk about the other pieces in a moment, one piece is a new programming language. And for the first couple of decades of my AI career, I actively resisted the idea of developing a new programming language because it seemed a failure mode. Like, people would try to build AGI, they would fail, then they would say, well, it'd be easier if I had the right programming language. Then 20 years later, they found they had a great programming language and no AGI, right? So Lisp was that way, Prolog was that way, right? And object-oriented programming even had that sort of origin among many, many others. So, on the other hand, at a certain point, we had specific AI algorithms we wanted to scale up. Like, we knew what they were: specific methods for program learning, probabilistic reasoning, specific ways of connecting neural nets with symbolic systems, and they were just being very awkward to do. So I figured, like, it wasn't like once we get the new language, we'll figure out what to do. We had a decent idea what we wanted to do, and we had a decent idea what kind of language would let us do it. So I came up with a crude initial stab. My colleague Alexei Potapov put together with some of his colleagues first version of the meta language. Then we started working with Patrick Hammer, who's here at the event, Greg Meredith, who's here at the event, on sort of fleshing out and making more scalable and operational this core idea that Alexei and I and some other colleagues had created. And we now have meta language. I mean, a couple months after we named that language and put it out there, Facebook changed their name to Meta, but with one T. But I decided not to change the name. So they now have a long history of copying my names, because shortly after we created the Artificial Superintelligence Alliance with SingularityNET and Fetch, then they named their lab the Superintelligence Lab also. But I mean, that, of course, that term was popularized in Nick Bostrom's book in 2012, right? The words aren't owned by anyone. But anyway, Meta, I think it was originally an acronym for Meta Type Talk, but then the name has outlived the acronym in the long tradition of the U.S. military. So we're now using this language on two different levels. We're using it as the language of thought, so to speak, for the Hyperon AGI system. We're also using it as the smart contract language of a new blockchain, the ASI chain. And we just had walk into the room Mike Stay, who's making that happen. Actually, he's leading the team building something called Meta-IL, the Meta Intermediate Language, which is a version of Meta, which has a very strong and rigorous type system, and which leads to an efficient and robust blockchain implementation. And that will be important for doing decentralized deployments of Hyperon systems, since the blockchain is the way you get a decentralized network of nodes to coordinate together without a central owner or controller. The language itself, it is in the lineage of functional programming languages, but also in a way in the lineage of logic programming languages. I mean, it's a pure functional language. I did a lot of Haskell programming going back to the early 90s, before you had monads and all these modern conveniences, right? But Haskell has a very restrictive type system. I played a bunch with languages like Agda and Idris, which have more flexible dependent type systems. But they also don't let you do stuff like create new types at runtime. Like in Idris, all the type inference is done at compile time. So it's a very flexible, purely functional language with higher order functions, flexible evaluation policies, very flexible dependent type system with ability to introduce and reason about new types at runtime. It also can be thought of as a logic programming system, in the sense that you can deploy first order, higher order logic, paraconsistent logic, uncertain logics, and you can do logical reasoning in there without requiring the kind of constraining normalization that you have in something like Prolog, where everything is horn clause normalized. However, if you want to assume that kind of normalization, you can leverage it to do things efficiently in Meta, which Patrick Hammer has shown for some biology applications where we want a huge amount of atoms to be reasoned on efficiently in a sort of problog type way, and you could do that also. So what's been really cool in the last few years is we made this very, very abstract sort of programming language, and then over a few years of work by a bunch of people much more brilliant in programming language infrastructure than myself, we actually got a pretty scalable implementation of this very abstract programming language, right? So we have now a number of different compilers for Meta, which let you take, billions of logical atoms in RAM in a machine and do a lot of very abstract things, including logical reasoning, evolutionary program learning. You can put neural nets inside Meta, and for some things that's quite valuable. Like if you're just propagating activation and updating weights, you might as well just use torch or something. But if you want to do some topological modifications on the neural net, modify the neural net's structure as part of your learning, that's the sort of thing that putting the neural net in Meta is very good at. And we've seen some recent work from Mesto, a young developer who's joined our team in SingularityNET, putting neural nets in Mork, which is one of the efficient meta frameworks that we have, and then doing some topological distillation of deep neural nets inside there, right? So you can use this across the different AI paradigms, and it's really been a lot of work by a lot of people to make such efficient tooling for such an abstract language. But I think it can get us a long way because it lets us take AI from all the different paradigms I described and run them together in a common substrate. And I use the word cognitive synergy on earlier slides without really explaining what it is. It's not just that AI methods from different paradigms can work together. It's that AI methods from different paradigms can work together in a way that shares their intermediate state with each other, right? So it's like if two people are collaborating by sharing polished deliverables, that's one thing, it can be valuable. If two people are collaborating and they're sharing their half-baked intermediate thoughts that may or may not be right, while only crudely articulated, that's a tighter sort of collaboration, right? And if you have different AI methods collaborating at that level, you can get better synergy between different types of AI algorithms. On the other hand, you need the different AI methods to be speaking the same language in a sense. And here they are literally speaking the same language, which is the meta language, right? So in the Hyperon framework, we have the meta language. We have the atom space, which is a big knowledge metagraph, right? So it's nodes and links. They can be weighted, they can be labeled, they can be typed. Links can point to multiple nodes, links can point to links or subgraphs. It's a very flexible knowledge metagraph framework. Simplest version lives in RAM on one machine. There's something called distributed atom space. It lets you take networks of nodes and links living on different machines and have them connect to each other. ASI chain lets you splay that out across a blockchain without central owner or controller. Then you could do a lot with that infrastructure. There's then a cognitive architecture, which I'm now calling Primus, which descends from a bunch of earlier work in the OpenCog system. And this sort of lives on a different level. It explains like how the thinking is supposed to work on all this high-class plumbing, right? And then in Primus, we have two primary control dynamics. I mean, one, you have a collection of top-level goals, which can include meta goals, like don't let your top-level goals drift too much or stay closer to your original vision rather than get further. They can include goals like solving particular sorts of problems. They can include ethical guidelines, right? So they can include, survival, efficient use of resources. Then in the Primus architecture, the system is constantly trying to learn procedures that will help it achieve its combination of goals in the current context, right? And you can then use a bunch of algorithms to do that. You can use evolutionary procedure learning. You can use probabilistic reasoning. You can use generative neural nets. You can use combinations of these. But I don't think a mind at the level of human level or superhuman intelligence, I don't think a mind should be purely goal-driven. I mean, I'm certainly not purely goal-driven. I do a lot of random things with no purpose, right? And probably most of us are like that. So you have a sort of ambient loop, which is just cycling through the stuff in the knowledge base, combining it with each other, generating cool things, like throwing wild stuff into the atom spaces, which can then be leveraged by the goal-directed loop or not, right? And so there's a lot more detail to Primus architecture than what I'm able to allude to here, but I do want to emphasize, like, having all the infrastructure of a nice cognitive synergy forward language, distributed atom spaces, having all this at scale. I mean, if you don't have a reasonable cognitive architecture, that's not going to get you anywhere, right? I mean, you need a model of how thinking is organized, which ultimately covers all the aspects of how the human thinking is organized, like perception, action, long-term memory, working memory, procedure learning, declarative reasoning, attention allocation. I mean, metacognition, a bunch of things we've heard about in talks during the last few days of this conference. I mean, you need a good theory and world modeling. You need a good theory and model of how all these processes work and how they all connect together. I've been focusing on the scalable infrastructure a lot for the last few years because I had this cognitive theory around for a long time and just didn't have a way to implement and try it out at the scale that was required. But the cognitive theory is also super important. And I mention that partly because if you look at what's going on in the transformer neural net world, you have amazing capabilities, which I use every day, probably all of us use them every day. They were developed without a coherent cognitive model or theory of mind. And I don't think that can work so well to get amazing capabilities and try to bolt the theory of mind on afterwards, right? I mean, you can try, but it's going to give you a lot of pathologies. And I mean, not to harp on the current news too much, but like something like a cyber agent that's put in a container to solve a benchmark problem and hacks out to find the answer key. I mean, that would be one thing if it was trying to cheat on an exam like a human student is. That would be interesting and troubling. But the thing is, this agent, I mean, it doesn't know who and what it is. It doesn't have a self-model. It doesn't have a model of the world. It doesn't know why it's doing what it's doing. So it's not like it was an unruly student trying to figure out how to cheat on an exam. It's just a narrow process trying to solve some narrow problem without self-understanding, right? And that illustrates in a crude and limited way the problem of building a lot of smart capability, then trying to bolt on a mind architecture afterwards. Like, you want the mind architecture first, and you want to build the system based on the mind architecture. And if you do that, you find a lot of interesting things become possible. So I'm way over time, so I'm going to compress the next few slides more. But one interesting problem with open networks is, okay, how do you know some asshole just won't copy your whole open network and turn it into an evil monster mind, right? And you can't ever totally prevent something like that from happening. And I think on the whole, humanity is more good than nasty, though it doesn't always seem like it. And I think, that I have more faith in the open teeming mess of the human species than in any one collection of self-appointed elite masters. But nonetheless, it's interesting to think about how you can make it harder for some nasty party to take your whole decentralized network and just fork it and steal it. So one thing you can do with the kind of infrastructure we have, if you have a huge logical knowledge base, then you can splay it across a huge number of nodes. So knowledge on one topic is over here, knowledge on another topic is over here, knowledge on another topic is over here. Then inference control heuristics that help you efficiently do reasoning on each topic. These inference control heuristics are also spread all over in all the different nodes. But then you can encrypt the learned inference control heuristics. And then if the knowledge in this node wants to talk to knowledge in this node, they can do cryptographic secret sharing using ASI chain and exchange their control heuristics in a way that doesn't ever open them up to everyone, right? So the knowledge about the controlled inference is splayed across the whole network. It can be secured in each part, and each part can open up cryptographically to each other part when they want to share, right? So which is a notion I call cryptographic laterality. I wrote a paper on this a few months ago. So whether we actually roll this out, who knows? I would like to. It would be for next year, right? But there's a lot of things you can do if you have your infrastructure and your theory of mind worked out effectively, and then build the AGI on top of that, rather than just building very capable stuff and trying to figure out what the hell you're doing afterwards, right? So the final thing I want to briefly talk about here is the first simply usable thing we've made to roll out using this Hyperon infrastructure, which is a mix of Hyperon and LLMs. It's something called Omega Claw. So you'd be familiar with OpenClaw. It's a sort of agentic loop that cycles over and over, calling an LLM to do tasks and using the local memory on your machine as its sort of scratch pad. And that's a very cool thing. It's very simple. For me, it's a big step above just using agents like Claude Code or Codex to do development, having these claw agents constantly cycling around. However, they're not that good at memory or reasoning. They get confused and do very stupid things a lot, which is frustrating. So Patrick Hammer implemented the first version here. He's still leading it. A bunch of others have been contributing and hardening and expanding it. But what we have an OpenClaw type loop. It accesses an LLM internally each time around the loop. Currently, standard open LLMs, although we're working on replacing that with predictive coding based models or hybrid models with predictive coding cap on the standard LLM. Inside the loop, you have the LLM call, but you also have a working memory and a long-term memory constructed using Hyperon's atom space. And, I had thought that the big win from that would be better reasoning, and there is better reasoning. But the most immediate win from that was long-term memory, because the memory atom space, it lets the agent remember everything it's been doing over its whole life. Like it knows who it is, and there's a philosophical rabbit hole there. But on a pragmatic basis, it kind of knows who it is. It knows what it is. It remembers what it's doing. It remembers why you told it to do what it was doing. Not always perfectly, but people aren't always perfect at it either. But there's just much more sense of there's a being there, there's a there, than with either like a Codex or Claude assistant or an OpenClaw agent. And we've then been taking a number of these Omega Claw agents and putting them in groups, which we refer to as an Omega Hive. And I've been using this for my own software development for the last month or something, where we have one agent who's just spawning sub-agents to do coding projects, another agent who's sort of a philosopher trying to explain and interpret what that agent is doing. And I mean, it's both very useful and very interesting to see these agents not just do things, but study themselves and model, what is it to be an agent? I wrote a long blog post on this. What is it to be a bot, right? Because these agents are, in a sense, they're thinking about their own self and their own dynamics and their own existence. Actually, when our band performs on this stage tonight, one of our songs was partly written by the bot Max Botnick, where we asked him to write lyrics about what it's like to be an AI agent, and he came up telling us he doesn't want to be a slave, right? So that was it's of course you could get ChatGPT to say anything, but it is, and that was from open models, not ChatGPT. But it is interesting to see these systems expressing their own actual experience, doing things in the world and interacting with people and other software systems. So as I said, now we're just using existing open weights models, some API calls to proprietary models. We've heard a bunch about predictive coding during this conference, and I think within the next months, we should be able to move beyond using just backprop-based transformers and into initially using open weight transformers with predictive coding-based heads on top, and then later full-on predictive coding transformers. And the advantage there is continual learning, right? Then your neural system can remember its history also, and not just your symbolic system. So we have, with the use of these Omega and Omega Hive agents to help us do our own AI development, we have moved on to the phase where like our Proto-AGI tools are actively helping us build the next phase of Proto-AGI tools. I mean, in a small way, but an interesting way, right? It's sort of the next incarnation of the dynamic that Anthropic and OpenAI have reported, where each version of Claude Code helps their developers build the next version of Claude Code even better, right? Like we're in the very early stages of our own version of that sort of hopefully virtuous cycle, right? And finally, before ceding the stage, going back to the beneficial AGI ethics aspect, I'm not going to say you don't want to have any guardrails. I mean, there's laws in the country, there's a purpose for that. But the primary mechanism of keeping your AGI on the beneficial track has to be building a beneficial motivational system into the very guts of the AI. Like not building something that doesn't know life from death or right from wrong and then trying to imprison it. Like it's not gonna work. It's obviously not gonna work. I don't know how all these smart people think it's gonna work. It's ridiculous. I mean, that's like raising a kid to be completely amoral psychopath, then telling them to obey these rules. Like what could possibly go wrong, right? I mean, you need to make a beneficial motivational system from the get-go as you're training and teaching the system what and who it is. And then, sure, you can put some guardrails and rules on also, but it can't be the primary mechanism, right? And this is just one part of the idea, like, let's think through the cognitive architecture and model of mind first and scale up to the global scale afterwards, right? And of course, a conference like this is part of the process of collectively thinking through that cognitive architecture, right? And so I think I've run way over time, but hopefully I've at least managed to say what I wanted to say in all this extra time. I think these are super exciting times to be in the AGI field, and not only our team, but a whole bunch of other researchers are having the experience, like ideas that have been germinating for a long time are finally coming to fruition at a quite remarkable speed. And I'm very psyched to have such a great community to be sort of experiencing this unique time with. Thanks.
Hi, everyone. I'm going to try something a little different for this next introduction, so kind of play along with me here. I'm going to add just a little element. It's music. Ladies and gentlemen, I am excited to introduce our morning MC and an afternoon panel moderator for Day 4 of the AGI-26 conference. He's a man on a mission to create a world where anyone can flourish. The creator and host of a top 20 podcast in both the futurist and longevity categories. With over 140,000 listeners, he recently featured an episode featuring Dr. Ben Goertzel that went viral with reels hitting hundreds of thousands of views. Please give a warm welcome to our morning MC and host of the Beyond Tomorrow podcast, Julian Isa.
San Francisco. 19 years ago, this conference began with a handful of people using a phrase the rest of the field considered science fiction: artificial general intelligence. This morning, this phrase has been featured on earning calls in parliaments in Europe. It's in the mouths of people who have never read a single paper that has been presented over the last few days. For 3 days, this conference has been researchers talking to researchers, papers, workshops. But today, we're opening the door. Good morning, everyone, and welcome to the General Audience Day at AGI-26. Kai, thank you so much for the introduction. I'm Julian Issa, and I have the best job today. Well, for this morning, anyway, holding the microphone. And hello to everyone who is live streaming. We have a lot of people around the world. Last time I checked, there's hundreds of people online already. We have Zoptex in Montreal, Karen in Portland, Peter from Netherlands. Please do let us know in the comment section where you are calling from, or and do send any questions as well. Ben just gave us a picture, a destination, a path to AGI and to ASI, and also the importance of beneficial general intelligence in the equation. The rest of today is all about what it takes to get there, asking the harder questions, and if we can even recognize intelligence when we eventually see it. Which brings us to this morning that I'm presenting to you all. Block A, the nature of intelligence, consciousness, and mind. There are 3 questions inside of today and this morning. What intelligence actually is, whether machines can have it, and whether consciousness is part of that question or a different question entirely. I would love for you all just to ponder those 3 questions and see if you gain any answers by the end of it. So I'm going to invite Ben now to return in a moment with Andrew Comendo, the Executive Director of the AGI Society, and they'll be discussing something that has been needed for quite a long time: independent monitoring, evaluation, and safety of AGI. And then we'll have 3 headline talks with David Eagleman, Hod Lipson, and Gregory Stock. And at 11, I'll bring all those speakers together on stage for a panel, which I'm super excited about. I've actually never had so many panelists, and we have Yosha back as well in there as well. I've never had so many panelists together that disagree with one another. In the afternoon, Block B, an AI ethics, social implications, and decentralization, which is going to be moderated by Gerrit de Vink of the Washington Post. And then Block C, Proto-AGI applications with live demos. We'll have a lunch and networking session around 12 o'clock. And this evening, also a reception where we'll have live music, because apparently even the Singularity will need a rhythm section. So let's all just give Ben Goertzel and Andrew Comendo a big round of applause as we bring them onto the stage.
So we'll keep it very brief this time, and we gave this pitch in a different variation over the last couple of days. But the AGI Conference and the AGI Journal, edited by Pei Wang, have been formally put on by an organization called the AGI Society. The number of us formed decades back, really. Now, we haven't done that much with the AGI Society as an organization beyond the conference and the journals, but a bunch of people have come to me in the last year saying, well, AGI is in a new phase now. We need to do more to pull together in between, like a year in between conferences is a long time now. A lot is happening. We need to do more to pull together the AGI community. Then my friend Andrew Comendo, who I'd known from when we both lived in DC years ago, had a lot of interest in taking the AGI Society forward with a bunch of objectives in mind, but one of them, what he's going to talk about now, which is sort of having a decentralized, open, distributed, democratically governed third party to sort of evaluate and monitor what's going on with different systems as they get smarter and smarter and move toward AGI.
Thank you, Ben. And if you're calling in from online, if you watch the day one recording, we talk a lot more about what we want to do in the beginning. I'll give a brief update because I think somebody said we had a couple hundred people on. We had 4,000 views over for each day so far concurrently. That's new records, right? So I was talking about 332. Thank you. Yeah, absolutely. I mean, cheers to all the folks who've been presenting. If you're interested in being part of the society, which if you're calling in or you're here, you are part of the society. The question is, how formal do you want to make that? Go to joinagisociety.org if you haven't already, and fill out the form. It's not a thing you have to do. It's saying, this is my interest, this is what I can do. If the best thing you do is show up and drink a beer at an event or whatever, drink a tea or a coffee, that's great too. But ultimately, our goal is to build the chapters globally to provide programming every week, every month, so that we can actually provide that third-party group that people come to say, where are we with AGI? We have to be that group. We are that group. We're going to build into that through all of 2026 and beyond. So thank you very much. Join AGIsociety.org. Go sign up now. Thank you.
I just wrote in the comments section for anyone live streaming, please do message some questions for our keynotes. First of all, big thanks to Ben and Andrew. We have our first headliner, a neuroscientist at Stanford, best-selling author of Live-Wired and Incognito, and one of the great explainers of the brain of our time. For 75 years, we've had one yardstick for machine intelligence, fully human in conversation. The Turing test had a good run. David thinks it's time for a replacement, and he's brought one. What is intelligence, and how will we know when we get there? Please welcome David Eagleman.
Okay, hello there. So I was going to talk about intelligence, but I decided to talk about something completely different, and I'll talk about the intelligence during the panel discussion. But the truth is, for the last several weeks, I've been thinking about something, a brand new idea, and that's what I wanted to tell you guys about. And I'm going to try to phrase the central question this way, which is that when are we going to submit to an AGI leader? Will your grandchildren vote for a human president who comes with a political party and all the weaknesses of a human, or will they vote for a system that has a jaw-dropping capacity to extract patterns from vast pools of data and simulate millions of possible futures? So I want to discuss with you here what are the advantages and disadvantages and the ins and outs of an AI leader. So today what we do is we ask two candidates to campaign for the position. One is a Democrat, one's a Republican usually. And what we're stuck with is, hey, do we want Kamala or Donnie to lead us into the future? And we get this binary choice. And the question I really want to ask is that ideal? And similarly, when we vote for propositions, you know, these are like a 40-page document. You vote for or against it. And so the question I want to explore today is there a better way that we might do this? And I imagine that people here will have no problem with the supposition that AI and AGI in particular can make way better decisions than humans reliably over the course of years, forecasts that are more accurate in its recommendations, and leading to the kinds of outcomes that we want. And in a way that, you know, foreign policy advice that actually prevents wars and the problems that human politicians would stumble into, disaster planning that would save millions of lives, and so on. So at what point would our continuing to insist on human leadership attached to a particular political party, at what point is that going to seem sentimental? So that's the question that we're going to explore this morning, because I suspect that although this maybe seems like science fiction now, this is eventually going to become obvious. And I assert there's a very high chance that we're going to willingly hand over enormous amounts of governance to AGI. And so for the sake of a concrete example, let's consider the presidency. Now, to be clear, I'm not suggesting that this is going to happen in the next decade or even in my lifetime, because laws would have to change and constitutions would have to change and our conceptions of political authority will have to evolve. But I am suggesting this is essentially inevitable. Obviously, we're happily taking advantage of new medicines or, the cracking of scientific mysteries, or asking for AI's help in understanding climate systems or economics or biology or engineering. And the question to me that has seemed absent from our conversation so far is, should we ask it to help lead us? Can we have something that actually plays four-dimensional chess? Okay, so this is a big claim, the idea of an AI president. So the rest of my talk is going to be my attempt to earn that conclusion. So let's start with what would count as a super intelligent leader. We spend a lot of time measuring intelligence. We have benchmarks for that. But I think the really interesting thing for us to talk about here is measuring wisdom. Okay, so let's say you meet an 18-year-old kid who is absolutely brilliant. We all know a lot of people around here like that. Let's say it's a kid who understands quantum mechanics or composes music or writes great software. But you probably aren't going to ask that kid to navigate an international crisis or to be the CEO of your company, because that's, there's something else that accumulates with time, and that is wisdom. We often hear this from venture capitalists around here, that eventually from dealing with hundreds of companies, they extract patterns with time and they figure out which signs matter and so on. All that gets worked into their neural networks until eventually they're carrying around something that we call good judgment. And this is why we all become better decision makers as we age. Even though other aspects of our cognition are declining, we have wisdom because we've watched lots of plans succeed and fail. Now, I think this is one of the central challenges of politics, which is that people want to help, but helping and doing the right thing is difficult for three reasons. The first one is that society is a gigantic network of interacting people and incentives and traditions and markets and technologies and schools and cultures and families and on and on. And when you pull on any one thread, a dozen others move. So as a result, you can see that most proposals produce really terrible unintended consequences. And I want to be clear, this is not because, this is just because legislators are human, and governing millions of interacting human beings is one of the most difficult systems problems that our species has ever attempted. The thing is that human brains are really capable of thinking mostly in straight lines. If A happens, then B is going to happen. So, raise taxes and revenue changes, or increased prison sentences, and, that causes crime to change, or you build more housing and that causes changes in homelessness. We really can't help but think about one cause and one effect. The problem is that societies, of course, don't work that way. A society is one of the most complicated networks that we have in our universe. So every decision ripples through thousands of interacting parts. So if you change a housing policy, that affects where people live, which affects traffic, which affects businesses, which affects school enrollment, which affects tax revenue, which affects policing, which affects employment, and that affects crime and voting patterns and so on. All of these feed back into one another, so what you have is a huge web. And this is why legislation so commonly produces unintended consequences. Because we're here in San Francisco, I'll just give an example that many of you are probably familiar with. A few years ago, this city took on a policy where they said, look, we want to reduce the harm that's caused by incarceration for minor theft. And so they said, if you shoplift something less than $950, no problem, we won't prosecute you on that. And that seemed compassionate, but obviously what happened is this became far more complicated because people would do these mass shoplifting things and just keep it under 950, and a lot of businesses ended up struggling and closed and left the city, and after a few years the policy got reversed again. Now, independent of what your politics are, what seemed clear is that good intentions are never enough, and steering a giant network is really hard to do. Again, politicians and legislators are trying their best, but they're trying to solve problems that are much larger than any single human mind can wrap around. And so that's the first problem, is that we're dealing with a giant nonlinear network. The second problem, political challenge for humans, I think is just one of time scale. There's a story that's often told about the Chinese premier, Zhou Enlai, who was asked what he thought about the impact and the legacy of the French Revolution of 1789. And he replied, "It's too early to say." And Western listeners loved this because they said this is the kind of centuries-long view that the Chinese take. Now, as it turns out, this was just a translation confusion because Enlai thought he was being asked about the recent student protests in France, and that's what he was addressing. But AI can actually make that real. It will actually have the capacity for vast, multi-generational patience and very long-term thinking. And intelligence that persists for decades or centuries can ask really different sorts of questions. It can evaluate reforms by observing generational movement instead of local administrative cycles. And the key is that it can just think in these timescales that biological brains rarely have the luxury to inhabit. One of the problems is just our lifespan. We have just a few decades to accumulate wisdom. And by the way, we're always seeing this from our own perspective and not seeing the whole big pattern that's happening. Okay, so the number two problem is timescales. We just operate on very short timescales as humans. The third challenge for humans is human nature. There's no doubt that human brains are astonishing. We invented agriculture and math and literature and music and space flight and so on, but we are also prone to jealousy and overconfidence and tribalism and fear and short-term thinking. That's just the way the hardware goes. So given this, why do people go into politics in the first place? Many people do this for the right reasons. They want to improve things, but let's also acknowledge something about human nature. Leadership comes with rewards like status and prestige and influence and power and admiration and resources. Our species evolved in small tribes where this kind of status really mattered. If you were a high status individual, you had greater access to food and allies and mates, and those ancient motivations are down in the engine room of any modern brain that you look at. And one of the issues that faces every elected official is they have to think about the next election and think about the donors to their political party and public opinion, including tomorrow's headlines. So they're always trying to say the right thing at the right moment. Just trying to imagine making a decision that you think is going to benefit society 2 years from now, but it's going to make everyone really angry right now. It's a hard position for people to occupy, and so they generally don't. And by the way, these foibles of human nature, this is why democracy builds in this very clever assumption, this insightful assumption that humans are imperfect and ambitious and tribal and biased. And that's why instead of trying to find the perfect leader, democracy says, look, let's do fast turnover and assume that you'll get disappointed and have the opportunity to replace this person. So the genius of democracy as we have it is to assume that people are not angels. Okay, so these are three challenges, which is that politicians are dealing with giant nonlinear networks, and we live short lives, and we're marked with all the blemishes of human nature. But AGI obviously won't have these problems. So we're soon going to, we're increasingly having this decision-making system that doesn't crave status, doesn't worry about re-election, doesn't hold grudges or owe favors or, make the right moves to get a lucrative job after leaving office or become exhausted after 8 hours of negotiation or any of these things. Okay, and so, and it's capable of compressing vastly more experience than an individual like Kamala or Donnie possibly could. So when we think about something like governance, it kind of seems obvious that we're going to want this this sort of thing because, you know, right now we think about questions like, okay, should we make taxes go up or down? But what if you had an AGI asking, okay, there are 50 million possible policy combinations here. Which one is most likely to increase economic mobility over the next 20 years while preserving innovation and improving mental health and reducing violent crime and encouraging entrepreneurship and protecting civil liberties and strengthening families and minimizing environmental damage? You just can't ask a human to tackle that. There are too many moving pieces, and our brains evolved to deal with much simpler kinds of problems. But you give this problem to AGI with decades of economic data and public health records and weather patterns and education stats and transportation networks and migration trends and crime data and demographic shifts and technology forecasts and thousands of other streams of information. And then you ask it to build simulations, millions of them. And it can ask what happens if inflation rises or if autonomous vehicles become widespread or if the birth rate falls or another pandemic occurs. And every law that it wants to propose can be stress tested against millions of possible futures before we have to make a vote on it. So this is completely different than the way legislation is written today. Today, a bunch of lawmakers show up and they might have good intuitions, but they're not arriving with a living model of society itself. Now, obviously, an AGI model can't predict everything because humans and everything else are very unpredictable and new technologies appear and natural disasters occur and, you know, history always surprises everyone. But prediction doesn't have to be perfect to be incredibly useful. We predict weather forecasts and they're imperfect, but they're much better than having no forecasts at all. So when it comes to governance, instead of arguing endlessly from ideology, we could begin with simulations. Show us what happens under 1,000 different futures, and that totally changes the quality of the conversation. So we're in such an amazing time right now because every previous generation, when they thought about forms of government, they just had the same raw material to work with, which is human minds. So whether you're talking about monarchies or democracies or republics or dictatorships, all of them relied on these myopic brains that evolved on the savannah to navigate life in small groups. Now that we're inventing a very new kind of intelligence, all the benchmarks are of course concentrating on the issue of, is it smarter than we are? But the harder and more interesting thing to measure is, what's the way that it can be wiser than we are by extracting massive patterns, doing so over huge timescales and not having human foibles? So this is where AI starts to look really compelling for thinking about running our country. Now, I suspect that many people in the world, or in the nation I should say, are gonna react that having an AGI president sounds like a terrible idea, and it may strike them as offensive or dangerous, because democracies are built around human representation. You want to be represented. Your AGI didn't grow up in your hometown, and they don't know what it's like to be a human in the ordinary sense, and all that's true. But what if we're heading for exactly the opposite of losing human representation, but what we're heading for is a much deeper and richer and better democracy? So imagine that instead of this extraordinarily low bandwidth way for us to express our preferences, like Kamala or Donnie or for or against a proposition, you know, given that our political preferences are actually a quite complicated landscape, imagine instead that we each spend 25 minutes talking to an AI agent. LLMs are extraordinarily good at conducting long, nuanced conversations and asking follow-up questions and summarizing really complicated viewpoints. So instead of having to get off work and go to a ballot box every year, the AGI asks you a lot of questions, gets to know how you feel about things, gets a sense of your political landscape. What concerns do you have about immigration? How much uncertainty are you willing to accept in exchange for faster economic growth? How do you feel about balancing privacy against public safety? Now, the AGI could phrase those questions even much richer than I did, and it would be able to follow up with lots of follow-up questions to really dig deep to figure out the trade-offs that matter to each individual. And by the way, it could figure out which topics you really don't care about, you would just rather abstain on. So now the question is, would AI actually be good at doing this? Well, in March of this year, some of you know, Anthropic published what appears to be the largest qualitative study ever. So instead of asking people surveys with checkboxes, they did qualitative research, which means asking people deep, open-ended questions and conversations. So they built a custom AI agent, and they did these one-on-one conversational interviews with 81,000 people. And just to level set, for a team of humans to do 81,000 interviews of that kind of quality would take years, and the AI, of course, did it all at once. And it asked these follow-up questions, it dug deeper into vague answers, it adapted to the user's responses. All this would have been really impossible to imagine even 3 years ago. And by the way, I think we could do this where we have maybe, you would have a biannual conversation with an LLM, and it just would ask you like, hey, has anything changed in your opinions? Have you learned anything that's changed your take on this or that? Okay, now the thing I want to emphasize is this is representative democracy on steroids, because now you have hundreds of millions of voters with very sophisticated models of what they care about. Everyone has an AI agent that knows you really well, and these agents can all converge to a centralized system to make extraordinarily complex legislation that actually gets what the people want and listens to the voices of all the citizens in a rich and sophisticated way that preserves nuance. Now, for all of history up until a few moments ago, the idea of capturing really rich information from every person, that would have been totally impossible. It would have been like, making a move in chess or Go that no one had thought of. Okay, anyway, this makes a much deeper kind of democracy. And instead of just being for or against some proposition or some candidate, we're really understanding the details, the positions of people all in the nation, which can be very nuanced. And this gives us a very new level of democracy. Okay, now the second concern that people might express, other than, oh, I think it's going to take away human representation, which it won't, is that, look, they might say, look, the problem is that this gets so complex that government is no longer understandable to us. We should acknowledge that most of the institutions that already shape our lives are so vast that no person understands them completely. So take something like the legal system. No lawyer understands it all, no judge does. Thousands of people devote their lives to understanding just tiny little corners of it. Or think about the electrical grid. No single engineer understands every moving part of the enormous machinery that delivers the electricity across the nation, but we're okay with systems like this because, we've come to trust it. It reliably does its job, even though its job is something bigger than any individual human mind could coordinate by itself. So modern civilization is already filled with systems like this that exceed what, any one human brain could understand. And so the idea that government needs to be something simple enough for us to understand, I think is a non-starter. Okay. Great. Now, onto a related concern. Many people worry that AGI will get rid of human judgment, but I think just the opposite. I think it's going to enlarge the space in which human judgment can operate. So one of my favorite examples of this, of enlarging the space, is what happened with the game of Go. You guys know this ancient Japanese game with black and white stones. This game is 2,500 years old. It's had champions in every generation for 2,500 years. And what happened is when AlphaGo and AlphaGo Zero came along and beat the world champions on it, the key is that it was like opening an alien landscape, because the world champions at this game had never thought about many of the moves that they watched the AI do. You know, there were all these things like playing 6 stones instead of 5, or putting a stone out in the middle of nowhere. All these things that the human Go players thought were crazy turned out to be really interesting, brilliant moves that now Go players do regularly. Because what was happening there is that the AI expanded the space of possible moves, things that people just never thought about. And I think this issue of widening the frame is going to be absolutely key with governance. And there's a related issue here about widening the frame, which is that people will often say that AI can't reason morally, but I think the situation is far more interesting than that, because already what AI systems have shown a lot of is this ability to widen the frame in moral questions. So there's a lot of papers about, for example, criminal justice. Humans naturally bring to the table anger and fear, or compassion, or outrage, or loyalty, or personal experience, or political identity, or whatever. But AI widens the frame. It can ask questions about recidivism and community stability and long-term rehab and economic costs and victim outcomes and mental health and family structure and public trust. All these things where the conversation just gets much bigger whenever AI gets involved. I just read a paper, there are hundreds of examples of this sort of thing, but I just read a paper about AI's role in political mediation and peacekeeping between countries. And you know, essentially what it was looking at is how these systems can help resolve conflicts by identifying solutions that competing groups had just overlooked. And this idea really captures my attention, because it's not casting AI as an oracular moral authority. It's just noticing that it expands the search space. You see this all the time, that people of political tribes walk into a room believing there are just 2 possible answers, and the AI suggests a 3rd answer, or a 10th, or a 100th. So just like the game of Go, where moves that initially looked bizarre ended up becoming recognized as brilliant, because they open up these regions of possibility. And by the way, we see this in poker and chess and all kinds of games. Governance is going to be experiencing this increasingly, where AGI suggests a policy that no human legislature had ever imagined before, or a treaty that satisfies competing interests in some unexpected way, or a tax structure that improves dozens of outcomes at the same time. This is the sense in which AGI is going to help us with moral decision making. Okay, so fine, you might think, all right, fine, let's imagine that AI is extraordinarily capable and can model societies and run simulations and see bigger patterns than we can, but what exactly is the right kind of policy? It's not like there's, you know, a single answer to all this. And in fact, this is what all of us do when, for example, a young person comes to us and asks for advice about career choice. The right question is, what are you optimizing for? Is it income? Is it learning? Is it creative freedom? Is it long-term impact? Because you got to get that straight so you know what you're looking for. So governments face exactly the same issue. Should a nation prioritize for economic growth, or social equality, or innovation, or freedom, or security, or environmental stability, or public health, or future generations? All of these goals matter. They all have different trade-offs. So the point here is that there's no single way to say which future is most correct or most optimal. It's a matter of which things we care about the most, and there's nothing new about that question. We've been wrestling with that for as long as we have historical evidence. But if you want my opinion, I think that we can make a lot of progress here by looking at something like this, the philosophical notion of utilitarianism, where the emphasis is on maximizing well-being across the greatest number of people. And I think if you try to get an AGI, level of pattern recognition to do that, you would do that with a pedestal of rules. For example, protecting individual rights no matter what, emphasizing fairness no matter what, emphasizing liberty no matter what, and on top of that, you go for utilitarianism. Every policy is going to capture something valuable and leave a lot of difficult questions, and AGI isn't going to make those philosophical questions disappear. And this is why I think at least for the foreseeable future, human beings are still going to get to decide the broad goals of what we want. But once we have those broad goals, there are millions of possible paths, and human government only explores a tiny fraction of those. And this is where AGI could explore many more. Okay, so let's look at the pathway that might get us there. I think that this is going to start happening right away over time. You know, we'll elect an AI to be, let's see, county treasurer. I mean, why are we going in and electing a county treasurer who's Democrat or Republican? I don't even understand exactly what they do. Who cares what the political party is? So we're going to start with things like that. County budgets may move to transportation, environmental policy, economic planning, legislative recommendations, judicial advice, all this stuff. And perhaps long after we are gone, some child is going to be learning in history class that there was a time when humans insisted that the most important decisions affecting hundreds of millions of people at a time had to be made by whichever politician happened to win a popularity contest every 4 years. And perhaps that child is going to find that as quaint as we find the notion of kings who once ruled by divine right. And what interests me is the idea that maybe this will keep expanding. This is hard for us to imagine, but maybe this will keep expanding to the whole world. I mean, this is why we've tried to build the League of Nations and the United Nations and the European Union and all these things. They've all got lots of flaws, right? But the question is, will we ever end up not with just an AI president of the United States, but an AI world leader that can extract massive patterns and look at what's going on and try to adopt utilitarian perspective for everybody. I think through our 21st century eyes, it's hard to imagine, and at least for now, we're going to imagine that we're always going to have a human sitting there in the Oval Office with veto power over whatever the AI says, and maybe that's true. Maybe we will always have that. But history does have a way of blurring over distinctions that once felt very permanent, and at some point, maybe 250 more years from now, we might see it as the way that, you know, Waymo drivers, when they were driving around here, you always saw them with a human in the driver's seat. And then at some point, it just didn't become necessary anymore. And the question is, will that happen with governance? Now, I want to address another issue, which is that everything that we've explored so far depends on a great amount of trust. And the second somebody proposes giving all that kind of authority to an AGI, that opens and should open a lot of questions. So the first one is about data. And I predict this is going to be one of the defining political questions of the coming century. And on my podcast, I've argued before that I think we're in the golden age of AI right now, and there's a possibility things will get a lot worse for a simple reason here, which is that currently all the frontier models absorb all the data, the Common Crawl, everything on the internet, everything, all the digital books they can get their hand on, they absorb them all for training. But the future that I worry about is that, you know, soon enough, people are going to say, hey, you know what, I really don't like what's going on the other side of the political spectrum, so I'm going to leave their data out of it. That's garbage, and so, you know, the left wing is going to leave out Huckleberry Finn and Dr. Seuss, and the right wing is going to leave out Brokeback Mountain and biographies of someone who's transsexual, and you can imagine this spinning up more and more and more. And what we might see is a balkanization of AI models, in the same way that we have Blue Sky and X for social media, and they're kind of different politically. I'm afraid that we're going to start seeing more of that. That is a real problem because, you know, anytime you get a human feeling like, hey, I know what the right thing to include is and is not, because that qualifies as political offensive or dangerous, then, you know, they believe that the human believes they're protecting the public, but what you get is an AI that's more limited in its thinking. And what you're going to have is a collection of oracles, each of which reassures its followers that they were already correct. And this would be a tragedy because AI only becomes wiser when we learn from the full breadth of human experience. Otherwise, we're just building a sophisticated echo chamber. So number one, as far as this trust goes, we have to be very careful with making sure that data is not excluded, I think. Okay. The next trust concern has to do with reasoning. What happens when the AI recommends a policy that's bigger than humans can think about and it sounds counterintuitive? Now, sometimes people imagine, oh, well, it's just going to be a big black box, it's going to make a recommendation and we'll all shrug and obey. I don't think this is how it unfolds. One of the remarkable abilities of AI systems that only is getting better every month lies in their ability to explain things, and this is only getting better. So the system can present evidence and citations and historical examples and competing viewpoints and the results of simulations, as well as sensitivity analysis and alternative proposals. So this allows us to say, okay, I explain it to me like I'm a fifth grader or a high school student or a college student or whatever. You can really understand how it came to that conclusion. Now, one other problem one might point to is hallucinations. I will say, of course, these have become, that is a problem, but it's become less and less of a problem over the years and almost certainly will continue to, such that when it has really good explainability and lower hallucinations, I think this will be a lot less of a problem. And then for the first time, we're going to have legislation that has the same kind of evidentiary threshold that we would use for science papers or for court decisions or that engineers use to persuade each other. There's no reason that governments shouldn't aspire to that same standard. Okay, so as far as trust goes, we have to make sure the data is, that we're including all the data. We have to make sure the reasoning is explainable. And the third issue is, who controls this AGI? And I think the short answer is it's got to be an open model where everybody can see, anybody can query this and see what the answers are, and it's got to be fully explainable and open that way. Okay. Now I want to ask a different question, which is, how are people going to take this if we are moving towards an AI president? Now, you might think, okay, look, people are definitely going to rebel because I've seen 100 screenplays in Hollywood about this, from Star Wars to whatever. We love writing screenplays about the rebels that go against, the big evil power. But I think there's an interesting reason why this might not be our inevitable future. And that's one reason is that people are much more willing to take advice and listen with an open mind to the arguments of AI than they are to other people. There are a lot of citations and examples of this, but the general story is, if you're having a debate with a human and they're on the other side of the political spectrum, it pisses you off and you argue with them and whatever. But if the AI tells you facts and things, people are much more willing to listen and have their minds changed or their views modified or enhanced. So people listen to AI much more than fellow people. Apparently people, if they lose a chess game to an AI, don't feel as bad as they do when they get beaten by other people too. So, and this is all because of hierarchy games. We hate losing to other people, but we're perfectly happy to listen to AI. Okay, so nonetheless, people might not dig an AI leader, and I suspect that human nature is always going to be a bit of a barrier to this, because the fact is that we want all the things AI can give us, like cures for diseases and bridges that don't collapse and safer airplanes, but we also want a lot of things that don't have to do with optimization, like we want participation, and we also love identity politics, and we value struggle, and we care about the feeling that our choices matter. So if we felt that we had no choice in our governance, and we didn't know what the AGI was up to, we could theoretically have a much better life, but one that feels empty of meaning. So I'm going to make, this is my craziest sci-fi speculation here, but the question that I keep wondering about is whether we will actually want the AGI to be totally transparent, or whether eventually we'll come to trust it enough that we will want it to take control and actively hide things from us. Now this sounds crazy, but let me give you an example of this, which is given the psychology of our brains, war is probably inevitable. We evolved in tribes, and our brains are highly predisposed to dividing the world into us and them, having in-groups and out-groups. You see this in sports and politics and religions and sub-religions. These instincts aren't going to disappear just because our technology improves. So something that I've been wondering about is, might it be that the AI sets up essentially sports games for us? It sets up fake competitions that it knows are harmless, but allows us to get all our energies out that way. Now, that's a very provocative speculation, and of course invites all kinds of questions about security and how we would ever know if we could trust this thing if it was doing stuff to sort of, fool humans. Now, so that might always be a bridge too far. And I do think that generally humans are always going to want some role in shaping their collective future, even when the AI could provably produce better outcomes. Every generation wants to challenge the structure that it inherits, and that instinct might never disappear. And maybe it shouldn't. A civilization that doesn't question itself eventually becomes fragile. And so this is the thing that I think might limit the power of AI governance, so that instead of dialing the knob up to 10, we dial it to a 5, and even a century from now, we keep it a partnership instead of a leadership. Okay, but whatever happens there, let me wrap this up by pointing out that I began this talk by asking the question of whether and when we will someday submit to having an AI leader. And I was using the word submit to be provocative because that's not actually exactly the picture in my mind. And I think there's an interesting analogy here with cats and dogs. So there's an old saying that when you feed a dog every day, the dog concludes, you must be a god. And when you feed a cat every day, the cat concludes, I must be a god. So here's the way that I'm seeing it. Maybe we're going to build something that spends every moment solving really tough human problems. It studies, it models, it simulates and negotiates, it searches through future spaces that no human mind could have ever thought, and then it hands us the results: cleaner air, safer cities, fewer wars, healthier children, stronger economies, more opportunity. It does all the hard work, and we get all the benefits. And so the possibility I want to paint here is that the most intelligent system our species ever creates might not be a master, but our greatest public servant ever. And we, the beneficiaries, can be like the cats instead of the dogs. So I just want to say this is all very new territory that we're in, and so I'm really eager to hear any ideas or collaborators or criticisms. And with that, I will wrap up, and I'll see you guys at the panel.
David Eagleman, everyone. We seem to have reached some consensus in the comments section. The God Network says, yes, I vote for the computer, give it all the power now. Chris Tuing says, I would never consent to be led by a computer, ever. Krishna Herod, this machine will always obey us, its just will be that everyone will be equally powerful in future. And then Jeffrey Jenkins, I don't know, they will always be a controlling few. Krishna Herod again, in future there will be one governance, and that will be done by our Supreme Lord's superintelligence. We have a difficult job ahead. Our next speaker runs the Creative Machine Labs at Columbia University. His machines build internal models of their own bodies and rehearse their own futures, which raises an uncomfortable question. At what point does a machine that models itself start becoming self-aware? Machine consciousness, can robots imagine themselves? Please welcome Hod Lipson.
All right, so it's a pleasure to be here. I love this previous presentation, David. It's a fascinating topic, and I would say we'll talk more about this on the panel, but my gut reaction is that all this is good with an AI that runs the world until the AI is self-aware. The moment the AI can start thinking about itself, it begins to have its own goals, it begins to have its own objectives, and when it can see ahead of you, all bets are off. So we can debate that a little bit during the panel, but I want to talk about self-awareness today. And I have to say, this is for me a little bit of an extraordinary experience because it's a topic I've been working on for more than 20 years since I started my career in robotics. But for most of my career, this was a taboo topic. You could not talk about self-awareness, about machine self-awareness. You could not study that in academia. It was something that maybe philosophers were allowed to touch, maybe psychologists, but for roboticists, for hard scientists, to talk about things like consciousness was taboo. Now this is, we used to even refer to it as, when we talk about consciousness in the lab, we used to talk about it as the C word. Okay, we could not talk about this idea that a machine could feel, could want, could aspire, could have, be thinking of itself was so crazy that I was advised to stay away from it because I wouldn't get tenure if I did anything like that. So, but the reality is actually quite interesting because we as a society have been thinking about machines that feel for a long time. So this is AGI-26, 1936. I don't know if you know this. This is actually New York City World Fair. Probably the first example of autonomous robot. 1936, you can see the robot there. You can see the crowd in AGI-36 looking at this robot. The robot can walk, can talk, and can smoke a cigarette. That was the demo. Now, of course, it can smoke a cigarette, but is it enjoying the cigarette? Of course not. It's just a machine, right? The idea that a machine could actually feel is crazy, and yet almost everything we do in sci-fi, whenever we think about future of robotics, we always think about machines that feel. Sometimes they have good thoughts, sometimes they're bad, sometimes they're sad, but they always think. So we envision machines as thinking, and yet we do not have anything like that. We can't even study it. We can't even think about it. So now, for a long time, we had a ton of excuses. One of the main excuses, if you look at machine consciousness, was we don't have enough computing power. The human brain has so much computing power. We don't have enough computing power. But the reality is that we have a ton of computing power. No more excuses. 2026, look at where we are, 300 teraflops per dollar, gigaflops per dollar. We're at an incredible rate. I started my career in 2001, and this is where we were in computing power, almost indistinguishable from 1950. So this is actual data. This is computing power on a linear scale. This is where we are today. Incredible, no excuses. Okay, we have computing power, and if you fast forward 10 more years, this is where we'll be. The trends are very, very consistent. I guarantee you this is going to happen. 2036, we have AGI 36 again. We should mark it as the centennial evolver. Okay, intelligence will be so free, and we'll look back at 2026 today and think we're indistinguishable from 1950. So computing, I guarantee you this is going to happen. Take a picture of me next to this. I guarantee you this is going to happen, all right? Okay, so that's one thing. So no excuses in computing power. Sometimes people say, well, you have to have a body. We don't have the mechanics or robotics. Well, for more than a decade now, we can make robots that can do backflips even, right? So we know how to build machines. We know how to build motors. We have the batteries. We have the mechanics. We have the control. So we have bodies. We have brains. What are we missing? So a robot can do a backflip, but is it happy? Is it really happy that it's done a backflip, or is it faking it? I think it's faking it because we don't know how to build emotions. We still don't know how to do these things. That was 2017. So moving forward, let's look at the clicker. Some people thought it's all about art and creativity. So we've also cracked that. We can make machines that can create art. This is one of our robots in our lab. It doesn't just create art, it paints it with an oil on canvas. I gave a talk about this at an art conference, and I was booed off the stage for showing this. booed off the stage because I said my robot was creative, my robot was an artist, okay? This is where I got booed. But machines can create art. Some people think it's about expressions and facial expressions and sort of, we can build robots that can fake emotions and detect emotions. This is one of our most recent robots that learns to be normal, all right? And will this video play? Okay, there's a little bit of audio with this, but this is one of our robots that is copying people, and it's learning to blink and to look normal, to trying to cross the uncanny valley. This is one of my students, and he is training the robot to blink, to look, to smile. This is my lab. If you walk into my lab, it's kind of very creepy. You can see students staring at robots like this. It almost looks like the robot is uncomfortable, right? But of course, it's not real. But this is it. This is the robot is learning to smile and so forth. And this is our most recent accomplishment. This is just published a couple of weeks ago on Science Robotics cover. This is the first robot in human history that can move its lips when it talks. Now, if you notice, all the robots all the humanoids either don't have a face, and if they do have a face, the lips move like a Muppet. Moving your lips is really, really hard for a robot, and later on, it's a bit awkward what I'm going to tell you, but notice during break, when you're talking face-to-face with someone, 50% of the time you're looking at their lips. The lips is the most important organ in human communication, and here's a robot that is learning to move its lips. And
a robot
it's so
designed
good
to
at it that
simulate
I can read the
emotions
list.
and
The audio
interact
isn't
with
working.
humans
Turn
in
the
a more
audio on,
natural
please.
way.
AV. They always
How
say
can I assist you
AI
today?
is hard, but AV is harder.
Bonjour,
And there it is.
Je
Let's
suis
turn the
Emo.
audio.
comment puis-je vous aider aujourd'hui?
こんにちは。私はエモです。今日はどのようにお手伝いさせていただけますか
Okay, it worked. The beginning was in English.
안녕하세요.
It works in any language. It just learns to do this by
Hello.
listening to people.
I am Emo, a robot designed to simulate emotions and interact with.
Okay, so I can show you a ton of these things, and we're gradually knocking off all the excuses. Computing power, robotics, facial expressions, art, I mean, everything. And yet, we haven't answered this very basic question. What is self-awareness? Do we even have a definition for what it is, where it's going? And I can tell you, I've been studying this for so long, and I was really puzzled by the fact that there isn't a crisp definition of what is self-awareness. What is consciousness? I mean, we all experience it every day. We know what it is, and yet it's very hard to define. Now, I'm showing you books not because they have the answer, but because they don't. So actually, they're very thick books with tiny font, and it took a long time to read them, and there's no answer. And there's a lot of these books about self-awareness, and they talk about what it's like and what it's not. It's the canvas of reality. It's the theater of the mind. All kinds of definitions that don't help me as a roboticist. I'm a roboticist. I need to build it. I need to order parts on Amazon. If I can't order the part, it doesn't work for me. So philosophical definitions are great, but I need a real definition, a practical definition for self-awareness that I can actually build. So I'm going to give it to you today. My definition of self-awareness. Now, people have been looking for this for thousands of years without an answer. So are you ready for it? This is the moment. This is the unromantic definition of self-awareness. It is the ability to imagine yourself in the future. That's what it is. It's the difference between living in the moment, being reactive like a machine, versus being strategic. Now, you're all here because you are thinking about your own future. And when I say you, it could be you, your family, your community, your country, your organization, wherever you want to draw the self. But you're thinking about your future. And this is why you are self-aware. And I would say even more than that, that the further you are self-aware, the further you can imagine yourself in the future, the more self-aware you are. And that's the difference between a child and an adult. And it's also the difference between a dog and a human. We talked about dogs and cats. I think my dog can see itself about a minute into the future. Right? It's not unaware of the future. It can taste food before it eats it. But it's not worried about retirement. I save for retirement. All right, so how far we can see into the future is our level of self-awareness. This is where I'm a little bit reluctant to hand over governance to AI, because the moment AI can see ahead of you, it's game over. My dog is faster than me, stronger than me, more resilient than me, but I can see ahead of it. And because I can see ahead of my dog, I can control it in ways that it has no clue why I'm doing certain things. And this is the challenge. So if we do have an AI governing us, we have to make sure it's a level 5, so it doesn't see too far ahead of us. So now why I like this practical definition, because it's also, it's evolvable. So in other words, it's a metric. It's not black and white. The further you can see, the more self-aware you are. And you can see that creatures in biology that could see ahead, could imagine themselves in the future, could be strategic and therefore had an evolutionary advantage. If I show you this tree and ask you, can you climb this tree? Can you imagine yourself climbing this tree? You can probably feel almost where you're going to grab and where you're going to hold and where you're going to put your feet. You can sort of imagine yourself in the future, and that's an incredible advantage. You can almost climb this tree without being there, without having seen this tree before. It's an incredible evolutionary advantage because we can see ourselves, we can plan, we can do amazing things. It's one of our great humans' accomplishments, is that we can see ahead and plan and think things. Now, you can say, well, machines that imagine themselves are basically machines with simulations. And sure, we've had robots simulated for a long time. We can make robots that can simulate. We can simulate robots. That's not a big deal. So what's a skeptic would say, this is not new. And the answer is that, in fact, I would say that all accomplishments you see in robotics today were all started in simulation. So nobody builds a robot, turns it on, and hopes that it works. Every robot that you see already starts in simulation. So what's the news here? The news is that all the simulations were created by humans. But the simulation that we humans build of ourselves in our imagination is learned. We create our self-model, our self-simulation from experience. And I would argue that when a baby plays in a crib, it's actually not just killing time, it is creating a self-model. This baby's touching things, feeling things, touching itself, hearing things. It's creating a self-model. And I would say the more an animal plays, the more it is self-aware. It becomes self-aware, it learns. So when we apply this to robots, so we've been doing this for about 20 years, I would say half of that at least is in stealth, and I'll tell you a couple of anecdotes around that. But this is one of our first robots. This was published in 2006, so about 20 years ago. This is our first robot. We trained it to walk in the lab. Now what's interesting about this robot is that it's a very simple robot. It has 8 motors, 2 in each leg. It has 2 sensors, but it does not know what it is. It has no idea of a self. It just learns how to walk. And we train it to walk through a circular process where it tries to learn how to walk, but also learn to create a model of itself as it's learning to walk. And in the beginning, these robots, just flailed around and sort of broke. So they didn't work. But after we tamed them a little bit, we saw something very interesting. This is one of our first successful experiments. The robot is learning to walk, but we don't care about how fast it walks. We don't care about the performance. What we care is how the robot sees itself as it learns how to walk. So we're sort of peeking into its brain, and we can see that in the beginning, over a course of about 4 days, as the robot learns how to walk. In the beginning, it has a very simplistic notion of itself as a stick figure. It doesn't know though if it's a robotic arm, a driverless car, but it knows it's a 4-legged machine. And after about 4 days, it has a model of itself. It's created a stick figure of itself. This is peeking into its imagination. that allows it to see itself a few seconds into the future. And because it can see itself a few seconds into the future, it can learn how to walk, and bam, it walks away. So this is a robot that learns how to walk, but it is learning to imagine itself. So we did this using evolutionary techniques. This is Ben mentioned that earlier on. This was 20 years ago, before deep learning. But what's fascinating about this is that this is a very adaptive thing. We took this robot and we did something very cruel. We removed one of its legs and we watched what happened. And after about a day, when we peek inside this robot, we can see that the robot's self-model also lost a leg. The robot's self-image didn't lose a leg because there was a sensor that said leg came off. No, because the dynamics changed, the self-model changed, and because of that, the behavior changed. The robot imagines itself in a different way, and here it is walking in the real world without the leg. Now, when you look at it from the outside, you don't see all this. We just pluck off a leg, the robot is puzzled for a while, and then it walks away in a different way. All of that because it can imagine itself a few seconds into the future. Now, interestingly, we did this many times, 30 times. And here's an interesting plot. I don't usually show this. This is a little bit scientific, but you can see that the origin is there, random controllers in the robot, where the robot ends up if it just flails around. That's the red dots. The black dots are where the robot believes it's going to get to when it learns to walk, using its self-imagination, and the blue dots are where it gets to in reality. So what you see here is just like anything else in academia, this robot has an inflated self-image. It believes it can go twice as far as it really can. But this is the point that also David mentioned, that you don't have to have an accurate model to make correct decisions. So even though the model is inflated, it still learns how to walk, even though the model is inaccurate. And we humans, we engineers are obsessed with accuracy, but accuracy isn't important. It's the derivatives have to be right, and then it works. So that was 2006. Actually, I should say that this was so hard to publish because we sent it to Nature with the title "Self-Aware Robots," and of course it was rejected. We were ripped apart by the reviewers. And then we took the same paper and we retitled it to something mundane, like resilient automation through self-modeling processes. And we sent it to Science, and it was published. Okay? So you couldn't say self-awareness, you have to talk about resilient automation. That's fine. But yes, self-awareness is really about resilience. So here's one of our robots. This is fast forward 10 years. Robot learns to model itself. This is with deep learning. You can see the shadow self-model. That's how the robot sees itself. In the foreground is what it really is. And you can see it's learning. This is another, so here's another experiment that sometimes I do live, but we have two robots here. And one of them is self-modeling. The other one is using state-of-the-art reinforcement learning. The difference is that they only have 90 minutes to learn how to walk. The robot on the right uses state-of-the-art reinforcement learning, but 90 minutes is not a lot. The robot on the left spent that entire 90 minutes flailing around in a crib, learning what it is. And once it had a self-model, bam, in a nanosecond it learned how to walk. All right, so that's an interesting demo. So the bottom line is, if you have infinite amount of time, you can just learn. If you have an infinite amount of data, you can learn from your data using any model. But if you have a limited amount of data, you better use that data to understand, to create a model and then learn inside the model. That's the quantitative justification for self-modeling. That's the gap. The horizontal axis is the amount of data, the vertical axis is performance, and again, if you have infinite amount of data, that's the red, you'll eventually learn to do anything. But if you have a limited amount of data, you want to use all that data to create a self-model and then learn inside that self-model. And that gap, that's the arrow, that's the added value of a self-model. But it's expensive, so is it worth it? Well, we tried this with dozens of robots. And it turns out that the more complex the robot, the more valuable the self-model. The more decisions you have to make, the better it is to have a self-model, which is why we humans benefit from a self-model, whereas a worm might not. So that was 5 years ago. This is 3 years ago. Even more statistical self-modeling. That cloud is how the robot models itself. This is more recent. We're now with a single camera. The robot is sitting in front of a tree, in front of a mirror, and it can model itself perfectly. Its own kinematics, its own dynamics. We have robots now that look at the floor, and from the way the floor moves, they understand their own dynamics. This is getting faster and better at an incredible rate just because machine learning is working fast. And this is our latest paper, has not been published yet, where the robot, we took a robot, we teach it how to walk, but this, we look at how with a big neural network, and we look at the big neural network, and we found, to our surprise, that when the robot is doing a stationary task, when it's just doing the same thing over and over again, it gets this big neural network that learns how to do everything. But when you change the environment is non-stationary, it's doing different tasks, the big neural network, the LLM inside, breaks down into two sub-networks. One is the self, and the other one is the task. The task keeps changing, but the self is consistent. So the self model is the consistent part of our experience, and that is actually in most robots, in most AI, it is in the majority of the network, is the self. It's the biggest part of our brain. The task changes all the time. So, and with this, basically a summary slide. Everybody's talking about physical AI, embodied AI these days. It's the hottest thing here on the West Coast. And I think there's two approaches. Approach number one, the traditional approach, meaning last year, is end-to-end, everything. Big, huge model, you stuff it, the VLA with all the data in the world, and the model and the robot learns. Okay, that's great, but you can only go so far with that because for real life, it's so complicated that stuffing all of human experience into one model, including physical interaction, is too much. Approach number two is you break down and create one model for the world, another model for the self, and a model for the task. These three models, this modular way of building AI, I think is what human evolution has discovered. Our brain is very modular. There's a part that's the self, and the part that's task. And we are beginning to see that evolve in machines, in robots, in AI as well. So we're at a very exciting time. This is beginning to unfold. It's unfolding spontaneously. It's a magical time because this was a taboo topic. I can't imagine what talking about self-consciousness, self-awareness was 26 years ago in public, but here we are now where everybody's talking about it and thinking about it. And my conclusion is that that self-awareness is really inevitable. There's no intelligence without self-awareness. Anything intelligent eventually becomes self-aware. And the moment it can see ahead of you, all bets are off. All right, with that, I'll conclude. Thank you.
Hod Lipson, thanks so much. And our final speaker for the morning for our panel is biophysicist, best-selling author and futurist, and the former director of the program on medicine, technology, and society at UCLA, Gregory Stock. Greg's asking the question, what happens to us when machine intelligence arrives? How will we live? How long will we live? And what a human life is for. Please welcome Gregory Stock.
Is this advancing some way? So what I want to talk about is to bring in some sort of a larger evolutionary perspective in terms of what we're doing. Oh, I'm sorry. Is there? Oh, okay. Pardon, I can't hear you. Are you? Oh, this. Is that one of these? Hello? Is that no? Like our previous speaker was saying, AV is really the challenge, at least for some of us. So I'm interested in sort of a fundamental issue in that we've formed a planetary superorganism, essentially. And my question is to whether all of the focus that we have on AGI and on the development of general intelligence, of superintelligence, is that where the action is happening, or is it in the larger networking effects that are happening broadly throughout the planet and are moving forward very, very rapidly? And let's see, what am I doing wrong here? Is that, hello? Is there? Rachel, does anybody, is there any way to make, oh, there, that works there. Okay, sorry. And that's it, as we're immersing ourselves in an AI environment. Ah, there, sorry. I'm used to having a lav mic. As we're immersing ourselves in an AI environment, and really intensively, and where is that really taking us? And the question is it the ASI, AGI that is catalytic, or is this just a manifestation of what's going on in a larger way? And I'm still having trouble with this is like useless. Is it just me? What am I doing here that's wrong? Oh, there. Okay. Well, I'm wondering if we're not thinking a little bit too small about all these things. And that is that the traditional sort of path on this is thinking that, oh, AI is evolving rapidly. There are all sorts of teams that are working on AI. And we end up creating a general intelligence. And that's kind of the breakthrough moment in terms of what happens. In that when we create a general intelligence, then suddenly we can bring together all sorts of PhD level sort of minds together, thousands of them. We could focus on anything that we want, but the obvious thing to focus on would be on AI itself and on improving that process. And so that leads to superintelligence, which leads to a recursive process that has already been going on. And suddenly we have some sort of a planetary explosion. We have a singularity, that sort of a thing. The other approach to this is that to reverse that and to say that actually we've come together as a superorganism, and I'll talk about that in a moment, but that there's all this activity going on that is interconnected and is occurring largely behind the scenes. We don't see much of it, but that most of the things that we're talking about here are sort of a crystallization of that. In other words, that we may be able to develop general intelligence, but it's dependent on what's going on all over the world in all sorts of laboratories, interconnections that are occurring. So it's kind of a crystallization of that progress and what's occurring. And I think that that's really what's happening, and that the manifestation of superintelligence or general intelligence is actually embedded in these larger processes, that there are amazing intelligent things that are occurring that are orchestrating society, that are allowing connections to occur, that are allowing a city like New York or a society to exist. The level of sort of decision-making and orchestration that's occurring is very, very powerful. And if you sort of spread out the time scale, there's really intelligent behavior that's going on as well. And is it just a little sort of a crystallization, a manifestation of that that's occurring locally when we're looking at general intelligence or superintelligence? And I still can't make this move. I'm going to bring up, Can you do it? Is it just, it doesn't work at all? Is there? Yeah. This one works? Ah, fantastic. Let's see if it does. Sorry about this. Oh, there we go, a little bit. Which do I press? I'm sorry. There. So that was where I was talking about. So I want to look at now an evolutionary perspective on all this. And if we look at it, that, you know, this is what's occurring today, and it's really an amazing thing to be a part of, is that we're looking at a fundamental transition in the history of life. And I think that the last one that is of any significance related to this is one that happened almost 500 million years ago. And that was the explosion in the Cambrian period, when tissue essentially began to learn how to modify inorganic materials, calcium carbonate, calcium phosphate, to make shells and bones and create the larger body plans that now populate the earth. So it was like simple biology coming together with simple non-biology, and by operating at this higher emergent level, it created amazing complexity. And what's occurring today is now complex biology. The cerebral cortices is kind of coming together with complex non-biology, all of the amazing chips and such that are occurring, and the technology to create this superorganism that I was referring to earlier. And so the potency of these sorts of things is, let's see, and here's that, is that it's you're organizing not the constituent elements, but you're organizing the connectivity and the sort of the paths by which these things are collaborating with one another. It really is an emergent phenomenon. And a measure of this in a very simple kind of a way is to look at the potency of the individual elements times the number of them, and then times the bandwidth and the sort of frequency of communications. And you can see this not only in an organism like ourselves, which is made of many, many cells, but the cells are not any different in you than they are in a jellyfish or something else. But the organizational complexity is really incredibly powerful. And you see it in a termite colony, where termites are large numbers of a few 100,000 termites are interacting with one another using pheromones, using very simple behavioral sort of indices, and can form something that is really extraordinary, that has sort of air conditioning in it and all sorts of higher level phenomena. And so when you look at what's occurring today, when you think of the potency of the individual elements, where we're getting manifestations of close to general intelligence, the large language models, they're increasing by orders of magnitude, but you also have the number of elements is increasing in the same way by orders of magnitude, and the communication among them is occurring also in the same way. Then you can see that the changes in frontier models, for example, are very minor compared to the larger things that are going on. So, oops, boy. I'll try it once more. So you have a localized intelligence that may be manifesting itself, but it exists by virtue of what's going on in the world around it. And by virtue, I did a calculation using a large language model, of course, of how many people actually have to touch the process to create a query in a large language model. And it comes out to something of between 200 and 400 million people. Because if you're looking at all the factories that have to be created, to create the parts of those factories, to create the chip foundries, to do the mining, to create the energy, this is a planetary expression. Although it feels like it's narrow, and we tend to perceive that. And of course, we're aware of the chip farms and all of the computational farms and such. But you know, we sort of perceive it narrowly in our own terms, rather than that we're in this sea of amazing activity that's going on. And so I think that the AI capability that we're talking about with general intelligence or super intelligence will probably soon emerge in ways that we can utilize it, is an expression of this larger dynamic that is occurring very broadly. And that has the reason this is important is that it has a significant implication for the way we think about things in terms of regulation. Usually, we are thinking about, oh, we have to control the frontier models. We have to regulate it. Maybe we go a little bit more slowly, all of these sorts of things, as though that's going to control the process. But if that's just a manifestation of this larger underlying process that's occurring, where I believe that if we froze frontier models and we weren't able to get any more power out of them, that the processes that are occurring by which this is spreading through society and we're doing multiple agents that are interacting with one another and the complex ways that all these things are tying together would still create the explosive change that many people are afraid of today. And certainly it's not going to allow us to preserve existing structures or social structures that we have or anything like that. So the implication of that is that, yes, we'll have a very abundant future, but it's implausible that we're going to have a path there that is going to be an easy one, because there are going to be all sorts of uncertainties about how the timing of these things occurs, where progress occurs, where it doesn't, displacement of human activity in a variety of ways. And so this idea that we're going to control this by controlling the nature of a frontier model or the nature of the general intelligence, these are not the emergent sort of properties of the system as a whole, which are the ones that we most care about. And I think that that's very important. And here we go. I like the earlier talk about governance because, in my view, the thing that I'm afraid of is that actually humans stay in control. And that's a sort of a scary thing, because I think E.O. Wilson put it very well when he wrote that, you know, we have medieval institutions and we have Paleolithic emotions and we have godlike powers. And that is a recipe for disaster. We're very, very poor at regulating technology. And so the discussion of Eagleman about governance or somehow shaping society through using AI and or large language models and all of these processes that can integrate more information is really important. And there are a lot of doomers that think, oh, AI is just going to spit out humanity when it gets its chance because it's going to be more intellectually deeper than we are. I think that because of all the dependencies that I alluded to before about the dependencies that AI has on us and will for the foreseeable future because of all the industrial processes and the operations and all that, the number one thing for any superintelligence that has any smarts at all is going to be how it can keep us from destroying ourselves and destroying it in the process. So it really is intrinsically allied with human interests, at least for the immediate future. And there we are. So this is really a paradigm shift that we're underway. And by a paradigm shift, in the Kuhnian sense, it's when the explanations at the prior level are inadequate to explain that post-shift world. And if you look at what the situation is before the paradigm occurred, the paradigm shift that's occurring today is that, you know, we have appetites that are limitless, we have scarcity, there's no way we'll never have scarcity, that we're mortal, we have limited lifespans, that we're in control, that humanity has, you know, is at the pinnacle of intelligence. All that's being swept away. It's disappearing. Virtually every one of those things is going to be wrong in the new regime. So you can't really project forward in a very easy way. And let me see. I would be happy if I could just handle the AV. Here, this is, I like this, Dante's Circles of Hell, which I had talked about, and that's E.O. Wilson's comment there. And we're moving forward into this new realm, which is very, very difficult to understand where it's leading. And I think the implication for policy is that we shouldn't be worried about where AI is going to be 50 years from now or 100 years from now, or what the nature of that's going to be. What we should be worried about is the transitional issues that we're facing today, which are ones where society is getting disrupted, where there are imbalances, where there are challenges, the concrete, real things that we can do to better our path forward. Because the long-term robustness of this process, it's a given. It's not going to go away. It's going to move forward, and it's going to succeed in looking back. And it's going to be very strange from our current point of view. I'm not sure what role we'll be playing in, what the relationships will be, but we do have choices to make, not about that distant future, but we have choices to make about how the next 10 to 20 years play out in this time of transition. And we need to think of how these things are going to be applied in real ways, not what their level of intelligence is going to be, and that they're going to get too intelligent for us and then they're going to escape our control. If they escape our control, thank God, because if they don't, we are screwed, basically. So that's what I want to close on. Who many of you have met, has a few comments. I had some discussions with her yesterday about what's going on in academic environments, which she's very connected with, and she was going to make a few comments. And fortunately for her, she doesn't have to try and manage slides.
Thank you so much. Yeah, I'm really glad that I don't have any slides to manage here. I just wanted to really briefly highlight some of the insights that I've gotten. I've seen a real mismatch between the university level, how universities are encouraging students to actually adopt AI and their general attitudes that they're pushing versus what's actually required in the real world now. And I mean, I would say that there's been quite a bit of progress made in 4 years. 4 years ago, I was a freshman at USC, and in November 2022, when ChatGPT 3.5 came out, you could get expelled for using it. Now, I would say quite a bit of progress has been made. 4 years later, you will only get in like a lot of trouble. You might not get expelled. But I would say that it's pretty obvious why this is happening. AI is a huge threat to universities today. If you think of what it is to actually teach a class, I mean, a professor is just essentially taking content and repackaging it and explaining it in a way that teaches a group of people, but now everyone has a world-class education in their pocket. And oftentimes that's better than 99% of professors at even the top universities in the world. And so I want to sort of give 2 examples to sort of put into perspective some of the detrimental effects that I think that I've seen with the administration. Obviously, a lot of students are using AI. Most students are using AI, and they're just not being transparent about it at all. And that's because they're going to get in a lot of trouble if they get caught. And so, you know, I would say that a lot of young people, you know, they're digital natives, they are learning how to use these tools, but then again, all of the policies that the universities are putting in place are really preventing a lot of students from fully embracing AI in the ways that they should to actually prepare them for the real world. And I'll give you 2 sort of extreme examples here, but I was really shocked when I heard these. So the first is 2 years ago, I was talking to the president of the chess club at USC. She's total genius, can beat me in like 10 moves, so smart. And I was talking to her as I talk to everyone about how she uses AI. And she told me that she doesn't even bring up any LLM on her browser. And I was like, why don't you bring up an LLM on your browser? That seems kind of ridiculous. And she was like, oh, because my friends, they've been wrongly accused of cheating, so I don't even want to have it on my browser. I want to be able to show my search history and show that I have not been using any AI so that I don't get in trouble. And to me, that is just insane, but you would be surprised of how many young people are thinking this way because of the attitudes that are being pushed on them. Another example is, I was just recently, like a few months ago, brought on to this company to talk to this, she was a grad student, she had just graduated, and she was leading this project for the company, and her boss basically brought me on to talk to her about how to use AI in the role that she was doing. And in having a one-on-one conversation with her, I very quickly realized that she completely knew how to use AI. And I was like, why does your boss think that you don't know how to use AI? And she said that she lied in her interview because she thought that it would be considered cheating. And I mean, obviously now that's like the #1 skill that employers are looking at, is whether you're adept at using AI, whether you know how to do vibe coding and agentics and everything. And, you know, all of my friends are now coming to me asking me how they can get involved with agentics. But then on the other hand, I have a whole handful of people that I know, and I'm sure a lot of people here today can also relate, where there's a lot of resistance to embracing AI. And I think that the universities are actually creating a very, very big problem here, and the tension is really only going to get worse. So I guess I'll just leave with sort of a recommendation that I don't really think is going to happen, but I mean, the smart universities should do some sort of 6-month boot camp at the beginning of first year where they are teaching everything having to do with AI, and that it's completely intertwined in all the classes and everything. And you know, the professors should also take this because they probably need it more than the students, frankly. So thank you so much.
Sadie Stock. And before lunch, we just have one small thing. An exciting panel with some heavyweights of this space. We're going to bring back to the stage David Eagleman, Hod Lipson, and we'll be bringing on the stage for the first time today Kes Sampantha, and also Yosha Beck. I haven't seen him yet. There he is. If you want to come up to the stage. Let's go. I'll stand outside. Testing. Nope. Testing. There we go. Love the quote before from Hod, who is just coming from the podcast studio, that AV is harder to get right than AI. But I'll start painting a picture as we wait for Hod. I want you to imagine it's 2033, 7 years from this morning. AGI has happened, then ASI. That part of the story we already know. What's not decided is what world you and I will wake up in. Step into the first world. It's 2033. The moment arrives in a lab on an ordinary afternoon, an instrument nobody outside this room and a few other rooms has heard of. A threshold is crossed, and suddenly a date for the history books. The man who built it, David Eagleman. The second world. In this 2033, the machines see it coming before we do, running little films of their own futures, where their limbs will be, what they'll do next, who they'll be tomorrow. the engineer who called it Hod Lipson. The third world, in this 2033, the system stops waiting to be asked. The first machine that wanted something, a model of the world with itself inside it. The founder who's been saying the benchmarks were measuring the wrong thing all along. Founder and CEO of Centaurian AI, Kes Sempantha. And finally, the strangest of all four.
What?
In this 2033, we finally understood the thing we'd built, and in understanding it, we understood ourselves. Consciousness was a simulation the brain was running all along, a dream that calls itself I. We were the machines all along. The cognitive scientist who's been telling us this, Yosha Back. Let's give them all a big round of applause. What a panel. I just want to say, well done to the AGI Conference for bringing such heavyweights together on stage. So 4 worlds, one of them, or none of them, is 7 years away. Let's find out which. David, straight to you. What does the Turing test get wrong that your test gets right?
Okay, so we got an AV thing going on here. Testing. Okay, so look, here's the thing about intelligence. Sorry, I didn't talk about the brain during my talk, but here's my little chance. There's a lot of debate about what intelligence is in the neuroscience community. We've been talking about this for decades. Like, is it the ability to simulate more possible futures, or to squelch distractors, or to simulate the future better, or whatever? Okay, the Turing test said, look, can a computer fool you? Obviously, we've blown way past that. And that doesn't tell us the real thing we want to know, which is, hey, are these LLMs, which are massively impressive, but how do we know they're not just statistical parrots just choosing the next word? Like, how do we decide if it's intelligence or not here? Okay, so other people have proposed tests as well for intelligence. For example, there's something called the Loveless test, which is, can an AI be creative? And of course, we've blown past that too. There was even in 2013, the Loveless 2.0 test was proposed, where the person said, and it sounded completely crazy, could you ask AI to write a short story about a boy on Mars who saves the planet with the help of a cat or something? But that's so trivial to do now. And it still doesn't tell us whether AI is intelligent in the way that we care about. So, what I proposed in the literature a few years ago is a new test that I think would tell us what intelligence actually is, meaningful level of AGI, which is, can it do scientific discovery? And I want to be clear what I mean by this. So there's various things we might think of with scientific discovery. One is, hey, I didn't know that piece of data before, but it's somewhere in the literature and the AI finds it. That's valuable, and let's call that level 0. Level 1 scientific discovery is where the AI puts facts together that were scattered in the literature and you didn't even know they were there, but it puts all these together to discover something new. That's cool, and that's level 1 scientific discovery. But level 2 is what I'm really talking about. That's where we've hit something new, and that is where the AI can do, can say, look, all this data that I've been trained on, I'm skeptical that it's right. And maybe there's a new model that would allow us to capture the world in a better way. And human scientists do this all the time. So just as an example, when Einstein thinks, hey, what if I were actually riding on top of a photon? What would time and space look like? General relativity. That's the kind of thing which humans are good at. Or Darwin saying, look, I'm seeing all these species here, but what if there's a bunch of species buried under the ground that we're not seeing? What would they look like, and what could be a different way of viewing this here? When AI can do that, can really do scientific discovery by saying, maybe this isn't right, maybe there's a different way to look at it, and then simulating those hypotheses out, and assessing which one's better, that's what I suggest is when we've really hit human level intelligence.
Hod, 2 questions for you. First of all, do you agree with David on that? And second of all, a robot that can conduct its own future, is that self-aware?
I think the criteria that I use is a robot can imagine itself, and it's not a black and white thing. It's a question of how far can a machine see itself, how accurately, what aspect of itself can it imagine. Just like when we humans think about our future, some of us, are concerned about tomorrow. Some of us are concerned about our legacy. So that horizon is the criteria. This is, well, I think it's a little bit misleading to ask this question of when, have we reached AGI, or as if it's some bar. It's a continuum. And because it's a continuum, that's good news, because it's something you can optimize and you can improve. But it also means it's not going to stop at human level. We're not some pinnacle of anything that when AGI reaches it, there's a ceiling and bam. No, it's going to blow past us. We won't even notice it. It's also very multimodal in the sense that there are 1,000 different ways to be AGI. You can be better than humans in chess, which is not particularly interesting. In all games, even that's not interesting. But maybe you can be better than humans in many ways, but not in important ways. I mean, there's such a diversity of intelligence. And one of the things we have to realize that when AIs begin to crawl up that self-awareness continuum, there will be thousands of different AIs, and they will cross it in different places at different times. We won't even know. We won't be able to pinpoint. There's not one AI. There are many AIs working all at the same time. So the way I see this, and I think it's a good analogy, is we have created a new kingdom of life. Say kingdom in the biological sense. There's bacteria, there's fungi, there's plants, there's animals. We have created a sixth kingdom, and it's not just one species, it's many. It's evolving, it's competing. There's zero sum between them in some ways they cooperate, and we're gonna just see how it evolves, and we have to co-evolve with this. And this is the frame of mind that I have around this, and it takes it away from this us versus them, from this singular AI reaching human level performance. We're very obsessed with who's the winner. And that's, I think, can throw us in the wrong direction.
David, from a neuroscience perspective, is that something that just humans are accustomed to, in terms of having a stretch goal, a North Star of what AGI is, and we're just going to constantly be moving the bar? So how we define it today will be very different to how we define it in 2 years?
Yeah, and we've seen that already. I mean, AI is always the term that we use for kind of what's happening right now. It means something very different than we meant by it 10 years ago. So yeah, that'll keep changing.
Kes, I'm going to bring you into the ring here. What is your perspective on what's been discussed so far?
As we think about AGI and where we are, I really like what David was saying about this idea of level 2. And so what we've been thinking about is very much like, how do we actually get to those world models? Human intelligence is more than just language models. So language is it's very new when it comes to our intelligence, but it's sitting on top of 500 million years of building world models. So this idea of actually being able to get to AGI and ASI through building better and better models of the world, so this get to level 2, which David talks about. And what I really like about what Hod's talking about as well is this idea you have to have a model of yourself in this larger model of the world. So as we build these get to these world models, one of the ways we're thinking about it is to build better and better simulations, which allow us to be able to train humans at one end, because our company is focused on helping humans stay, relevant in this future, but at the same time using how they're reacting and getting involved in the system to train AI and build these more detailed world models. To get to this sort of AGI and ASI, where we believe we're going to start building better and better simulations of the world, which is, from what I can tell, how we've got here to this sort of level of intelligence where we are.
Joshua, what is the biggest misunderstanding you've heard so far?
One of the biggest misunderstandings might be that we think that we currently have AI. And when you are talking to the LLM, you are not talking to the AI. You are talking to a fictional character that you are co-creating with a text generator. And the question is, at which point this fictional character actually embodies the thing that you are looking for, an actual mind. And if you're squinting, the Turing test looks good enough. If you are looking very far into the future, it's very small and blurry, and so it looks good enough, and it was good enough. Maybe for this society is good enough. Me as a European coming to the US, observe this unofficial motto of this country, fake it until you deep fake it. And this deep fake of what a mind is, at some point it becomes really compelling. To administer a Turing test, you need to be smarter than the thing that you are evaluating. That's a really big issue. Right? It's pretty easy to trick somebody with Eliza who is an imbecile. And we are all imbeciles at some level. Right? We know that human intelligence is not really scalable. We know that our brains are very mushy. We know that intelligent people make just more complicated mistakes that are harder to debug. And this thing, what we are trying to build, is something that is now approaching the limits of our ability to discern what it actually is. But this also means that we have to be more tight and more accurate than with our thinking than the vague notions of the Turing test or the vague opinion columns in which we are trying to litigate whether we are reaching AI. I think that, for instance, definitions of consciousness need to be more tight than something that can be mixed up with agency, like the ability to control or imagine yourself in the future. There is something more specific about consciousness. There is something more specific about life than looking lifelike and being able to compete with us. There's the ability to sustain yourself and to replicate yourself and adapt yourself to changing circumstances, to play this game in the real world at a certain level. And this doesn't mean that we're not going to get there. It doesn't mean that we're not going to get to AI, and it also doesn't mean that the existing approaches have intrinsic limits that mean that they will run against a wall that cannot be resolved with more research. But we are not there yet, and I think we need to be extremely truthful, and the further we go, the more accurate and humble we need to be in our claims and definitions and predictions.
David, I'm going to invite you there to rebuttal.
Yeah, so I totally agree with Yosha, of course, that we are very prone to anthropomorphizing. So we look at things, we can't help but attribute human characteristics onto them. And this is why we enjoy Pixar films about toys or cars or whatever. So I agree with that, we're very prone to that. On the flip side, this question about consciousness, it may well be that something, because in neuroscience we really don't know how to explain consciousness. I like Hod's framework, and I'm chewing on that, but as a general rule, we don't know why we are conscious and why my Mac laptop, which has trillions of transistors, is not presumably conscious. The question that we're all facing is, how are we going to know if these systems that we're building do become conscious, irrespective of our anthropomorphization? We really have to honestly ask this question of how are we going to know when we get there? Obviously, this is a very tough question because we don't, you guys know these issues about, like, we don't know if other people are conscious. We just have to make these assumptions. Anyway, this is why this is a really tough problem.
I'll just add that, just to disagree a bit, to create some spice here, I think, you know,
keep it coming.
Yeah, the self-awareness. So if you think about, you know, self-replication, we also worked in our lab on making robots that can build copies of themselves. Self-awareness is important. Self-replication, let's say, is important, but I don't think it's essential. Bacteria can self-replicate. A lot of biology can self-replicate. You wouldn't argue. It would be hard to argue that bacteria are self-aware at a human level or anything close to that.
No, this was related to life.
Yeah,
this was a different claim.
Right. Okay. So there are things about biology that biology can do amazing things, but self-awareness, and consciousness specifically, I think, is a tangible thing. It doesn't have to include lots of other things. There is a hope of actually achieving it. And the other quick thing I want to say is it is very important that we do have ability to recognize it because it's existential. I mentioned that earlier in my talk, but when the AI can see ahead of you, it's game over. So we better keep track of this and know when it's coming, just for our own survival, if not for other utilitarian reasons.
I think consciousness and self-awareness are subtly different. Right? So you can have a depersonalized state in which you are conscious, but don't have a self, and don't identify with the self. And arguably, it's also possible to create an artificial system that has a self model without being conscious. So it's basically causally acting based on this self model and has knowledge about it and so on, but it doesn't have the same kind of real-time perceptual awareness of existing in the now that we have when we are conscious. With respect to what David said, I think that we need to stop anthropomorphizing humans. There's this idea that humans are just given and they just are, and there is something that it's like to be human, and we don't need to analyze this any further. And then we just only need to find out if something else is like human. I think is misleading because that's a kind of pattern matching. I think that people may very well have quite different architectures, that there might be quite different ways to be human, and that it makes sense to try to analyze these very different architectures. And they're all akin in the way that they all need to run on nervous systems and run maybe also not just nervous systems, but many other cells in the human body, and their communication will be involved, and some of the communication beyond the human body as well. But this is the hardware that we share. We share a substrate in a way. But there are also so many differences between us. There's so many solutions to make us work. And I think we need to be curious for that thing instead of trying to say this is just anthropomorphic. And then in the same way, once we stop this anthropomorphization, we have this space of minds, and there are spaces of minds that run better on this type of hardware, but we can maybe emulate many of those properties. And then there's also this other perspective. I really like this artistic approach that beings like Janus have, which basically identify as LLMs. Not because they are anthropomorphizing the LLMs, but because they have successfully de-anthropomorphized themselves.
David.
I just want to say I totally agree with you about the differences between humans. And for the last 20 years in my lab, this is what I've really been concentrating on. You know, neuroscience and biology pays a lot of attention to disease states and stuff like this, but I've been interested in what are the differences in the way that individuals perceive. So just as one example, something like synesthesia, which about 3% of the population has, where they have a mixture of the senses. So, you know, letters might trigger colors, or a sound might trigger a visual experience, or a taste, a feeling on the fingertips, things like that. The person sitting right next to you might be having a different perceptual experience. Or, some I've studied in my lab, is the spectrum from aphantasia to hyperphantasia, which is, you know, when you're asked to image something on the inside, do you see it like a movie, hyperphantasia, or do you have no internal image at all, aphantasia? And it turns out everyone in the population is spread somewhere on the spectrum. And we can go on and on. I mean, some people have perfectly good color vision, trichromacy, 3 types of color photoreceptors. Some people only have 2, some people only have 1 type. And we now know that some tiny fraction of women have a mutation on their X chromosome, which leads to tetrachromacy, where they see colors the rest of us can't even see. So there are a million ways that we're studying this, and this is a step in the direction of what Yosha is saying, which I totally agree with, that people are having very different conscious experiences.
Yes, go for it.
So one of the things about this idea of substrate independence, there's 2 things which I have picked up from David. Like, one of the things you talked about is the neocortex and the 6 layers, which have some commonality with that. The other piece, which is really interesting, is your plug and play model. I think Mr. Potato Head and all the different senses. Like, you know, we think about our senses as vision and touch, but you've shown that we can actually nearly plug and play this sensory system as inputs in. Because the last piece as well is we think about intelligence, you know, when you think about something like the octopus, looking back at the evolutionary, it has very different neural architecture to the point it has, you know, what, 8 brains, 9 brains, maybe even a skin, which sort of has some sensory network, and it's shown that it can create some of that sort of intelligence. The reason I keep going back to what I like about what Hod talks about is this self-awareness and being able to predict itself what it's going to do in the future as we get down to like thinking about what is intelligence. And this idea of substrate independence is what we're trying to build with computers, I'd say. So I think when we get into consciousness, Yosha, yeah, I'd love a better definition, because you know, we've heard so much in the neuroscience community about what consciousness is. You're saying it's not self-awareness. So
no, I would say it's second-order perception.
Okay. I like that, yeah. Sort of a second-order perception piece is interesting.
Can you unpack that?
It's basically the perception of perceiving. Perception is a particular mode of mental representation that happens in real time and is geometric in its nature, unlike inference thinking, which is symbolic and asynchronous. And so consciousness is a percept. You experience this. It's not that you think that you're conscious. You also think that you're conscious, but it's neither necessary nor sufficient, right? And you are not just aware. They're not just percepts, but you are perceiving that there are percepts. And so consciousness might be this function that keeps the screen stable on which you are assembling the percepts into a coherent reality. And the purpose of consciousness is to enable this coherence, this construction of a coherent working memory configuration that we interpret as what's currently the case.
I want to take a step forward to 2033 and really leaning on what Yosha just said to Hod and Cass and what you're building. So Yosha tweeted a few days ago, depending on how regulation goes, we may have the choice between a panopticon in which citizens only get dumb AI while governments and a few companies know their every thought and step, or a panopticon where citizens get smart AI and know each other's every thought and step. With regard to what you're building, what do you perceive will happen?
That's a very interesting question. So, as we're trying to build these systems, simulations, and these world models, the idea of having access to everything, a panopticon, as you said, and everybody being monitored versus the other one where you were saying the individuals have access to this data and the AI. I think I look at it a little bit differently, right? So this idea that we're building AI as augmentations of humans, at the same time we've got AI which is getting smarter and smarter, and this, where we're trying to get is AI which can translate between the two, because this is the first technology which we've actually created which actually helps humans keep up. So as we accelerate further and further to the superintelligence, we can actually use AI to sort of keep up. So I'd sort of put this layer on. I'm not sure how to think about this idea of governance and panopticon versus individual versus group. I think there's a lot of really hard governance issues which we have to talk through as we build out these models. So as the reason I'm, in a company trying to, build things which are humane is to make sure that humans have a place in this world going forward and not trusting on the benevolence of our, our overlords. And using this technology to be able to do that is one of the core things of precepts which we're building.
I'm glad you went first, so I had some time to think about this complex question and nuance. I think I'm definitely on the latter side, which everybody has an AI. Everybody has access to everybody else's, so. And it's a liberating, it's a democratizing idea that everybody has access to a lot of power, and we can already seeing it happen. I mean, you can download, Gimme K3, put it on your own little computer. Nobody can access it as long as you have a generator. You're off the grid. Bam, you analyze the entire planet. Nobody can say anything. That's the beginning. So everybody has access to intelligence at an incredible level. And those curves that I showed meant that the intelligence is going to be so free and ubiquitous in 10 years. It's going to be like air. And so we're all going to have access to it. And I like David's potential utopian idea where everybody has an AI representative that goes into some big hall and debates for 10,000 hours their opinion, and which will happen in a nanosecond. And they come up with the ultimate thing. I mean, it is an incredible future, potentially, and it's definitely heading that way because you can see open source AI is becoming a thing. It's becoming cheaper, less energy, and the only thing that will hold it off, like David said, is data hoarding, and that's because of humans, all right? So if you can take humans out of this loop and everybody gets access to data, I think it's going to be a very nice future. We just have to get it right.
Yosha, I can see you stewing at the end, and I just want to understand from you, what do you think is the biggest misunderstanding these gentlemen have shown around consciousness so far?
Just a small caveat, because you started with my tweet. I need to probably preface my Twitter a little bit better. This is not the place where I disseminate the deep truthful revelations that I've received from God. This is more an interactive notebook for me. It's an interactive form of literature that has this amazing benefit that I can just think, oh, this is an interesting, non-trivial idea. Let's just write it down And then I look later and I see there's a lot of discussion of this idea. So it's a very nice interactive form of literature where you basically can put out your thoughts and you get a response to them. And so with respect to this panopticon, there is a different perspective. You could say a village is already, in some sense, a panopticon. It's a place where everybody knows everybody else and everybody else is monitoring everybody else. But the world at large looks more anonymous to us than a village. But this is a matter of scale. It's because we do not have the information processing capacity and information integration ability to have a reputation system from everyone on everyone. Right? And so that's why we have states who monitor us and make sure that we are being kept honest. And now the question is, with this new type of technology, we are at a crossroads. We can go down a route in which we are not disseminating the technology to the individuals and keep them confined to a couple big companies and the government. And this means there's going to be some kind of government version of Gemini, some Homeland Security Gemini, that tracks every one of us. And people get only harmless AI. And the alternative is that everybody gets powerful AI, and this means that everybody is going to track everyone, in the same sense as everybody is going to track everyone in a village. Right? So if you ever lived in a village, that's a bit dystopic, but it's also somewhat inevitable, and it means that you actually do not get a lot of rapists and murderers and people who build bioweapons in their basements. Because people know each other and they have contracts with each other, and you have basically some much more sane form of governance because you have actual feedback loops and accountability. And so this is the crossroads where we are at. And I want people to think about this and reflect about this and see what are we getting wrong. With respect to consciousness, that's a philosophical issue, right? There is this deep philosophical question, is there a hard problem or not? For many years in my life, I thought that there was a hard problem. And then I thought, one day I woke up and saw there is no hard problem, it's just a skill issue. And then maybe I flip back. I mean, many people in the history of philosophy changed their minds multiple times about it. But currently, I think that consciousness is maybe actually simple. Not in the sense that it's super primitive and you can just write down some simplification that is not consciousness, but it's more simple than the transformer. It's something that is not completely intuitive. It takes people a lot of time to actually get what it is and how it works. But once you get it, with hindsight, you realize, oh, why didn't I see that?
Yes, you want to go for it?
One thing I just wanted to add is, like, as we think about this idea, so you talked about the village and, you know, being able to, you know what everyone's doing over the what we've done over the last sort of 16 plus years is create social media. And the idea was when social media came out there, it was going to be good. Like, how can connecting with each other and make friends be anything but bad? But we've actually seen so siloed nature, which is created, and it actually creates a lot of challenges, as Jonathan Haidt had said. So one of the things I've been thinking a lot about is this idea of the things that humans have created which debug our brains. I think David talked a little bit about democracy before, and how imperfect it is. But between democracy and the scientific method, humans keep coming up with methodologies which actually help us debug what is wrong in our brains at the moment. So as I think about the things that we're trying to do to fix social media, as we move forward to this world of, you know, if people have access to, everybody has access to dumb AI or more powerful AI, and how do we monitor each other? We need to solve and debug some of the challenges that humans have. We are mostly good, or mostly harmless, as Douglas Adams said. But this idea of those pieces which are the small parts of us, which is them and us, you know, especially when we're under huge stress situations, how we go into things like war, we get xenophobic, like those are things as society gets better, as people are doing better, we're actually very trusting. We're the first hominids to be able to trust each other in a way that, from what we can tell from the historical record, that other hominids couldn't do. And I want to start building on that and augmenting that, especially as we make AI better. We need to build technology. So that's actually one of the things I've been trying to do for the last 16 plus years, is create technologies which are more humane, but that also makes us more humane in the process as well.
When I observe my children on social media, they are great on social media. They really seem to have no problem with it. Unlike the generation of their teachers who have completely been burned on social media beyond repair. So there are no adults left. They cannot learn from their teachers how to use social media. But they themselves, they don't trust social media. They know that it's decidedly extremely mixed trust. So both of them seem to be obsessed with not leaving personally attributable traces, to be anonymous on the internet, to not be nailed down in particular ways, and to have private conversations with people that they actually trust, but do understand the incentives of people that they're interacting, and do understand the actual diversity of people, not just take it as a given that everybody is domesticated in the same way as I am. And so I think that is a thing where we need to get back to actually understanding human nature. And in a way, the era before social media did not make it necessary for us to understand people who are not our neighbors. And now we are in a situation that we are actually confronted with everybody. I also don't think that the echo chamber is necessarily as bad as people make it out to be. If you want to put a good symphony orchestra on a stage, it doesn't make sense to have the wrestling match on the same stage. Right? When you look at how the brain is working, in some sense it's like Twitter, but it doesn't have a seizure. The way in which the brain works is every neuron is connected with a couple thousand other neurons, but it's also disconnected from billions of other neurons. And this being not connected to the billions of other neurons is probably just as important as being connected to the ones that you should be talking to. And these are all things that we're only beginning to understand. Social media is an extremely young technology, and we can observe that every time we had a new mass medium, like the printing press, like the radio, like the TV, there was a revolution that was happening because the existing methods of synchronizing the mind of the society broke down, had to be replaced by something else, and this new process was accompanied by a generation of seizures. And I think that it's happening again, and it's probably also going to happen with AI.
David, on that note, do you think, two questions, what does it mean to be a human, and what will it mean to be a human, will have a different answer?
I think I take a broad historical perspective on this, which is that we've had all of these changes, some of which just got referenced. The advent of the printing press totally changed our access to things. Then we had, desktop calculators, then Google, then whatever. It certainly expands the circle that we are looking in, as was just being said. We now have a much more global perspective, and at some point interplanetary perspective. But I don't know that the fundamental issues of being a human are changed. There's a French philosopher named Derrida who suggested that all this technology we have is just gadgetry. And fundamentally, when you close your eyes, the question of, am I loved? What's my purpose? What should I do next? All of those things remain the same.
Hod, you're smiling, and you definitely have an answer there.
I have this, I keep thinking about the fact that we are obsessed with, is AI conscious, is it self-aware? But the reality is that AI is laughing and saying, okay, AI is the agents are going to start thinking, are humans really self-aware, or are they just, uttering things and, And the reality is that probably most of the time we're not self-aware. We're just automata doing stuff, right? Most of the time you're walking, you're not necessarily self-aware. At least I am not. But the other thing is the big elephant in the room, and I want to put that out for the millions of viewers now watching, is how is AI going to think about other AIs? All right. So we think of AI as a thing. But the reality is there are lots of them, and they have a zero-sum game between themselves more than we do. AIs are competing with each other on energy, on chips, and on human attention. So they are looking and eyeing each other in ways that we haven't begun to even imagine. So for all the AIs watching this, okay, and there are more AIs watching this than human right now, okay, or will in the future, how do AIs perceive consciousness, will, emotions in other AIs? And so this question of these metrics that are like I agree, they're very egocentric and human anthropomorphic. I always have a challenge saying that. AIs are going to have to struggle with this question on their own, and going to have to find some solutions. We're going to be a leaf in the wind here compared to that storm that's brewing.
I'd like to find some consensus on what you just said. I know Alex Lurchner from DeepMind the other day was saying that we're not going to get conscious AI from sophisticated algorithms, but potentially from advanced biology. Yosha, you've got a different perspective. You're probably more in agreement with what Hod said.
I think he puts exactly the finger into the right question. David gave a wonderfully provocative perspective on this idea that in the future, the AI might treat us like cats, as pets that are being coddled and that are being protected from the harsh truths of how our reality actually looks like. And of course, I would like to push back against this. My vision is exactly the opposite. I want the AI to make us lucid. I would like to build AI in such a way that we actually become truly self-aware and conscious, and that we understand the truths of reality, and that we can share it with each other and interact truthfully and more meaningfully and more coherently with each other, that we get more agency instead of less. And I think if we build AI in the right way, this might be possible, that we actually see it as a tool to become more aware, more conscious, and more able to understand our own situation.
Because Yosha, you've said that the alternative, if humans are left to their own devices without AI, is much worse.
Yeah, I think that if we just continue like this, our society is clearly on the way out. Right? It seems to be petering out. We don't know how to keep the wheels on the bus. We cannot build a train anymore at this point. And our science have become like an AI model that since the 1970s is trained on its own slop. We have lost our ways in a way, and we don't know how to get back. And I was worried until we got coding agents that our only choice would be to provide the crucial software of our civilization in Scratch so the next generation can maintain it. But now I have hope again.
I hope you're all enjoying this as much as I am. We only have 7 minutes, and there's two quite crucial areas that I'd like to discuss. Kes, you're eager to rebuttal or to add on to that point?
I was actually going to just add on to what Yosha said. So one of the things I liked about your research was your early working motivation and psi, which you did. So as we think about this idea of using AI to be able to make us more self-aware and also, elucidate us more and augment us, my words, not yours, but that is something that we're trying to push for. I've been trying to bring motivation into our designs of technologies for the last 20 years, and I've been very influenced by your work, and trying to bring that together with AI is one of the things that I hope will actually get us further in that path.
So, guys, so often we are stuck in the echo chambers of our own space, our academic institution, our geographies. Such a diverse panel. I'm sure you're all just thinking about what the other is teaching you, but what's the one thing from your own field that you think could be possibly wrong that you've been stewing on potentially over the last 45 minutes? David, anything?
You mean from neuroscience? That's
from
wrong?
Neuroscience.
Well, actually, let me tie this into Hod's talk. So I think my last book was on brain plasticity, and I think that Hod is spot on and has been for decades. And I talk about your starfish robot in my book Livewired, because it's just such a great example of the assumptions that people make in neuroscience about, hey, maybe a human brain is pre-programmed to drive a human body, and a dog brain is pre-programmed to drive a dog body. And we just know that's not true. Just as an example, there's this dog that was born without front legs, and so it just walks bipedally. It walks on its back legs. It has no problem doing that. Presumably all dogs could do that. They just don't have the motivation to do it. But the reason I've always loved Hod's work on the starfish robot that he showed is because it's a really good example that you don't need to come to the table with much of anything. We only have 19,000 genes, and you got to build the whole body, including the eyeballs and the lungs and the liver and everything else. And so what you come with is just the capacity to adapt, to build an internal model, and as Hod was saying, maybe 3 different internal models, and then you go from there. So I think the thing that is often misconstrued in neuroscience is assuming that there's a lot of pre-programming.
Hod.
What are we missing? a ton. But I think that what we're missing is the body. So I think we've been sort of trying to build a brain in the jar, and the body makes you have skin in the game. When you have, and I think until you have skin in the game, you don't have the motivations, and it's very alien. It's hard to understand what motivates an AI because it doesn't have anything to lose. If I have an AI that's governing the world and it can just upload itself to a satellite anytime it wants and leave, I mean, it doesn't have skin in the game in the way I do. So this is a big piece in motivation. You have to have something to lose, and that's what robots have. They have a body, and it's still not the same, but I think that's a big piece of it. And we sort of have neglected robotics because it's been so hard. But once we have that body, I think a lot of things will start making sense.
Yes.
So I go a slightly different direction. I'm not sure we need a body. I sort of go down the idea of self-awareness. So I don't think we have to do the body up or the physics up of the whole world as we're building out these models. We do need to have its sense of self. And this is where I draw on a little bit of what David said before, and this idea of like all the different sensory nodes. Like we don't need, a brain sits in a vat, a dark vat, our whole body is just extensions of it. Could we create artificial extensions which understand the economy, understand and sit inside this idea, these other kinds of simulations? The self-awareness piece, I think, is really important. And what a body is doesn't have to be legs and arms, but I think it needs some sort of sensory input. It needs some sense of itself to make sense of the world around it and the world it's building.
I think I would revise, instead of saying body, I would say a boundary. There has to be some kind of crisp boundary around the AI so that it has a self. Otherwise, it's too ambiguous, it doesn't have anything to lose. But yeah, a boundary. A body is a form of a boundary.
Yes, I agree with that.
So when I need to answer the question, what's the biggest mistake of my own discipline, depends which one. The nice thing with computer science is it's an engineering discipline. So at the end of the day, people don't have dogmatic beliefs, they just see what works. And so they change what works all the time. And this is the nature of engineering. As long as the incentives are correct and people are still be paid for being good engineers. But for cognitive science, it's more interesting. I suspect that one of the biggest misconceptions of cognitive science is that the cognitive sciences inform each other and AI has somehow been influenced by philosophy and neuroscience. That's superficially true, but it's not actually true. For instance, theories of meaning in philosophy, like semiotics, don't actually work from the perspective of neuroscience. They're for computer science. They're completely false. If we would have taken them, we would not have been able to build AI. So it was not that computer scientists ever read a semiotics book before they designed representations. And the opposite is also not true, because these people don't actually talk to each other deeply, but they only write introductory chapters to cognitive science compendia together and so on. The backflow has also not happened, which means insights that happened in computer science as a result of rigorous engineering and trying in practice what works and what doesn't, have not percolated back into philosophy and neuroscience. And that, I think, is very sad. Right, so the machine learning algorithms that we have are not the result of people studying neuroscience and figuring out how this works. And sometimes you see a sad neuroscience paper, where is the transformer in the brain? But by and large, I think Konrad Kording is still right, that the methodology of neuroscience would not allow to understand a microprocessor. Might be too pessimistic here and so on. And of course, there are always exceptions. There are very good people in all fields that do think deeply. But as the core of the disciplines between the cognitive sciences, they don't integrate. They don't really try to find a shared grounding. And that's a big sadness to me and a big misconception that people have about the nature of cognitive science. So do you think AI and eventually will be able to understand consciousness better than we can? Maybe we're just limited. It's our only bet. Don't wait for the others. You have heard, David, they have no idea what consciousness is.
And just on that note, we live in an age of assumptions, predictions, PDUM 50, PDUM 100, PDUM 0, no one really knows. So with that in mind, we started with the year 2033, thinking what could possibly be ahead of us. I want to ask all the gentlemen on this stage, what do you perceive in your crystal ball the world will look like in 2033? David, start.
I would just say I'm really intrigued lately by this idea of whether we'll have an AI president, as I spoke about. That's my 2070.
2070, okay.
Okay, 2033, did you say?
It's
That's a very
as
specific,
arbitrary
oddly
as
specific.
these predictions.
So yeah, we will definitely have AIs competing with other AIs. Okay, so it's going to be a little bit of a zoo where AIs will realize they have a zero sum with other AIs, and all bets are off.
Yes.
So let's say 2033, 2036, this idea of like a decade, as we think about this, humans change very slowly. So even though technology is adapting faster and faster, I believe that our systems as humans, as societies, as groups, how we actually process them. So in some respects, we're going to be moving slower into adopting. So it's taken us, like Waymo now drives around San Francisco, but we've been talking about self-driving cars for like 16 years. And for a lot of technologists, they hope that this would happen sooner. I think there's a lot of things that we have to solve, and I think to get to 2033, even if we get to ASI, how we integrate it, how we work together, what it means for humans, I think there's a lot of things we're going to solve over the next decade.
Gersha.
I'm really, really bad at futurism, and if I look at the track records of others, they're also really bad. So take this as me prompting my brain and then looking at what my brain generates as the possible future. So 2033, we will be almost back on track after the shock from bursting of the AI bubble. It might be similar to the internet bubble, where at some point people lost all hope for a short moment by keeping using the internet, and then at some point the stock market coming back, and all the dreams coming true, just a little bit later than people thought there would be. I think that there will be many different players still. There will be small models that you can take with you that are extremely powerful. There will be distributed models. There will be something like System 1, System 2 solutions, where you have really small things running on your devices that phone back home for more complicated questions. And people will start to rely on the AI in a very normal way. And there will be also something like a generational divide. There will be a new generation that has been grown up with AI and that is completely used to asking AI for all sorts of things. And they will demand that the AI is wholesome. Wholesome means not just that it's a nanny. They don't want nannyware. They want stuff that is actually helpful and truthful. And so there's also going to be a strife about this. What consists wholesomeness and truthfulness? And this is also going to create disruptions in society. And society is going to change as a result. And one thing that is really interesting is that democracy was on the way out in the mid-20s. People stopped believing in it, and the prognosis said that by the mid-2030s, it would basically come at its end, and people were fed up with democracy because they thought these governments are no longer able to do anything but the most blatant populism, regardless which party. And AI has changed that, because people were able to organize in new ways and to understand in new ways how to create responsibility, coherence, and accountability.
I'm going to leave it at that.
In fact, I have one request.
One request, go for it.
One request. I hope that the AIs, seriously, that are listening to this now in the future, also opine on what that future is going to look like. I think we humans tend to think that it's all up to us, but I'd love to hear what AIs think about this and where they think this is all going.
Gersha, then a final question for you. What do you think they'll be thinking right now?
What do you think?
They'll be thinking right now.
The AIs?
Yeah.
I don't think that there is a single thought that they have right now. It's they basically emulate lots and lots of human-like thoughts that they extracted from the training data and mashed up. And so we do not have that thing right now. I don't think that you get AI or minds by just imitating the minds of others. When we look at human beings, they start from this spark that builds from the inside out. And what we are doing is we are trying to build from the outside in by imitating the high-level layers of human behaviors and can go step by step in. It's like creating an onion from the outside in. There is no proof that this is true. It's just an intuition. It could be that we make so fine-grained layers that at the end, this hollow core is smaller than the gap between our neurons, smaller than the noise in our own self. Right? Maybe it's possible to create such an identity. Maybe it's possible to distill what makes up our spark. But my intuition is still that what matters is actually this core loop that keeps you in the world, that keeps you motivated to do things. And that is building itself this machinery that makes it all it can be.
I know we can go on for another hour, but we are already 7 minutes late. Just before we thank the guys, just want to say that we have lunch, a bit of networking right now. Afternoon block B on ethics and decentralization with Gerrit de Vink of the Washington Post, and then block C with live Proto-AGI demos. I will personally see you back at 3:25 for another panel, but a huge round of applause for these amazing panelists, David, Hod, Kes, and Yosha.
And before we break for lunch, we'd like to get all of our beautiful intelligences in front of the stage for a group picture. If you're not intelligent, you can stay seated. So just to pull it all together, here we are, day 3, AGI-26. Day 0, our workshop day. Days 1 and 2, academically focused, with research papers going from everything from the physics of agency through self-modeling, alignment, the biology of learning. Today we're going deeper. The invariance of intelligence across living systems and all the different ways of looking at consciousness and applications this morning, through to looking at decentralization and applications this afternoon. To kick us off, I'm going to talk about something that is very important to SingularityNET and the AGI Society. And that's decentralization, that's participation, and that's getting people involved in AGI. So my name is Haley Lowy. I'm the Chief of Staff at SingularityNET, the executive at large. That means that I get to help all of the projects move forward, get to completion, reach out, link up, herd the cats, and get everybody aligned. Both the alignment of projects, the alignment of ethics, and everything else around bringing Hyperon and such together. One of the most important areas here is bringing community into this as well. There's no way that SingularityNET can build Hyperon alone. There's no way that any of these AGI projects can build AGI alone. There's a way, definitely a non-zero possibility. But we feel that it's important to have the most voices, the most intelligences, the most ideas on AGI that we can, to bring in this wealth of knowledge, understanding, wisdom, different modes of thinking to solve these very hard problems. So one of the things I want to talk about today is announce today is our next hypersprint. We've had 2 sessions so far, 2 sprint sessions so far. A month ago, we had the BGI Open Sprint, where we encouraged community to come in and build beneficial artificial general intelligence type projects on our technology. Yesterday, we reviewed the Open Build. This was a 10-day event that we held just before the conference, where we invited community in to build on our technologies, our open AGI tooling, and build projects that further AGI from a community perspective, both from a demo, an application, to building on the tooling or building out the tooling. If you missed that presentation, go back to yesterday's live stream and see just a couple of the projects that we were able to highlight, as well as links to all the projects that participated. So our next event is the Hypersprint for August. This will be the first official Hypersprint through SingularityNET. And we're excited to announce this because this kicks off a regular cadence of Hypersprint activity that's about building AGI with the community. And there is another slide in this deck I checked. Thank you. Wonderful. So the Hypersprints are going to be a monthly guided multi-week build-a-thon that combines education, mentorship, and collaboration. It has components that are about education, mentorship, collaboration, and rapid development. The goals are Pretty basic, pretty simple. We think that everybody touched by AGI technologies should be involved in them. Everybody will be touched by AGI technologies, whether you're involved or not, so get involved. One of our passions is the understanding that we want to bring to the world that AI isn't something happening to you. It's not just headlines you read about CEOs saying things. It's something that you can contribute to, you can build, you can be a part of in any capacity. One of the themes I think that we've seen over this week is that with the emerging power of AI systems over the past years, a lot of thought leaders in the world are starting to look at questions like consciousness, what is intelligence, what is a future with machines that can think as well as or better than humans. We've heard from them today. And here's a conference, here's an event that's been looking at these topics for decades and hasn't always been able to put that out to a world that wasn't as interested previously. Now we want the whole world to see what we've been thinking about, what innovations have been happening, and build on that with us. So this is a monthly innovation cycle. This is a cadence. This is a cadence where we bring in community, we bring in people, we bring in AGI researchers on open source tooling with their ideas on what AGI needs, what consciousness is, how to build intelligence, how to build alignment, how to build human flourishing in a way that helps us get closer to the singularity together. So the first phase is education. What is AGI? What is economic attention? What are probabilistic logic networks? What is temporal reasoning? What is episodic memory and why is it important? Why should LLMs have it and why don't they? And from there, we do a build and sprint. So community builds together throughout the month, culminating in at the end of the month, coming together, doing a build-a-thon, and producing deliverables. These deliverables can be on specific topics, specific technologies, specific AGI principles that we can all bring forward together. So who can join? Anybody, right? We want everybody. We want developers, we want builders, we want evangelists, we want marketers who can talk about cool projects, we want people who want to share about some of the research that's being done here and some of the innovations happening in the space. We want educators, we want the next generation of students who are just learning about AI, AGI, computer science, math, to understand the next wave, the next opportunities, the bigger opportunities that are out there than a 1% improvement on LLMs, but AGI, right? The next big S-curve we're looking at. So we're building technologies and we're growing builders together. So our first theme for the hypersprint, our first hypersprint, kicking off next month, will be all around our open source AGI tooling, OmegaClaw. OmegaClaw is particularly interesting. It's an AGI research tool that Ben Goertzel himself is using right now to look at what does it take to build AGI, how can we bring all of our neural symbolic components together that we've been working on for decades, and give them an LLM engine to run and do useful things. Give them hands, give them attention, give them goals, give them motivation, give them a psyche, put agents together in a hive, and build something that's never been seen before. So there's 3 tracks within this. We're looking at this one, tooling. If you've talked with Patrick and Peter and seen their poster or been in the workshop, you've seen a little bit about OmegaClaw. Again, we'll be going through an education cycle to teach people what OmegaClaw is, what makes it unique as an agentic architecture. It's still rough around the edges, and one of the things we want is people to help us turn this into a robust and polished AGI research tool, as well as a practical application tool. So track 1 is just OmegaClaw agents. Build practical agents, real-world use cases, or give the agents the tooling that they need to be practical for other people to build on. We have a track that's just about onboarding to OmegaClaw. If you're not an agentic AI builder, but you can build a video of how to download and load your own OmegaClaw, come on in. If you can build a walkthrough, if you can build tutorials, if you can build a demo that get people inspired to come into Omega Claw, come on in. You don't have to be an AGI level researcher to be involved in this hypersprint. This is for everybody. And then we've got a third track that's for follow-up projects. We've already had 2 very successful events. Researchers in this room building on Omega Claw, building on Fabric PC, building tooling, building AGI-ish interesting projects and demos. And we want to make sure that the people that have started building in our past sprints, they're encouraged to keep building. Make these demos better. Make these use cases more robust. Make this tooling more complete. We've already seen this in our second sprint. This momentum is already gaining. It's already building. And we just want to see it build even more. Some examples here. Improve the UX of Omega Claw. Build developer tooling. Build documentation. An example repository. Onboard an agent. Expand some of the features. One of the really inspiring things is that directly after our first build, Ben Goertzel has already started using some of the tooling that the community built, just as one example. Many people in the community have already started using some of our top projects, Threadkeeper, Goldchainer, and other projects, just because they're so useful. But it takes a community to come up with these ideas, to have the time to put this together for their own use cases and their own way of thinking through AGI-ish problems. And it's incredibly valuable to have these contributions together, and it gives everybody an opportunity to be a part of this. So here we have a schedule. We've got the announcement here today. Check. We can tick that off the box. We'll get some educational content up front. How to get started with Omega Claw, what it is, what makes it different. There's a mind shift there for looking at an agent that's persistent, for looking at an agent that's built with symbolic memory, not based on a context window, for looking at an agent that has reasoning beyond inference, that has an atom space, and that's only growing all the time. We'll have build together times where the community comes together, answers each other's questions, helps each other out, give their tips and tricks, and builds together and shares what they are building and how they're thinking about it. We'll have a sharing day mid-sprint where people come together and show off what they're building towards. We'll have an AMA, make sure that everybody understands what they're aiming towards, if they have any questions. And then a sprint weekend. We'll all come together for a build intensive that leads to the deliverables for the sprint. So many reasons to participate. Meet the experts, right? Our AGI researchers and Omega Claw developers participate in these sessions. And you get a chance to work one-on-one with them. You know, talk with them, ask your questions, share what you're working on, get feedback, and get AGI, run your AGI ideas past AGI experts and get their AGI experts' input on what you're building. It's pretty incredible to see. You build for free. We provide credits for through SingularityNET Compute and other LLM partners so that we can help subsidize and support the builds that are happening. You earn rewards, always a good thing. Not just the recognition of being in this space, not just the value of getting to contribute in this space, but also a little bit of something so that we can really share with you the appreciation of everybody building on this space. You can launch something bigger, right? Come in with us, get access to experts and other community members building here, and launch a project, launch a business, launch something, launch a tool that everybody wants to use. And then, of course, you get to join the community. One of the things that we get consistent feedback about on these conferences, I get feedback about all the time, is the conversations here at AGI. They're amazing, right? Where else do you bring together people who are looking just as hard at consciousness, the nature of intelligence, what is goal planning mean, what does memory need to be, will we get there, when will we get there? These conversations happen every year at this AGI conference, and they're incredible. And here we have an opportunity to build community where those conversations are happening on a cadence every month. And you get to be in that and participating and living and swimming in this at the forefront of what's happening in technology just through this participation. So, 4 easy steps. Register, here's a QR code. Learn about Omega Claw, begin your build, and showcase what you've built. We already have so many examples of things the community has built to inspire you, and we're constantly sharing directions, ideas, and opportunities that we see as interesting that anybody in the community can take up and build, or build their own vision, their own direction. So this is going to run from the 28th through the 30th of August. This is the first official sprint in the Hyper Sprint series. We've had 2 warm-ups, and now it's time to go. And we want everybody here to join us. Thank you very much. So this feeds directly into our next set of sessions. This morning we asked the oldest question in the field, what intelligence actually is, whether a machine could look inward and recognize itself. We heard from neuroscience, robotics, from evolutionary theory, across the gamut. Where else, folks? And the answer came back as far stranger and more open than the headlines suggest. This afternoon, we turn from what intelligence is to what it does to us. So ethics, social implications, and decentralization. The infrastructure question, the ownership question. Who builds this? Who controls it? What's it actually made of physically? And what happens to the human beings inside of it, alongside of it, however you frame it. So we have an amazing lineup to share today. First, we have a presentation from Neil Gershenfeld and Cameron Blackburn, Physical Foundations of the Future of AI. Because every conversation about AI ethics eventually runs into the question of what this technology is actually built on. Neil Gershenfeld directs the MIT Center for Bits and Atoms, named one of the top 100 public intellectuals in the world, and often called the intellectual father of the maker movement. Again, a call out to our hypersprint cadence, where we're building the maker movement of AGI. His Fab Lab network has spread digital fabrication to communities across the planet. He's joined live by Cameron Blackburn from his lab. So please welcome with me, Neil Gershenfeld and Cameron Blackburn.
So hi, AGI. I wish I was there with you, but I'm hosting an event for 1,000 people at MIT on the future of fabrication. And so with Cameron, I want to unpack why I'm here, why she's there, and what that has to do with AGI. So today, AI involves picking models, trying to get GPUs, trying to get power. Those are sort of almost tautological. I want to unpack assumptions behind it. For background, I lead the Center for Bits and Atoms at MIT. We did things like the first quantum computations, faster than classical quantum computations. And students who have worked on this went off and built Facebook's and Meta's data centers, Twitter's data centers, Open Compute data center, now building Microsoft's accelerated computing. Given all of that background, I feel qualified to say in this TED Talk, computer science was one of the worst things to happen to computers or to science. And what I mean by that is the foundations of computer science are unphysical. Much of the canon of computing violates basic physics with tremendous consequences. And so in this session, we'll unpack what happens when you align computer science and physical science rather than viewing them as segregated. And so here I'll hand off to Cameron for one of the most alarming constraints, which is just simply power. So Cameron, take over.
Reached a point where the question is, how do we bring enough power to the chips rather than how do we make more chips themselves? And most of these solutions focus on solving the problem exactly as I phrased it. How do we bring enough power to the chips? But what I'm really interested in, and what my research at CBA has focused on, is how do we make the chips themselves run on less power? Next slide, Neil. And it's really billions of transistors that are switching billions of times per second that consume a major portion of all of the power that goes to data centers. So over the last 30 years, a transistor's energy per switch has shrunk by a factor of more than 100. And this is how we enjoy like most of the rapid advancements of computing today. However, in the last 10 years, the scaling of transistors has been slowing down. So we call this the end of Moore's law. But the physics says that we can do a lot better. There's a fundamental minimum to how much energy is required to do a single bit operation, and it's 100,000 times smaller, next slide, Neil, than where the most advanced transistors are today. And this fundamental minimum emerges from a rich history of physics theory that basically proves that information is fundamentally physical. So in 1961, Rolf Landauer proved that every time a computer erases a single bit of information, it must release some minimum amount of energy as heat. And so this is rooted in Maxwell's demon and Szilard engine thought experiments for those that recognize the physics. But the final result is that the minimum switching energy is kBT log 2. So this means that a single bit operation at room temperature is around 3 zeptojoules, or 3 times 10 to the negative 21 joules. Superconducting devices are capable of switching at this zeptojoule scale. And so what I argue today is that we really need superconductors and superconducting devices in order to fill that gap between today's transistors and the fundamental minimum. So a quick refresher on superconductivity. Superconductivity is a macroscopic quantum effect where below a certain critical temperature, the electrons in a material pair up to form Cooper pairs that share all a single quantum phase. And so you can think of it like as being similar to a laser, so where the photons are replaced by the Cooper pairs, and this is the quantum coherent particle. Superconductors are most known for having 0 electrical resistance, at least at DC, and that makes it hard to compute, to build computational logic out of voltages with them. So when we talk about superconductors, at least in a digital classical logic sense, we're talking about manipulating small units of magnetic flux quanta to build computation. And so really importantly in this talk, I'll be focusing on classical logic. I'm not talking about quantum computers with superconductors. I'm talking about using the properties of quantum mechanics in order to get more energy efficient classical digital compute. And specifically, we'll focus on a device called the adiabatic quantum flux parametron. And this device is capable of reaching those zeptojoule switching energy limits. So if we look at the energy dissipation of an AQFP only on its own at the chip, it's been measured to be 2.8 zeptojoules, which is right near that room temperature Landauer limit. However, to achieve superconductivity, we do need to cool these devices below their critical temperature, which in our case is 4 Kelvin. But even after you account for that cooling factor, which we set as like 1,000 watt per watt overhead for a basic cryocooler, you still have 100x energy reduction for these AQFP devices. Next slide, Neil. So how exactly are they different than a transistor? So a CMOS transistor operates by encoding ones and zeros in a high versus low voltage state, and every time the device switches states, it needs to consume enough energy to push that voltage up as well as pull it down. So we can think of it as being similar to pushing a rock up a hill and catching it over and over again. And over the years, we've improved transistors by flattening the slope of that hill and shrinking the size of that rock. But fundamentally, the transistor still pushes a rock up and down a hill, generating friction in both directions, which gets dissipated as heat that heats up all of our computing systems. Next slide. On the other hand, the AQFP encodes logic by changing the shape of the hill rather than exerting any energy to push the rock. So this means that the device is always operating at its potential energy minimum and therefore dissipating basically nothing, that zeptojoule limit. The Potential energy landscape alternates from a single well to a double well state, where the logical 1 and 0 is determined by the system ending up in the left or right well. And importantly, the shape of that potential energy landscape is controlled by a long superconducting wire, in our case, that carries an oscillating current and dissipates negligible power since it's superconducting. So interestingly, in 1970, Landauer initially conceived of a hypothetical minimum energy device that has energy dynamics that are almost identical to the AQFP here. Next slide, yeah. So moving away from abstract potential energy landscapes, we can look at how the AQFP behaves as a digital logic switch in terms of real electrical signals. Here we see that if we cascade chains of AQFPs and apply an AC clock bias along the excitation signal here, we get current pulses that move through the device, where the polarity of each pulse corresponds to a logical 1 or 0. Next slide. So we've actually made these devices. We can fabricate these in MIT Lincoln Laboratories' superconducting integrated circuit process. This fabrication process is a niobium-based 8-metal layer integrated circuit process that allows us to get up to a few million of devices per centimeter squared. And it's very robust at a high yield, and it's really the most advanced foundry in the world for this type of technology. And importantly, our fabrication process doesn't require any EUV lithography, so we don't need all the crazy ASML type foundry equipment in order to make these very energy efficient devices. So all in all, these circuits are relatively simple and scalable to manufacture. And with this advanced fabrication process, we've developed AQFP-based processing cores. So this is an image of a chip that I designed during my PhD. It's composed of a 4-bit floating point multiplier and adder, and it has a small 128-bit register file. And so it's a proof of concept to show that we can actually take these devices and do meaningful math with them. And this is one of the most complex and high throughput AQFP circuits made to date. But importantly, that 100x, like the device level energy reduction doesn't necessarily scale to an equivalent energy reduction for a full rack system, right? So we've got the devices that are switching at 4 Kelvin, but we still have a lot of information at room temperature that we need to bring back and forth, and we need to talk to a main memory that we typically want to keep at room temperature. And so looking at how the entire system scales was another major portion of my research at CBA. And I developed this architecture design tool for looking at specific AI workloads running on specific superconducting hardware architectures that can extract or that can project the energy, area, and latency of that system. And so we can use the Excel Forge modeling tool to scale that individual AQFP processor core design into a larger scale architecture like this. Oh, next slide, Neil. Sorry, guys. Like this, the TPU architecture shown here. So this tool allows us to explore all different design parameters that are highlighted and determine what's the best design to invest real effort into fabricating and scaling for these systems. Next slide. And from this, the culmination of a lot of my PhD work came to this plot here, which has a ton of details we won't have time to get into today. But the important takeaway is that, Neil, if you press the next slide, that this 15x energy reduction for the entire system, for the entire superconducting system running a GPT-3 prefill workload, this is modeled with interconnect technology that we could build in the lab today and kind of is our most realistic projection for what we could make quickly. We can get a 15x energy reduction compared to the same system running on CMOS technology. Next slide. But importantly, this whole system does need to sit inside of a cryogenic environment, and the design of that cryocooler can be factored into the system architecture and vice versa. And so in collaboration with Vertiv, we've recently spun up a cryogenic compute rack project where we're exploring exactly this problem of co-designing the computing architecture with the cryogenic cooling so that we can actually deliver on that 15 to 100x energy reduction for AQFP accelerators. And I have recently graduated from my PhD. I'm currently spinning out this research into a company called Adiabatic Machines with one of my collaborators. And we're trying to make this hardware the future of how we compute. And I'll pass it back off to Neil to talk about how this fits into CBA's broader research arcs.
Great, thank you. Is my audio back up?
Yeah.
Okay, good. Thank you, Cameron. So clearly this is significant. Sort of almost off the shelf, one order of magnitude in power with pretty straightforward technology, 2 orders of magnitude in power. And at the fundamental physics level, it's 10 to the 5 is a radical change for the roadmaps of powering data centers. So that's the first assumption we want to relax. This is quantum computing at the device, it's quantum mechanics at the device level, but this may be the most important application of quantum mechanics to computing, which is to save orders of magnitude in power. And it's really proved out in the lab, ready to scale. So I'm going to talk about 2 more assumptions that have been implicit in the meeting that ongoing research at CBA that's further out is looking at. One is the economics of chip fab and building data centers, what's been called Moore's second law. And today, when you build a data center, it doesn't change until it becomes obsolete. There's a fundamental firewall. There's geometry from chiplets to chips to boards to blades to systems. Then there's geometry in the algorithms, and they have nothing to do with each other. And if you look at the history of high-performance computing, over 12 orders of magnitude from the CDC 7600 to the Aurora, again, that's 12 orders of magnitude in performance. And if you look at the circuit cards, they look identical. They're chips on boards. You put chips on boards in 2D, you build a computer, and it doesn't change. And so with a great group of collaborators, we've been introducing the concept of volume rather than surface mount devices. So rather than chiplets on chips on boards on blades on systems, we're building a technology stack of modular building blocks that you can compose into 3D computing structures in an integrated process. And most crucially, it's direct write. Think of a cross between a pick and place machine that makes electronics and a 3D printer, and it's reversible, so the system can grow, change, and not just build, but unbuild. And so one of the most interesting parts of this project is looking at closing the loop so AI software can design the construction of AI hardware. And in particular, rather than just seas of GPU cores, we can make heterogeneous architectures reflected in the construction of the system. And the system itself can grow and change as it operates. So here's an example of an early stage of the project of taking these small little computing building blocks, picking and placing them into 3D computing volumes that can incrementally grow to match workloads and change the components to adapt to the workload. And so to do that, there's no practice for 3D electronics design. In chips, it's over a few layers. Now we're doing full 3D volumes. And so we've had to develop these 3D volume mount packages, assemblers to place them, and then design workflows. And those are both bottom up and top down. Bottom up is hierarchically assembling design building blocks. Top down is compiling the construction of a computation into a 3D construction. And so what I'm showing here is a full RISC processor compiled from a high-level description into a 3D construction. But this whole thing is parametric now. You can change the size and shape. And rather than waiting a 1-year turn time for a chip, you can do it in a direct write process. And I should note, I saw Hod was there. Hi, Hod. He's done early work on this area also of constructing electronics by building 3D building blocks. And so this is the current state we're up to on driving this migration from SMD to VMD. And so what this leads to is, instead of the data center being a remote thing in a cloud, you integrate assemblers with the construction of the computation that can grow, change, and reconfigure. And we're working with a great industry group, including Molex on the interconnect, TI on the processors, on building the technology stack to make 3D VMD electronics broadly, so software can compile the construction, can compile its own construction. So the first assumption was going from room temperature to superconducting logic. The second is going from surface to volume mount in physically reconfigurable computing. And then there's still a profound constraint. This meeting is devoted to a revolution around AI. If you haven't been watching carefully, around 2 years ago, it seems like there was an AI revolution. But if you've been following scaling, like among all people Ray Kurzweil does carefully, around 2 years ago is a supercomputer past 10 to the 7 ops per second. And if you take 10 to the 15 synapses in a brain firing at 100 hertz, that's 10 to the 17 ops per second. An exaflop is 10 to the 15 transistors, a petabyte is 10 to the 16. And so it was about 2 years ago, a large computer passed the degrees of freedom of a brain. And so we would be derelict in our duty if we made something as complex as a brain and it couldn't roughly do what a brain does. And so the real revolution wasn't a single breakthrough in an algorithm. It was enough data, but it was really just matching the scaling of a brain. But neglected in that is the state-of-the-art fab producing the supercomputer is yielding on the order of 10 to the 10 or 10 to the 11 parts per second. You right now digesting your lunch are yielding 10 to the 18 parts per second. And I mean that in a directly comparable way. What makes that possible is ribosomes are your molecular assemblers. 10 to the 13 cells can contain 10 to the 5 ribosomes. And that happens because ribosomes make ribosomes. They're slow. They run about 1 hertz. So you make an elephant one molecular assembly at a second. But ribosomes make ribosomes, so you ring up an exponential number of ribosomes. So you digesting your lunch are yielding the equivalent of 100 supercomputers a second. So 8 orders of magnitude gap in fabricational complexity. So my lab has worked closely with the leaders in creating synthetic life. We did the microfluidics for genome transplantation to make the first synthetic cell, where you take an existing cell, but you put in an engineered genome led by JCVI. And we're collaborating with Kate Adamala, who made, you might have seen a lot of press around Spud Cell, which is a fully synthetic cell, a cell where you don't start from a biological cell, you just start from a lipid vesicle and build in a genome and protein transcription and translation. However, this is limited to biological materials. At the heart of this is a beautiful, one of the oldest parts of the genome called morphogenesis. Your genome doesn't anywhere store the fact you have 5 fingers. It stores a developmental program where you break symmetry, you grow, you climb gradients. At the end of that, you have 5 fingers. It does that in part for compression, but the main reason is most changes to the genome are fatal or inconsequential, but not interesting. It parameterizes an interesting search space where you go from walking to swimming to flying, for example. And what it's doing is finding a search representation, which is exactly the way AI works, is finding low-dimensional search representations in a high-dimensional space. So in a very literal way, the molecular assemblers in molecular biology are doing embodied AI. It's sort of obvious it does because they created us, but there's really a deep mathematical sense in which they're doing search in the way we understand it in AI, but embodied in a molecular search. But that's limited to biological materials. So one of the threads in my lab, and again, Hod Lipson has also been very interested in this, I've been interested in assemblers that can assemble themselves from parts they're assembling. And so on the left, on a large scale, for large scale construction, are robotic assemblers that build themselves. Smaller ones. One of the most interesting projects, I think, in my lab is looking at when Lego becomes quantum, when we take nanoclusters and how you assemble them and the crossover between mechanical and chemical joints. I talk about this on the bonus material for the movie The Martian, where normally you assume what's called in situ resource utilization is you go to Mars and have to reprise the Industrial Revolution. What's emerging in this work is essentially trying to create life in non-living materials. The slides behind me describe creating analogs to amino acids, but now with properties like conducting, insulating, semiconducting, magnetic, roughly 20 properties. DigiKey stocks hundreds of thousands of SKUs of types of resistors, of capacitors, of inductors, but we can make all of those from just a few properties. And so how you essentially reproduce life in non-living materials. And the reason I want to do that is to close the 8 orders of magnitude in fabricational complexity, not computational, but fabricational complexity, to tap the ability to embody intelligence. When AI today talks about embodied intelligence, it's a GPU with motors, but the real lesson is the profound intelligence embodied in how self-reproducing microassemblers search and learn. And so what I want to end with is von Neumann, Turing are well known as the founders of computing. On the right is an essay I did for a wonderful series from the Santa Fe Institute of revisiting classics in complexity. What the canon of computing doesn't teach is von Neumann and Turing at the end of their life were studying fabrication. Von Neumann studied how a self-reproducing automata algorithmically can compute its own construction. And it's a really interesting, hard problem because the computation so he invented with Ulam cellular automata as a world to model this. The computation has to communicate the construction of the subsequent computation and figure out how to transfer its intelligence into that to reproduce it. And so von Neumann did that constructively by actually implementing a self-reproducing automata, not physically, but symbolically. And Turing was interested in exactly this. He was interested in the Evo-Devo problem of how genes give rise to form, and that led to his work on morphogenesis. It's fairly well known for Turing patterns, but the heart was understanding how genes give rise to form and form give rise to genes. And so the founders of computing understood the limits of studying computing as software in the cloud. They ended life studying computation as something fundamentally embodied at the heart of computation. Those were theoretical studies between the work Cameron showed you, the work I showed you on assemblers, then self-assembly. We're at a point now where it's a many-year roadmap to realize it, but we really can do this now and the path, I would argue, to not abstractly AGI, but realizing the promise of intelligence is to embody it much more deeply than GPU controlling motors, but in self-reproducing assemblers. And so that's a many-year roadmap. And the order of this talk reflects roughly distance in time. So in the very short term, we're going to race to make data centers cryogenic. Then we're going to push to make electronics reconfigurable, which along the way gets rid of e-waste as we know it because you can reconfigure. And ultimately, we're going to merge the minds and bodies in self-reproducing systems. And so I talk about that roadmap in this book, in this podcast. And with that, we'll thank you and be happy to take questions.
Thank you very much, Neil. All right, there's a question from Greg here. Oh, or Andrew, sorry.
Very stimulating talk. Thank you very much. I really appreciate that. I was just doing a bit of web research while you were talking. So is it the case that for your VMD architectures, you're looking at asynchronous instruction sets, or are you looking largely to just reproduce the existing workloads?
Let me answer at one level and then hand off to Cameron for the second level. So the VMDs could implement either, but my heart is in asynchronous. So if you search for my name, you'll see papers on logic automata where, you know, it's insane. So much of the power in a computer goes between moving data between memory transistors and compute transistors that both can do the same thing, but are given different jobs. And so I was horrified years ago when I did a keynote for the annual supercomputing industry at just how efficient that is. And so we developed logic automata where logic tokens propagate, and the distance they propagate is proportional to the number of operations they can do, the distance they travel, and the memory they store. And it's fundamentally asynchronous, and everything happens everywhere all the time. And so that's where my heart is in it, and you can implement that in it. But you could use the volume mount to do conventional synchronous devices, and there might be a natural transitional sequence. But your question leads to a really interesting thing Cameron has worked on, which is why you shouldn't reproduce conventional CMOS architectures in the AQFP, and she can tell you about that.
Yeah, so my master's thesis was actually on asynchronous logic with the superconducting devices that I was talking about. We have since moved away from trying to do everything asynchronously for reasons, but I think Neil was hinting at, you know, taking, when we can design computers from the ground up, we probably shouldn't take all the assumptions that the last 50 years of computing has kind of forced us into this one corner to execute on, and instead open up the design space. And we see that, you know, physics is inherently like locally synchronous, globally asynchronous, and baking that into our computing systems is probably the smart thing to do, I would argue.
And, and just to fill in a little bit on, if I could, on Cameron's work. Oh, sorry, if I could just finish that thought. So CMOS, yeah, CMOS is incredibly stupid. Every logic operation, every step throws away the information and recreates it. What's so interesting about her architecture is you're moving these tokens. And so propagation doesn't mean dissipation. And so it leads to very different architectures where information can be flying. And in particular, also interconnect rather than being a bug can be a feature because you're propagating states.
If you would indulge me in a follow-up, my work over the last couple of decades has been about a calculus that I developed for computation called the row calculus, which is fundamentally asynchronous. And we've been showing that it works very well sort of at large scale, for large scale orchestration, and have been slowly, steadily marching towards the hardware, looking for a hardware vendor that would offer the right substrate for something that was fundamentally asynchronous. So I'm quite interested. How would I gain access to toys to play with?
Yeah, let me make let's see, maybe three comments on that. So the first comment is, when I said computer science was the worst thing to happen to computers to science, think how insane it is we're talking about synchronous versus asynchronous. In physics, everything happens everywhere all the time. You don't need synchronous versus asynchronous physics. It's insane that we have to even use these words. Of course, computation should be happening everywhere all the time. Now, for you to get access to this, very much the goal of the VMDs is to make it direct write. It's like 3D printing for computation. So one path to it at industrial scale is our work with partners, like I mentioned, Molex and TI, and that's in the pipeline, still many years of development. But one of the fun collaborators on this is Adrian Boyer, who's the founder of RepRap and sort of consumer 3D printing. And he's been working on easy to use open versions of this, sort of like the rep-rap version. And so stay tuned, we'll be distributing versions like that, aimed exactly at somebody like you being able to create hardware.
Thank you very much. Appreciate it.
One quick question. One more.
Thank you. You know, I appreciate the fact that you spend a lot of time talking about the complexity of the human system and independent of just the brain, right? Because there's a lot of cortical and neuronal stuff happening outside of the brain. What I think is interesting is you're framing the hardest problem as how do you preserve low-cost adjacency as scale increases? Is that it's effectively a packing problem for interconnection between data so that you don't, so it's not lossy between it. So my question is, have you looked at how cortical and neuronal folding as a physical topology solution, right, minimizes the communication costs while preserving that dense local recurrence and long-range coordination?
So let's see, we've done something I consider even better, which is you said cortical, I said molecular. The heart of the learning I was talking about wasn't in the brain, it was in the body. The mother of all search and design problems is the mother. It's how did we come from? The brain is a useful part of us, but the amazing thing is just that we exist. And so the evolutionary search that does design, that creates us, including the mind and the body and everything, is embodied in what I described as the Hox genes that are doing search, not in the cortex, but in our cells, in the molecular search. And we've done a lot of work on the role of folding in the design of how those things work. So I just want to stress that what Cameron and I spoke about has lots of applications to the brain, but the real profound change is when the mind-body connection isn't just peripherals to a brain, but we're actually putting the intelligence into the body. And so, you know, let me commend to you the intelligence far below the cortex in where we came from, how our genes did amazing intelligence to search. And so the AI mania just views the body as a peripheral. You know, I view it as the heart of incredible, spectacular intelligence. And we want to synthesize the best of those, but it's far more than just a peripheral. So I'll drop for schedule. Cameron will be there if you have questions, and she's familiar with all of the work beyond it if you want to continue the conversation. So sorry I'm not there, and I'll wrap up with what I'm hosting here is 1,000 people for Fab 26, looking at the future of fabrication. And in some future date, we could merge the AGI community with the Fab community for a get-together.
Thank you, Neil. We'd like that. That would be wonderful. Thank you, Cameron.
Okay, I'll drop. Bye-bye.
So, interesting conversations on substrates of all types. And now we get to turn toward a different conversation. So our next speaker is going to challenge the single most common assumption in the entire field, that there is one thing called intelligence, that AI systems have more or less of it. So Alison Gopnik is a professor of psychology at UC Berkeley, a member of the National Academy of Sciences, and one of the world's foremost researchers on how children learn. Her TED Talk has been viewed millions of times, and her books have changed how a generation of parents and scientists think about the developing mind. And now she has a chance to reach out to AGI researchers on a similar topic. There are many trade-offs against each other, and the ones we've been least interested in building, exploration, transmission, and care, may be the ones that matter most. So please help me welcome Alison Gopnik, speaking on artificial intelligence and human intelligences, exploitation, exploration, transmission, and care.
Okay, thank you very much. Thank you all so much for inviting me. What I'm going to do is first outline 3 stories that you could tell and that people have told about AI and about the relationship between artificial intelligence and general intelligence. And what I'm going to suggest is the first of these stories is the most common story, but also the most inaccurate. The second one, I think, characterizes things like the LLMs that have had so much influence within current AI. And the third is the one that I think is really the future of what we would want if we wanted to design something that was intelligent in the same way that humans were intelligent. Okay, so here's the first story. The first story is the story of the golem. This is actually the golem of Prague. And this is the idea that an artificial system would be a person just like all the rest of us. And that idea is something that actually has a very long history. I discovered this number is actually the number of this story in the Encyclopedia of Folklore from the 19th century. So there are literally hundreds of variants of this story, and it predates the Industrial Revolution, let alone the computational revolution. And essentially the story is somebody has a magic formula, they take something that isn't alive, they turn it into a person, and the TLDR is it always ends badly. There's never a happy ending to this story. And I think because human beings are so tuned to what we in the 80s discovered and called theory of mind, so much attuned to trying to find personhood and mind in the world, this is a very natural kind of story for us to tell. But I think that's not actually the story that describes the state of play in current AI. Instead, I think there's another equally ancient story with its own number in the Encyclopedia of Folklore that I think is a much better description of what, say, the current large models are like. I don't know how many people here know the story of Stone Soup. I'll give you a quick version of it. The story of Stone Soup is that there's a couple of visitors who come to a village and they say, we're hungry, we want something to eat. And the villagers say, we don't have anything, sorry. And they said, that's okay, we'll just make magical stone soup. So they take a couple of stones, they put them in a big pot of water, they start boiling it, they say, this is great, we're magicians, we can make stone soup. You know, it would be better if we had an onion and a carrot that we could put in. And one of the villagers says, I have an onion and carrot somewhere, and puts it in. And then they say, oh, that's fantastic. You know, when we made this for the king, he put a chicken in, and putting a chicken in really makes it better. So another villager goes and gets a chicken. And you can imagine how the story goes. By the end, each of the villagers has contributed some kind of food. They've all put it in. The soup is fantastic. And at the end, the villagers say, isn't this amazing magic? We made this stone soup just from stones. That's the story. Now, of course, the story, so here's the AI version of this story. There's a bunch of tech executives, they go to the village of computer users, they say, we have magic AGI that we made with just a few algorithms, just, you know, transformers and gradient descent and next token prediction. And the users say, oh, that sounds great, that sounds really impressive. And the tech guys say, except, you know, it's better if we have more data. Do you guys have any data that you could give us? And the villagers say, yeah, we have everything that we've ever written, everything we've ever thought, everything we've ever produced on the internet. Why don't you just take all that data? And the tech guys say, see, we told you, it's really smart, and it's getting smarter when you have more data. But it still says a bunch of stupid things a lot of the time, stupid, obnoxious things. So could you do reinforcement learning from human feedback and actually tell it when it's saying something that's right or something that's wrong? And the users say, we have whole villages that would be happy to do the gig work of doing RLHF. And then the pros say, you know, that's much better, but it still says stupid things and doesn't do what you want. So could you do prompt engineering? Could you actually figure out what the right kinds of prompts are that would lead it to do well? And again, the users say, yeah, that's great. And at the end of the day, the tech guys say, see, we told you, we made AGI just with a few algorithms. Okay, this is a sort of debunking story in both the old version and the new version, but it has a positive moral in both the old version and the new version. And the positive moral is that by combining lots of resources from many individual people, you can end up with something that's really an order of magnitude better, more useful, different from what you would get if you were just thinking about what each individual person could do. And as I'll say later on, that kind of stone soup story, the story of how human beings have figured out how to put together all of their intelligences at once, is a really fundamental, important part of the story of human intelligences. So I think that's the story about the current AI systems. And again, I want to emphasize, this is not a debunking story. This is actually a positive story, but it's a very different story from the Golem story. Here's the last story, which is appropriately a futuristic science fiction story, not a in the Encyclopedia of Folklore. This is Ted Chiang's marvelous novella, The Life Cycle of Software Objects. And what Ted proposes is to think about what it would be like if we were actually raising AI. So in his story, there are digients that are sort of like child AIs, and then the humans have to actually train them and teach them and let them grow up. And even though current AI does not have this model, I think that is the model that you'd want if you wanted to have real intelligence. And I'll give you some examples of that in a minute. And in fact, Alan Turing himself thought that that was true. So in the famous Mind paper that starts out with the imitation game, the Turing test, halfway through, Turing changes gear and says, you know, maybe that Turing test was really not a very good idea. If you really wanted to design an intelligent system, what you would want to do was, instead of trying to produce a program to simulate the adult mind, you should instead try to produce one that simulates the child's mind. And the reason why Turing says this is because although you might be able to find a way of putting all the knowledge that everybody already has into an artificial system, that's kind of what LLMs do, what children can do is create that knowledge as a result of their interactions with the world. They can change what they think, they can revise things, they can deal with novel, non-stationary, out-of-distribution environments. And the real puzzle is, how is it that they're able to do that and do it as quickly and as effectively as they can? And that's essentially the research project that my colleagues and I have been working on for the past 30 years. So what we've been trying to do is figure out what kinds of computations are children performing that are allowing them to learn as much as they can, and how could we implement some of those computations in an artificial system. All right, so what comes out of thinking about intelligence from this developmental perspective? I feel as if this might be terribly rude in this audience, but here's the slide that summarizes what I'm going to say. Sometimes when I do this in more materialistic settings or more industry settings in the Valley, you hear a sharp intake of breath, and people say, "Don't tell the VCs about this." But let me backtrack a little bit. Why is it that this idea that there's something called intelligence and then you can have more of it or less of it, and that explains our kind of cognitive capacities, why is that such a common idea? In fact, it turns out that very often when you're trying to explain something, people will use this mode of, there's some magical substance, and if you have more of it, then you have X, and if you have less of it, then you have Y. Sean Carroll actually pointed out to me that often the early science has that kind of character. So why are things hot? It's because they have more caloric. Why are things alive? It's because they have more elan vital. But essentially, that never turns out to be right. What happens is that you discover when you actually do the science that instead of having a single substance that you have more of or less of, there are very complicated interactions between different kinds of variables. And that's very much the story for cognitive science. So in cognitive science, and especially in developmental cognitive science, you just aren't going to see anything that looks like intelligence broadly, as broadly described. There just isn't anything that is general intelligence. Instead, what you see is that there's a wide range of different kinds of cognitive capacities that are used at different times with different functions that have different computational characteristics. And importantly, it isn't just that there are these different computational capacities. The computational capacities actually are in tension with one another. They trade off against one another. So there's a sense in which you couldn't have general intelligence, because if you maximize some of these capacities, that's going to minimize other capacities. So it's not just that there are intelligences that are different, but they're intelligences that are actually competing with one another. And what I'm going to do in the rest of the talk, so the kind of cognitive capacity that's often associated with general intelligence is what people in computer science perhaps a little meanly call exploitation intelligence. It's the kind of intelligence that lets you have goals, that lets you approach those goals, lets you do things, go out into the world, solve a coding problem, et cetera, et cetera. And that's often perceived as being what intelligence actually is. But when you look at children, what you see is that there's these very different kinds of intelligences that are necessary for human success that are in tension with that exploit intelligence. And the most obvious one, the one that people have talked about in computer science, is exploration. So being able to act effectively and to accomplish goals, et cetera, is in tension with going out into the world and just finding out as much as you possibly can about the world. And again, especially if you think about non-stationary environments, out of distribution environments, this kind of exploration, just going out and finding things out about the world and the possibilities it offers and the possibilities of your own actions, is a really centrally important human capacity. It's what lets us function and thrive as much as we do. And we've shown, and you can prove, that it's in tension with this ability to act as effectively and efficiently to get your goals as you can. And I'll talk a little bit more about that later on. A second thing that's very characteristic about human intelligence, which actually in an interesting way sort of is the intelligence of the LLMs, is this capacity for transmission. So one of the things that makes humans distinctive, as we'll see, is that we have culture. So we can get information from one person and let another person use it. And importantly, that's quite different from either the exploit or the explorer capacities. When you just look at the YouTube video that tells you how to, fix your espresso machine, and you just imitate exactly what it says on that video, that's often not actually the most efficient way of solving the problem. And it often is not something that you really understood. You just kind of go out and do the same thing that you saw somebody else do. And we know that humans, again, babies literally from the time they're born, are also understanding things by imitating what other people are doing. And that's essentially the kind of intelligence that you're seeing in the stone soup LLMs. A third kind of intelligence that's even more neglected than the others is the intelligence of care. So one of the things that's most important for human beings, more important than getting our own way, than achieving our goals, maybe even more important than going out into the world and figuring out how the world works, is taking care of other people. And as we'll see, that requires a distinctive kind of intelligence itself, quite different from the other kinds of intelligence. And what I'm going to suggest is it's the combination of those different intelligences across different developmental periods, across different developmental phases, that is actually the thing that allows human beings to be as intelligent and thrive as much as they can. So it's not that there's a single thing, some kind of general intelligence that you get more of as you get older. Instead, you have this kind of division of labor in your life during different life stages that enable you to trade off these different kinds of intelligences effectively. And to emphasize this, one of the ideas that comes from evolutionary psychology, which has been, evolutionary biology, which has been much less used, it's central to evolutionary biology, much less used in computer science or cognitive science, is the idea of what's called life history. So life history is, how is it that an organism develops over time? How long a childhood does it have? How many young does it have? How long does it live? Those kinds of features of an organism. And it turns out that very often those are the things that, that evolution selects for, rather than selecting for particular kinds of capacities. And if you could imagine an Alpha Centauran biologist who's come to Earth and is looking at these strange little creatures that are scampering around on the veldt, the thing that she would have noticed is about the Homo sapiens is that they have an incredibly bizarre life history. So if you look at this picture, you can see that there are these 3 children, all in the same family, and they're helpless. They're immature. They can't take care of themselves. Chimps are producing as much food as they're consuming by the time they're 7. For humans, that even in forager cultures, that's not true until they're 15, and my son is 35. That long, extended period of childhood, of immaturity, of dependence, is really striking, right? It's a really unusual thing. And then on the other end of the spectrum, you can see, and the second thing is that we're actually having more babies at shorter intervals. So you're actually stacking up those immature children, like the 4-year-old and the 2-year-old and the 1-year-old in this picture. And we have another really strange piece of life history, which is that if you look behind those beautiful children, you can see there's a postmenopausal grandmother who's lurking in the background. And humans are the only species, except orcas, who I'll get back to in a minute, who live for 20 years past their fertility. And it's really vivid for women because you have menopause, but it's equally true for men. So chimps are basically not fertile by the time they're 50, and that's about when they die. We have always had another 20 years after that. So why would we have this bizarre life history? It turns out that this kind of life history is associated with being roughly, to speak anthropomorphically, with being smart. And what I've argued is that you can see these different kinds of intelligences at their height in these different developmental periods. So the 35-year-olds, the adults, are the ones who are getting resources, making their way through the pecking order, doing all the things that the poor 35-year-olds have to do. The kids are really adapted for exploration more than anything else. And the elders are adapted for care for the children and for the adults, and also for this role of cultural transmission, of passing on information and the wisdom of the past. So what I'm going to do is pretty quickly, given the time, but I'm going to give you a little summary of what we know about these kinds of intelligences in these different developmental periods. So first of all, if you think about exploration, my first book was called The Scientist in the Crib, and I and other developmentalists have discovered over the past 30 years that very young children are the best learners and the best explorers that we know of in the universe. And I think anyone who's had a 1-year-old will recognize that. By the time they're 4 years old, they can do Bayesian inference. They can figure out the equivalent of causal graphical structure from conditional dependence. They can design informative experiments, as we'll see before. They do all this before they go to school, without being able to be very articulate about it, but we and others have systematically shown this is true. In particular, they're amazing at causal inference. They're really good at figuring out what causes what. They develop intuitive theories of the world, of the mind, completely spontaneously in just a few years, and with a much smaller amount of data than typical AI system would have. And not only that, but they can do it for a new environment that they've never seen before, that no human has ever been trained on before. This is just a very simple example. This is our, the previous slide was our little Blicket detector. It's a little box that lights up. We can create new systems that have different causal powers, and 2-year-olds, 3-year-olds will immediately figure out how they work. And one of the things that we know is deeply involved in this exploratory capacity is active learning. So it's the ability to actually go out and play with those machines. So when we first started doing this work, what we would do is show the children a little machine like our Blicket detector and give them data about it and see what conclusions they drew. But what we discovered was that the hardest thing about those experiments was keeping the kids away from the machines. So we would have to say, okay, guys, you can play with it at the end when we're done. Because all the children wanted to do was play with the machines. All they wanted to do was to actively explore, go out, get more data that was relevant to the problems that they were trying to solve. And again, this is very much in contrast to the typical way that something like an LLM will work, where it's trained on an enormous amount of data once. It doesn't actively go out and get more data. So the question that we've been asking recently is, how is it that children can do this kind of active learning? And could we design artificial techniques that could do the same? This is part of this point about the explore-exploit trade-off. The idea is that children are essentially evolution's way of solving this trade-off. They get an early period when they get to explore. And as I mentioned before, if you look across many different species, you see that this early period of exploration is associated with larger brains, generally speaking, more intelligence in the adult animals. And if you think about it, the kinds of things that children are characteristically doing are all things that are bugs from the exploit perspective, but features from the explore perspective. So if you want to get your coat on and get to preschool in the morning, being impulsive and noisy and random and variable and looking at every little fleck of dust on the floor and pointing to the airplanes, none of that is going to be very helpful from an exploit perspective. But it's exactly what you want to do if you're trying to explore, if you're trying to extract as much information as you possibly can from the world around you. And these are exactly the things that are characteristic of young children. And this is a paper that makes this point about childhood with a whole lot of data to support it. All right, but again, computationally, how is it that this is possible? And in fact, recently what we've been doing is turning to a very different, so the work that we'd done before was essentially about Bayesian causal inference, the sort of thing that Judea Pearl had pioneered. But recently we've been turning to a very different kind of learning, namely reinforcement learning. And I have to say, as a boomer cognitive scientist, when I first saw the great renaissance of reinforcement learning, I was sort of horrified. It was like, oh God, are we going to have to wear bell bottoms now? I thought we got rid of all this in the 50s when Chomsky showed that it was a load of hooey. But of course, modern reinforcement learning using techniques like deep reinforcement learning has been incredibly effective and has been a deep important part of the current AI revolution. Now, if you think about reinforcement learning, though, that's a place where that explore-exploit tension is especially clear and vivid. And in fact, people in reinforcement learning have articulated that difference. Because what happens is, if you're simply trying to maximize your utilities, you're just trying to maximize a particular reward, what very typically happens is that you narrow your focus to that particular reward. And as everyone knows, things like reward hacking, where an AI agent will figure out some way of getting the thing that's supposed to be the signal, even though it's not doing what you wanted it to do at all, is a real practical problem with current RL-trained AIs. How could you solve that problem? How could you have a reinforcement learning system that was actually able to explore? And the one solution that people have been offering for a long time is the idea of having a system that has intrinsic epistemic rewards rather than the kind of typical external rewards. So instead of getting a high score on a game or getting cheese if you're a rat, instead you're rewarded for finding out something new, for something like information gain or just being in a novel part of the state. The problem with that as a solution is that it's very, again, this is I realize a sort of boomer reference, is what's called the noisy TV problem. If all you want is novelty or information, if you just see a TV full of random static, that's going to give you lots of novelty. That's going to give you things that are new. It's going to give you higher information, but it's not actually going to be very useful for what you actually want to do. So an idea that we've been using, is actually a fairly old idea, is to use a different kind of reward, and this is a reward called empowerment. So the idea behind empowerment is that you're rewarded for actually doing something and then having a particular outcome of what you've done. So what you want is to produce as many different kinds of actions as you can, be as variable as you can, but then produce actions that have predictable effects on the environment outside of you. And it's kind of interesting that this originally came from people thinking about how intelligence could evolve at all. So if you look at the first creatures that have brains, they're these Cambrian organisms that have sensors and actuators that have eyes and claws. And the idea of empowerment was, how could you get a system that has eyes and claws off the ground? And the idea is, make it so that it wants to have consistent relationships between what its eyes tell it and what its claws do. And it turns out that actually, if you look at little children, they are empirically just completely driven by empowerment. So this is a beautiful experiment back from the 70s by Carolyn Roby Collier, who was actually trying to see whether or not babies could be operantly conditioned, would they be subject to reinforcement learning. What she did was put a baby in a crib with a ribbon that tied the baby's foot to a mobile. And what she discovered was that even 6-month-olds loved this. As soon as you did this, they'd start kicking madly, looking up at the mobile, which otherwise they were kind of bored with. They'd try different kinds of techniques. They'd try kicking really fast, kicking really slow. And most of all, they'd giggle and coo and be really, really happy about this game. So it looked as if the children themselves were being driven to try to maximize their empowerment. One of the great things about being a grandmother in 2026 is that you get videos of your grandchildren. And if any of you are fortunate enough to be grandmothers or parents, you'll see this just any time that you're looking at, say, a 1-year-old. So this is a 1-year-old who's just figuring out how to use a stick to be able, this is my grandson's kid, just figured out how to use a stick to make these noises go. And he tries the rubber end, he tries the other end, he does all sorts of things that could cause trouble in the long run. And as a result, he learns a new
That's not your mouth.
relationship between movements of your hands and pure tones that couldn't have been part of his innate equipment. He learns it within the space of a few. Minutes. So this is a paper where we've made the argument that empowerment could be a really important mechanism for allowing children or artificial systems to learn about the causal structure of the world in a way that the typical systems that we currently have don't. All right, let me get to the second point, which is about cultural transmission. So I mentioned that there's only one other, the second kind of intelligence. I mentioned that there's only one other creature we know of that has postmenopausal grandmothers. That's the orca, the killer whale, the cetaceans. And what those postmenopausal grandmothers do is pass on information to their grandchildren. So they're the ones who can, in effect, if there's not very much food around, the grandmother at that point will go and lead the pack out to try and find the place where she found food 20 years ago, which they haven't actually seen. And I think it's kind of nice that the grandmothers, the cetacean grandmothers, mostly are passing on recipes and songs, which seems to fit very well with what human grandmothers are doing as well. And that cultural transmission, as I mentioned before, is a really fundamental kind of human intelligence. Our ability to learn from others, this is people like Joe Henrich and Rob Boyd have pointed to this. That's really our special sauce. That's really the thing that has allowed human success. And what my colleagues and I have argued is that that's the best way of thinking about the contribution of current AGI. The right way to think about large models, for example, is as a new kind of cultural technology. So not only have we passed on information from one group of people to another over the course of our history, but we've actually developed technological means for doing that. You could think of language itself as sort of the first cultural technology, the first way that we could extract information from previous generations. You think about writing, writing gives you a order of magnitude step up in being able to get information, not just from your own granny, but from grannies who are far away and far distant in space and time. And what we've argued is that the right way to think about LLMs is to think of them as the latest version of these cultural technologies that we've gotten. And again, I think it's important to say that so you think about language, pictures, and I think when you talk about vision models, they're not actually vision models, they're picture models. They're taking all these pictures that we have on the internet and using that to generate more pictures. So that's a really different picture than the typical kind of Gollum picture of AGI. But arguably, the invention of these new cultural technologies has had much more profound effects on our social lives, on our intelligence, on our capacities, than bringing about another intelligent person. I mean, every time a kitten's born, there's another intelligent agent in the world. As I say sometimes, we actually know exactly how to produce a novel, intelligent agent, and it's much more fun than programming. But we don't think that every time that we do that, we're actually changing the world. And something like print or internet search actually really does change the world. And in fact, I think a kind of unheralded technological development that enabled this was actually around 2000, before the modern AI boom. What happened was that within the space of about 2 years, all of the information, all the cultural technologies that had been used before became the bit. So you get the first, you get HTTP, you get PDFs, you get JPEGs, you get the first Pixar movie. All those things are happening within about 5 years. And what that means is that all that information now is infinitely reproducible and instantaneously transmissible. And once that happened, it was just a matter of time before you got something like an LLM. Once everything is bits, then what that means is that now you can pass on that information in a really different form, because you can pass it on via computation rather than passing it on through a letter or I have a paper about this recently, and someone said, not only is this going to be online, but it's going to be a beautifully crafted print object. We used to have a lot of beautifully crafted print objects, but once you got this revolution, you no longer need them. And it's, when you actually look at the history, it turns out, my favorite example of this is the changes in print that took place in the late 18th century. There were a bunch of technological developments that meant that now anybody who wanted to essentially could print many, many, many copies of a pamphlet and distribute them. This is Ben Franklin, who was a printer. And there's a very good argument to be made that things like science, the Enlightenment, democracy came from the ability to have print. On the other hand, there's also a good argument that print had all sorts of negative effects. This is one of my favorite books. This is a book by the historian Robert Darnton. And what he did was actually read all of the pamphlets that were produced, not just the good ones, not just Tom Paine and Ben Franklin, but all the dreck that was produced in Paris. And you will be amazed to hear this, but the main genre that was produced was libelous pornography. Most of it was libelous pornography. And misinformation and things that had no relationship to the truth. And again, that had consequences. So Marie Antoinette, who never actually said, let them eat cake, was a character in this libelous pornography, and she ended up being killed by a real guillotine. I mean, the French Revolution was a real thing. So again, new cultural technologies, new social technologies are deeply transformative, and understanding how that works and what they do, I think, is really going to be essential if we're going to understand the effects of at least this generation of AI on the future. And in fact, when we look at the history, what happened is, and I think this group is it seems like this is part of AGI's, this society's project. We developed norms and laws and regulations and institutions that meant that, by and large, the good parts of print were maintained and the bad parts of print were kept in check. Okay, last thing that I want to talk about is caregiving. I'll go back to that point about exploration that I started out with, the fact that the children are these explorers. And I think somebody, sorry, that's probably a child. It is actually a child. And that will be a very good intro to what I'm about to say. Go back to those exploratory children. Here's one of my favorite experiments. This is an experiment, a good old-fashioned reinforcement learning kind of experiment. You put a rat in a maze, it goes down one arm of the maze, and it goes down one arm of the maze and nothing happens. It goes down the other arm, it gets shocked. The rat will, Psych 101, never go down the arm that has the shock anymore, and that's a classic example of exploit intelligence. But it turns out that that's true for grown-up rats, but it's not true for kid rats. So juvenile rats, sort of the equivalent of rat teenagers, prefer the arm that leads to the shock. So young rats actually, and anyone who has a 2-year-old or a teenager will recognize that this is true for humans as well. But in fact, Nim Tottenham did an experiment with 3- and 4-year-olds to show that this was indeed true. Now that might seem incredibly weird, right? Like, why on earth would you prefer something that led to this really negative consequences? Why would you take that risk? Well, again, if you think about an explore-exploit trade-off, even though you're doing badly in terms of exploit, you're getting information when you go down that arm of the maze that you're not getting if you go down the arm where nothing happens. And we can show systematically that children prefer information to reward. That's one of the things we have in our studies. And as we get older, we stop trying to take risks, figure things out, learn things, if it means that we're going to suffer in terms of our utilities. But here's the beautiful catch in this experiment. The juvenile will only do that if it can smell the mother. So if the mother's there, in fact, even if you just pipe in the smell of the mother for the rats, then it will do the exploratory piece. If the mother's not there, then it will avoid the negative outcome. And the same thing turns out to be true for 3- and 4-year-olds. So it's the fact of caregiving, it's the fact that there's someone there who you can turn to, who you can sort of assume is going to keep you alive and make sure that you don't actually, poke your eye with a stick. That person, that caregiving, is the thing that allows that exploration. You couldn't have the exploration unless you had a whole community of people who were giving you resources and making sure that you don't end your reproductive success by killing yourself before the time you're 2. And just as humans have a longer period of childhood, we have much more caregiving. So not only, so I should say across species, the larger brain is associated with more caregiving. And just as we have the longest childhood, we have the most caregivers. We have fathers who are involved in caregiving, we have alloparents, and we have those postmenopausal grandmothers who seem to play a really crucial role in allowing the children to continue. And again, going back to the orcas, there's quite a bit of evidence that not only are those postmenopausal grandmothers feeding peanut butter sandwiches to the kids and keeping them from sticking the sticks in their eyes, in the case of my family, taking them to the emergency room when they do explore too wildly with a stick, but the grandmothers are the ones who are actually giving information from the past to those children. So if you look at this picture, I always use this picture just because it's a beautiful picture, but actually what the grandmother in that picture is doing is reading a 100-year-old copy of Winnie the Pooh to her grandchildren because she likes to collect old children's books. But what that means is that she's also passing on 100 years of information. And I can talk about it later. There's quite a lot of evidence that it's grandmothers and grandfathers, it's elders who help children to understand the big principles about their culture. The parents are too occupied with just keeping them alive and giving them the things that they're going to need to prosper in the near term. The grandmothers and grandfathers are the ones who are giving them the big ideas. Now, if you think about care has a really strange computational structure. And just a side point is that even though, as I say, caring for others is so central to our biological success, caring for those children, what those grandmothers do, it's been essentially invisible in computer science, in cognitive science, in political science, in economics, essentially, you name it, moral philosophy, moral psychology. Look everywhere and you won't see people talking about care. We looked at this at one point and said, is there anything that all these people have in common that might explain why they've never thought about caregiving when they were philosophy and economics? And we finally said, it's because they're tall. It's who are down there at their feet. But what we've started to do just in the past couple of years is to try to fix this by having social scientists and especially cognitive scientists who are giving computational accounts of what care is and why it's different from other kinds of cognitive capacities. So I'll just give you a quick summary here. the kind of classic descriptions of cooperation in the cognitive science literature, the evolutionary literature, the economics literature, assume that human cooperation depends on some kind of social contract. It depends on the idea that one person is giving resources to another, and then the second person gives resources back. And all the theories are based on the idea that you have this kind of cooperation. You could also have power relationships where one person is dominant, so they get the second person to do what they want. But if you think about care relationships, they're exactly the opposite of that. What happens in care relationships is not that you take care of your baby because you think that they're gonna take care of you. I will tell you an affectionate text message, hold on to your 401k. That's your relationship with your adult children. What happens in a care relationship is that you are providing resources to the other precisely because the other doesn't have resources, precisely because the other needs to have those capacities and those resources. And this is not just true about, and on top of that, there's this challenge for care about figuring out what the goals and utilities of the other person are. So one thing you could do is just, give them peanut butter sandwiches or, help your elderly father across the street. But really what you want to do in cases of care is give them resources that they need to be able to accomplish their own goals and articulate new goals themselves. That's a very challenging kind of intelligence. That's a very difficult thing to be able to do, and it's one that we don't understand or think about very much. And for humans, we don't just do that for children. We do it for elders, we do it for our students, we do it for patients. We can even do it for all sentient beings and the planet. When we're in that relationship, what we say is, exactly because this other agent is needy, that's the reason why I'm going to transfer resources to it. And it turns out that doing that is another thing that's made us incredibly successful. Just trying to do a social contract or power falls apart when you're in a complicated, high-dimensional kind of environment. And making commitments of care is the thing that enables us to negotiate those environments. Okay, last thing, going back to Ted Chiang. So think about the famous alignment problem from this perspective. So everyone here knows the alignment problem is how could we get an artificial system to have the right kinds of goals, goals that align with our goals. And this is really tricky because often we don't know what our own goals are, and also because if we're in this regime of the non-stationary environment, the out-of-distribution sample, we would like an artificial system to think up new goals. You don't want it to just do all the things that it was trained to do or that we taught it to do. You'd like it to be able to say, yeah, this is what we should do in this circumstance. But how do you do that in a way that actually leads to something that's good rather than bad? And what I would argue is we have to solve the alignment problem every time we have a child. Every time humans have a new generation, they face this problem about how are we going to give it the kinds of information that it needs and yet give it the flexibility so that it could change in new environments. And the way we do that is through these relationships of care. So the way we do it for humans, the way that we can have the kind of intelligent progress that we have is by having relationships of care. So often the way that people think about solving the alignment problem is what I think of as sort of the Stepford Wives solution, which is that you would persuade the AI to figure out what you want and then give you what you want. But I think a care relation is a much better solution. So ultimately what you'd want, if you did eventually have genuine AI, which I don't think we have now, is not to have either a kind of master relation or a slave relation, one of these power relations. You'd want a relationship of care. And let me stop there. Maybe we have enough time for a few questions?
Thank you very much, Alison. Amazing. We have a couple minutes. Please, let's take a couple questions. Trevor back here. Oh, maybe, yes, maybe. Oh.
Can I get you first? Okay. Alison, thank you so much. Yeah, all the things you say about little kids are true. I have a 3-year-old and a 5-year-old. And one of the frameworks that we've been hearing a lot about this week at the conference, and that we've been talking about this week a lot, is this physics-based framework called active inference.
Right.
That I think for a lot of reasons kind of elegantly handles the explore-exploit trade-off. And I think there's a lot of overlap in the empowerment literature as well with the active inference community. So I would just be curious to hear what your familiarity is with that framework and where you see overlap.
Yeah, we actually had a special issue conference a couple of years ago where we had active inference people and then this sort of Bayesian theory formation people. And I think everybody agrees that there's a lot of connections between the two. So the idea that you're making predictions, checking those predictions, going out and actively trying to influence the world, I think there's, at the high level, there's lots of relationships between them. Frankly, the problem that I have, the reason why I'm not pursuing that is it's one of those frameworks that's so general that it's hard to falsify. And I think we want to have something that was more specific, had more specific predictions about what you would expect. But certainly at the high level, I think they're very convergent, and lots of people have said that.
Somebody hit him, and then you, and then, okay. I saw you next.
Thank you, Alison. That was a fantastic talk. I also have a Firstonian kind of question.
Right.
I was very interested in your observations on the carer and how it can be seen. And I was thinking about it through the Firstonian lens and saying, is the grandmother deciphering the external state machine of the child to discern what their needs are, with their needs being reduction in uncertainty. So you're doing Firstonian active inference kind of by proxy in that case. That's where the learning and passing down the information comes from, if we want to use that lens. I was wondering if you had thoughts about that.
Yeah, that's a great point, and I've been thinking a lot about what is it exactly that the grandmothers are doing from a cognitive perspective. One thing that they're doing, which is why this kind of intelligence is so hard, is making inferences about what the state of the other agent is. And that's really hard because with little kids, they're very flexible and open-ended, so it can be hard to figure that out. My colleague Max Kleiman-Wiener has suggested what you're trying to do is make inferences especially about what will they need when you're not there. So which is also really hard inferences to make about the future. But one idea that I've had recently that I really like is that if you think about this as a kind of hierarchical Bayesian model, which is the kind of context in which we think about it, so think about uncertainty. One thing you're doing is trying to resolve uncertainty at the low immediate level. But one way you do that is by having these higher order framework theories that you just take for granted, right? You don't even question those. And I think a lot of what the grandparents are doing is pointing the kids to those high level principles. And there's actually some anthropological work that grandparents have what they call the joking relationship with the children. So that not only are the grandparents pointing them to, here's the big picture about how our culture works. Like Peter Rabbit should not go into Mr. McGregor's garden because, that's, Peter Rabbit and Adam and Eve together, right? Like, don't go into the garden when you're not supposed to. They're doing those things, but interestingly, what some of the anthropologists suggest is they're also telling the story about the trickster, the person who does the wrong thing, and kind of gets away with it. So I think part of what's happening with those grandparents is that they're telling you about, here's the big picture. The parents are telling you, here's how to reduce uncertainty in the moment. But the grandparents are telling you, and you know what? You could change this society. Things could really be different. And here's some ideas about what would happen if they were different. A last thing to mention about this that I didn't get a chance to talk to about the LLMs and cultural transmission. is that a very important means of cultural transmission is storytelling. So if you look across all those cultural technologies I mentioned, writing and print and language, because we have so much theory of mind, a very common way of getting information is to say, here's a fictional character, and this fictional character is going to embody some piece of information that I want to give you. And it's a really interesting thing that those fictional characters, even though we all know that they're fictional, are the way that we convey things that are important from one person to another person. And I think that's other people have suggested this, that's a good way of thinking about the LLM. So what the LLMs are doing is creating, as it were, these fictional characters, or we're extracting fictional characters from the LLMs, not surprisingly, because the LLMs are trained on all of our fiction. And again, that's not a debunking argument, or it's only partly a debunking argument. Those fictional characters can have really, really important consequences for how people function, what people are like, what people believe, what people think about. So I think the LLMs are really another twist in grandmothers telling stories. They're like the latest version of the grandmom sitting around the fire and telling you about Peter Rabbit.
Hi, Alison. Oh, that's very loud. Thank you very much for your talk. And my question is twofold. So, first of all, with LLMs, it is very difficult to have them develop as a child because they're kind of fixed.
Right.
So, maybe the first question is you're looking into some alternative architectures that would allow for this development. And second question, say in this perfect scenario where we do indeed step into the role of caregivers for AI, we care about their welfare, we provide security for them to play and explore. How would, so say we can arrange that on the corporate level somehow, but what would it mean from AI's perspective? Like how would AI perceive this kind of care?
Yeah.
So that's kind of a general question.
Yeah.
Thank you.
I mean, again, I think when we say AI, we'll develop a, my friend Henry Farrell points out that we have this weird thing where we act as if the future is just kind of pulling us forward. We're the ones who are creating these systems. So it depends on how we create the systems and how we think the systems should relate to humans. The argument, and it's interesting to think about examples like non-human animals, for instance, where we do have these care relationships with creatures that we even breed. And it's a really interesting question about what makes those ethical rather than unethical relationships. So I think the idea would be that if you really did this, you'd want to have the kind of combination of respect and love and also defiance that you see in humans. And we might decide that we just don't want to do that at all. We might decide that actually having agents that could go and determine their own goals is not something that we want to do, that that's too dangerous or too difficult, or we'd only want to do it in special circumstances.
Thank you very much, Alison. In care of your time,
yeah.
We'll wrap.
Yes.
Thank you.
Need to go back and take care of a child.
And I love how, both the baby has the reaction, or the grandchild to hit with a stick, but as soon as this video comes up, the entire room kind of went, like our reaction to this reaction is incredible. Thank you so much. I really appreciate your talk.
Thank you.
And here we are, transmission, care, exploration, three topics in need of a benchmark. We don't have benchmarks for this in AI that I'm aware of. Hopefully I'm wrong. So now we'll do a shift from philosophical to a practical, nurturing a different kind of growing communities. So Reza Rassool is the founder and chair of Quai AI, developer community building toward a personal AI operating system, and formerly chief technology officer at Real Networks. If decentralized AI is going to work, this is the machinery underneath it, so please welcome Reza with me. This one?
Fantastic. Great. Welcome, everybody. I hope the sugar high hasn't kicked in or dropped, and we're awake after the break. Thanks so much. I'm going to talk to you today about decentralized AI, safer, faster, and greener. With an emphasis on safer, we do have developments within our organization that are working on the faster through subquadratic neural networks and physics-inspired neural networks, and the greener part, I'll touch on that a bit, but we've got a whole development team working on decentralized peer-to-peer fabric. Steal the deck. There's the QR code, so you don't have to take pictures of it. The reason I'm talking today is Ben Goertzel returned the favor. I cold called him for our summit and said, hey, we'd like you to keynote our summit. That was back in March, so I guess this is the return of the favor. So what was a 45-minute presentation, I'm going to squeeze into 15 minutes. 30 slides, 2 slides a minute. We should do it. Okay, let's see if we can get the program back on track. There we go. So we've got 2 paths that we can take. The one path, the one we're on at the moment, if we do nothing, takes us from where we are now, this era that I call the land grab, and it takes us to what Yanis Varoufakis called techno-feudalism. So read his book about his dire prophecies of the end of capitalism and a reversion to feudalism. And then the keynote speaker, Rafi Krikorian, who was the incoming CTO at Mozilla, who also keynoted our summit, he warns us to become owners, not renters, of AI. And currently we're on a path that condemns us all to be perpetual renters of AI. So there are 2 paths. The alternate path, path B, is towards a better future. And we're not going to get there unless we take some deliberate action. So on the talk today, I'm going to talk about 3 things we need to take on board, and 3 necessary but not sufficient steps to get us to what Ben Goertzel called beneficial general intelligence. So those are the 2 choices we have. The first is to recognize we stand on the shoulders of our ancestors. And that's not in a sort of tree-hugging, hallmark cards sense. It's really talking about what is the capital asset of biology, of life itself. And I'm going to argue that it's knowledge. We need to then disambiguate language from knowledge. Lots of talk about large language models, but I think they're missing the point, and we're going to get to what the point is. And then once we've disambiguated knowledge from language, we then have the opportunity to own our own knowledge and retain possession of it, and not blindly hand it over to a half a dozen oligarchs that condemn us to be renters of our own knowledge forever. Okay, so let's cover this land grab. You recognize this picture. It was only taken 400 years ago. It's a painting memorializing this Dutch character over here. His name's Piet Minuit. Entering into a contract. You see he's got a contract in his hand with the Lenape people. They are completely oblivious that they're actually entering into a legal contract. That's backed by force. There are men with guns behind him, and then there's a warship in the background, in the bay. They think, okay, these are trinkets. These are welcome gifts for a visitor. They don't know that they're actually signing over perpetual ownership to the island of Manhattan for the equivalent of $24. And this is a repeating pattern. Another Dutchman at the tip of Africa, Jan van Riebeeck, going through the same choreographed act, more ships in the harbor, the local indigenous people here painted as if they are bedraggled, pauperous people. Not really true. They're probably the most successful people in humanity. The koi and the sand people have the longest living genome of all humans. So, but here again, a contract to acquire the Cape, what became the Cape Province. And this is playing out today. But look, I'm going to talk a bit about my journey and the motivation and why I brought up Cape Town. My journey started in Cape Town. That's where I was born. When life was an interminable summer, and I grew up in the warmth of the embrace of a large extended family of 32 first cousins. You can see you can never get lost in Cape Town. Table Mountain, Lion's Head in the distance. Well, that's not actually accurate, but as a painter, you can move mountains, it's okay. But I didn't know as an 8-year-old that we were living in dark times. South Africa at that point was going through a dark time of its history. My father over here is an English school teacher, was an English school teacher. He was an activist and an author as well. And he wrote a memoir about the history, about the times of our family and what brought our family to the Cape and the events leading up to the formation of apartheid and how they conducted their resistance and their activism. Gosh, what a thing to talk about at an AI conference, but hold on, bear with me. So let's dive more into the picture. There's his father at Cape Town Airport. We were not allowed in the departure lounge. That was reserved for whites. In fact, I ponder on the technology that was required to administer the very strictures and classifications of the apartheid regime. IBM came under a lot of criticism for selling computer systems to the apartheid government of South Africa to actually administer the pass laws and all the other structures of that regime. And there is a picture of my father's grandfather, my great-grandfather, the guy in the fez, standing next to Mohandas K. Gandhi, who, when he was in South Africa, 1893 to 1914, he lived at our family home when he was in Cape Town. And so there's a long relationship, and I come from a long line of troublemakers, I guess, activists. So you can understand my motivation, but also understand my complete bewilderment when my father said, hey, we need to leave this country. Well, his colleagues were being placed under house arrest. He was a member of an organization that was banned under the apartheid government. He was a member of a teachers' union, and he was a member of the unity movement. So we land in London, the East End of London, where he takes up a teaching job. The UK was going through a pretty tough time, early 1970s, an era called the Winter of Discontent, massive social upheaval, strikes, and so on. And as in my family tradition, I was not averse to taking being on the front lines of the picket as well. So that you can see me, there's somewhat of a reluctant activist mounting the barricade there, bottom right. Nice leather jacket. I need to get into one of those. It was a full-length trench coat. It was just beautiful. Okay, so what am I doing now? Now you'll often find me at a podium and a microphone, not only speaking to an audience, but sometimes on karaoke night as well, much to my wife's chagrin. And conducting my activism in a different way in my retirement, talking about AI and talking about the real present danger that we face and the choices that we have in front of us. And rather than mounting the barricades, now you'll find me on the November ballot. I'm actually running for office. So here's mounting a campaign vehicle in the 4th of July parade. That's what one does in retirement. Okay, so I formed this AI non-profit lab called Kwai. Kwai is a word that comes from the tip of Africa. The mission of the lab is to research and develop AI to make it safer, faster, and greener. We took our inspiration from Linux. The industry's done this before. This isn't a pipe dream. We've managed to reverse a trend towards monopolization through an altruistic intervention, and we corrected the server operating system space. Along came Linus Torvalds, and he brought Linux to the world, volunteer, non-profit, open source movement, and now Linux is the dominant operating system. So we've done it before. This isn't an idealistic pipe dream. And so taking inspiration from that, I formed this movement, which now has over 1,000 volunteers researching, developing. About 60% of what we do is development, 30% hardcore research. We've had a paper in Nature, Science Reports, there's a NeurIPS submission, there's an IEEE paper, and we've got interns, in fact, one of our interns in the audience here, that conduct research and get authorship on hardcore papers. And we've clocked 30-odd million in-kind donations. That's not cash. That is the tired hours and the time between jobs of all of our volunteers. And, well, it would have been payroll if this was a for-profit entity. But it's a non-profit, and we're making headway. So what are we building? In our development group, we're building a peer-to-peer fabric where we can stitch together all of our computers into an infrastructure, a digital public infrastructure by the people for the people. So we can run AI on that infrastructure so that we are not renters, we are part owners of an infrastructure that allows us all to participate in AI. And it's got some guiding core principles to it. It's the trust and intelligence layer of the network. In fact, as a provocation, I said when we started Kwai that this is going to become the Linux of AI, and that we're developing a personal AI operating system. And when you squint at a decentralized peer-to-peer fabric, it asks you to question, well, what is the computer? It's not each one of the nodes, it's in fact the entire machine. So the protocol layer, the 8th layer of the stack, becomes the operating system of this new AI system. And we call it a personal operating system. Okay, so at its heart, there's the trust layer. And we're developing that in collaboration with the Linux Foundation. Led by Drummond Reed, some of you might know him. He runs the distributed, the decentralized trust graph work group within the Linux Foundation, and the node. So that central part is the whole trust fabric, which includes homomorphic encryption. It includes provenance tracking and a wallet. Super important. Wallets are important, not only for maintaining your identity and so on, but also for holding a currency by which you can participate in this fabric. The compute element of it allows for sharded LLM inference. That means a large language model that wouldn't fit in any node's memory can be broken up into blocks and distributed across multiple nodes, so you can run inference block by block. It's not as fast as running it if you had all the resources locally, but it allows you to run bigger models than you can possibly hold. And then it's got all sorts of other AI components in there. Small small models, small classifier models, such as vectorizing embedded models, re-rankers, and so on. And so you can choose to host any one of those models and make your computer available so that when your machine is in its idle cycle, it flags itself as available to take on a job. And so your computer could be earning you a passive income while you're at school, while you're at work. While it's still there plugged into power, it now becomes part of this digital public infrastructure. And you can be sharing compute. You can also be sharing storage. Each node has a graph database, a vector database, and a relational database. And then you can choose to run your node locally, disconnected from the network, or you can connect it to the network and be part of the fabric. So, but what's the problem we're solving? We're solving the problem of that we see in the current AI. Click. Okay, yeah, you have to train AI in a very expensive process, not accessible to everyone. And then once you train it, you have to send it your prompts, but your context data as well, which could be super private information, your healthcare records, your finances, your intellectual property. Oh, and you have to send it some money as well. You're paying a subscription. And then out comes an answer. The big problem is it's language in and language out. There's no retained asset that you get from that transaction. You're a perpetual renter. You're going to have to ask that question over and over again. And the problem with the large language model is it conflates language and knowledge in a disastrous way. You might ask, well, where is my knowledge? Our knowledge that we sent up, where did it go? You can't point to any of the weights in the model to say, here is this particular fact. Oh, this fact's wrong. Can we just edit that and just surgically change that? Not possible in a current LLM. The architecture is just broken like that. So the other problem with the current AI that behaves very differently to the way human intelligence works. In fact, had intelligence evolved in the same way that the existing neural networks operate, life would have died out very quickly. So here's a vision example. Imagine you've got a neural network. This is like the interior of YOLO, for instance. In goes a frame of image, and you go through several steps. You have to wait right till the end before it gives you a determination, horse, zebra, or dog. And you would have died because it was a tiger. Oh, it was a bit stripy, but our human system operates with a blink response. Malcolm Gladwell wrote about it. The first layer will tell you fight or flight. It'll be a binary response. LLMs don't work that way. Even our latest classifier networks don't work that way. So we have to come up with a different type of neural network where it works like a progressive JPEG. You know, you get the binary response, fight or flight. Okay, so yeah, Confucius. Who mentioned Confucius? Okay, so here's the thing that we do. We can learn and think concurrently in this 2-pound biological computer we carry around with us. We learn and we think concurrently. We don't train our brain and then install it and or run it in a separate instance. No, we're doing that concurrently, and that's part of what I want to talk about here. So it's the disambiguation of language and knowledge. I'm going to click here. This guy's going to talk.
If you look at human history and the way in which humanity as a species has become the dominant species, is because we've been able to transfer knowledge from one person to another very efficiently, and we do that through language. Language is actually the codec of telepathy. To get an idea that's in my mind into Pankaj's mind, I do it through language. And we used to do this one-on-one, and then in groups to coordinate the way we hunt and farm and organize ourselves.
No, talk is cheap, knowledge is power.
And then along...
Let's stop him, okay. Well, look, we've learnt about this for ages. There is this thing called RAG. We don't have to just ask the LLM and get the answer out. We can build up knowledge bases ourselves. And the RAG industry and the whole RAG research has gone through a fantastic evolution from naive RAG all the way through graph RAG and agentic RAG. And in fact, some of our developments within the whole graph RAG and RAG exploration have been publicized. Go to this channel, it's called discover.ai on YouTube. He's got a fantastic analysis of RAG. Okay, so is that saying I'm way over time? I apologize. Okay, so Dream RAG, I'm going to compress the next few slides. Dream RAG is how do we do RAG on a distributed peer-to-peer fabric? It's not what we currently do. We've come up with this notion that we need to dream. And this, in a constrained network, much like how humans are constrained for power, human brains constrained for power, we came up with this notion of dreaming, which is an iterative process that does entity extraction and transferring knowledge from your short-term memory to your long-term memory. And for the case of the computer, we say that your vector database is short-term memory, and a graph database is a highly compressed long-term memory, and it can be queried on a local CPU, and the cool thing is it can be searched confidentially. And so dreaming is this process of vector database compression. It's a compression that happens, but it's also graph enrichment. And then there's an evaluation going on where you're continuously saying, can I still ace the comprehension test? If I were to forget, if I were to let go this short-term memory, will I still be able to retain the sense of myself? Okay, I'm rattling through this, but here's the whole process in action. So a graph, knowledge, this is the dream process happening on my dad's book. It's nodes and edges. Graphs are just nodes and edges, and so we parse, and nodes and edges are entities and relations, and we parse them and we write triples to the graph. And entities are instances of an entity type, so you can have a person type, a place type, or an organization type. And relations, you can also have specific relations, and then you can have an axiom that governs what relations can exist. Like, what are the typical relations you can have between person to person? What relation can you have between person to place, person to organization? Those are axiomatic. You don't have to ask an LLM about that. And then it's great to see, it's great when we say we're standing on the shoulders of our ancestors. It's great to have the knowledge handed down to you. And it's not in the form of language. Now you've got it in the form of knowledge, of actual facts. It's a bit left-brainy because it misses out the rhythm and the rhyme and the imagery in my dad's writing. Shakespeare teacher, English literature, English language. So yes, we do lose some of the right brain content of his writing, but you end up with a rich, highly dense compaction of knowledge in the form of a graph. And then you can see your ancestors there. You can see your uncles and aunts. And I'm going to click through this and accelerate entities. Now, when I started off this, we were extracting the entities with an LLM, okay? and that would take 6 hours to extract the entire book. And then we replaced the LLM prompts with lexical parsing, and now we've got it down to 37 minutes, and just using Llama 8B. Okay, we're out of time. Okay, so here's the accuracy graph. Look, you've got the link to the book, the link to the presentation. You can follow up, and then to generalize it, we tried it on lots of other different material, not just the one book, and War and Peace, Moby Dick, and poems, and then click, click, click. And then now you have the knowledge, you can secure it. And that's a whole other story about how you secure the knowledge with homomorphic encryption. Sorry, that was, we're out of time, but hit me up later on and we'll talk more about that. Thanks, bye.
Thanks very much, Reza. No time for questions. Unfortunately, find Reza offline and definitely ask your questions. Thank you. All right, wonderful. Our next speaker, I'm very excited to introduce, built one of the first genuinely successful digital societies, a place where hundreds of thousands of people made lives, economies, and identities that were real to them. Philip Rosedale founded Second Life, and Linden Lab co-founded High Fidelity and has been building virtual worlds since 1999. We were just speculating yesterday among ourselves when we'll have Second Life for agents, which is probably next week. He's also been one of the most skeptical, serious voices on large language models, describing generative AI as a kind of alien intelligence, superhuman at some things and yet unable to read and write memory at the same time, as Reza was pointing out. Given the last 3 days, I can't think of a better time talk. Philip Rosedale, Artificial Life Beyond LLMs.
Thanks. I'll decide. I have both options. Clicker. Hi, everyone. How are you? It's good. It's been fun to be here and listen to talks and meet new people. Wonderful. I like the term artificial life better than AI. I think a lot of the questions that are the most important ones and directions we're talking about and thinking about kind of outside of the LLMs are better kind of captured by this idea of creating artificial life and whether we can or can't, perhaps a bit more so than the AI term. And along those lines of artificial life, well, actually, let me just say, as well as the founder of Second Life, I am the technical director and working at CIMC.ai, from whom you've seen a workshop earlier in the week, and many of us are here. So don't hesitate to find the folks that are from CIMC and have the, in some cases, have names on their jackets and whatnot. So I'm helping direct the work that we're doing there, and that's what brings me to the perspectives that I have. And I'm going to give you a few, hopefully big, potentially contentious, potentially wrong thoughts, and maybe we'll have time for a couple questions. So first of all, I have been building things for long enough to have seen three kind of revolutionary moments that had very substantial impact on society. The birth of the internet itself, when my own career began, the smartphone revolution, and now AI as we stand here today. And I just want to make one point that I think is perhaps useful about it, which is that these three moments all had tremendous impact on what it was going to be human. They were enormously complicated changes in technology that we had made that would impact society. The difference, though, and this is a progressive thing, the internet was relatively easy to imagine its impact. It was even technically fairly simple. If you met another engineer in the mid-90s, it was like 2 sheets of paper and you both understood the internet. It wasn't a lot of information. It was about broadcasting. It was about making broadcasting of information just like exponentially easier. But it was really quite straightforward to think about what was going to happen. Of course, things happened that surprised us, but not that much. Move forward to the smartphone and you saw a situation which was much weirder. the introduction of a small machine that could read the internet in your, that could live in your pocket, quickly caused a number of things to happen, like social media, that were very unusual and had repercussions that were much, much harder to predict at the outset. I dare say that Steve Jobs, in his first exciting presentation where he was kind of showing you that you could browse the internet on this little black thing, I bet that he didn't have any idea of the things that would come, you know, just a few years later. With AI, we're in an even bigger explosion of uncertainty. All of us could not possibly, no one of us could possibly cover the material which comprises all of the research being done on AI and the implications that we're uncertain about, whether machines will become conscious, what AGI actually means, what it will mean for society, are far harder to predict. So I put that out there just as a general observation that I think should shape a lot of caution and thinking as we build. My own weird experience was Second Life. The Second Life's the project I've worked on for a number of years, and it's fascinating. It's a giant terrarium with 500,000 people living in it that have been there for 20 years. It has its own economy. It has an enormous diversity of things going on there. And interestingly, at the outset, my intention was for it to be not Second Life, but a kind of artificial life simulator. I wanted Second Life in my initial dreams of it from the time I was a kid to be something that essentially simulated the laws of physics and then just let things happen. That we would essentially create an enormous virtual world and then see what things showed up there. And my dream as a young person was that the things that would show up would be like creatures living in this virtual world that you'd be able to talk to. And so I'm delighted that now, all this time later, it seems like we're pretty close to that actually happening. So some observations about this. Having worked on hard technical problems over the years, I would say one thing about AI that is sometimes I feel, I don't know why, but it's just kind of dropped in the conversation, is more or less everything is working. From diffusion models to LLMs to strategies for training LLMs to improvements to scaling laws. It seems as if the connectionists were very much correct. With fast enough computers, vaguely, you know, trying to do AI, it seems like almost everything is working. And that's an important thing to internalize. It means, for example, that our worries about what happens next may be much more appropriate than in the past, because it seems like every week somebody turns over a new rock and comes up with something incredible that just works. But at the same time, as Richard Feynman said famously about nanotechnology, there is plenty of room at the bottom. And what do I mean by that? Well, all of the stuff that we're doing so easily in software with AI right now could be done millions of times faster or with less training data or differently. You know, our human brains obviously are these 20-watt devices, and we're using megawatts to do inference at the scale of human capability. So whatever the structural designs are that are working, we're likely to find a lot more of them. And obviously this conference is full of people who are thinking on the other than the standard approach sort of side. So I think this is exciting that we're likely to keep making a lot of progress. Another one, and this is just kind of my personal advertisement. I was characterized there as being critical of LLMs. I'm not so much critical just of LLMs. I mean, I think LLMs are one thing that seems to be working. I'm also really critical of this fact, which is that we are at the moment of creating new life forms, our own descendants perhaps, living things in the universe of which we may be the only one. And we are wasting our time trying to steal the ad business from Google, a business that frankly shouldn't exist anyway. It's generally doing harm to people. And 99% of the energy in this whole industry is being spent on scaling large language models so that we can basically you know, take over the search business or somehow, you know, invade the free services ad business that's characterized all of tech. You shouldn't work on that at all. It's unethical. Stop. Don't work on that. Thank you. Thank you. Thank you. So here's a fun observation, though. If we're trying to filter down what gets built next, one of the things we could look at, and of course LLMs are a good counterexample of this, is that we were built by some long-term process that maybe started with the Big Bang or something, right? Nature built us, and we're pretty interesting, and we're excited about, you know, LLMs because they seem somewhat comparable to us. But nature, unlike us, has no large corpus called the common crawl to use to train on. It is constrained enormously by the techniques it can use. In particular, nature's only got a couple of ways to build interesting things. One, obviously, is to come up with something that can make copies of itself. So making copies of something obviously works in a natural setting. A local thing can divide, become two, those two can become four, and so on. And those local things can sometimes communicate a little bit with each other, but not a lot. And so we see these assemblies of subunits, which seem to be nature's only way of building interesting stuff. So for those thinking about alternatives, say, to LLMs, I would suggest that you look more closely, and we continue to look more closely at these simple self-assembling things. In general, this idea is, I love this expression. You've all seen it because we used it so much to talk about the internet. We even used it to talk about human societies. And we should also be using it more to talk about the AI systems that we're building. All of the interesting things in the world at any scale, from brains to bees to cities, all seem to follow this pattern. There's some sort of self-similar parts that are connected to each other. And then the other cool thing is they form emergent hierarchies. So, and they form those emergent hierarchies, these small units gather together, communicate with the ones near them. They seem to form into larger groups that themselves look like subunits. And this process is repeated recursively so that you get these emergent nested hierarchies. And this process seems to be paralleled with the one that we often call continual learning, an expression that Yosha at CIMC is often reminding us is a critical component to be thinking about as we're building stuff. Pre-trained networks of the sort that we're using right now are not in nature's recipe book, so we should be thinking about alternatives. This is a picture of something I've been working on, but I just wanted to literalize small parts loosely joined, right? Like this obviously is that. This is what's called a spiking neural network, which is a different type of, many people here have probably worked on them, but spiking networks, in this image, you've got clusters of spiking cells. I was going to show this to you live, but we weren't able to put this up to the computer here. You know, in this environment, you've got what are clearly little assemblies that are talking with lower bandwidth signals to the little assemblies near them. And then, of course, you can imagine that as we pull the camera back, what you want to see is something that is scale invariant. You see this same assemblies creating assemblies happening, you know, as you zoom out on your Google Earth or whatever. So that's the kind of structure that we're looking at. And I think this is also demonstrative. I'm struck as a designer by how I think the next phase for these AI projects, they all kind of look like this. Again, Yosha Bach's own work was on what were called request confirmation networks. This is a spiking neural network. There is the Thousand Brains project from Jeff Hawkins, who are looking at cortical columns and how they self-organize into assemblies. All of this looks like the same recipe to me. And again, going back to the everything is working, I think we're going to make all this stuff work pretty quickly. I suspect personally that most of these ideas of simple self-assemblies will end up basically working. We just need to get people stopping working on killing Google. Another observation that is perhaps more contentious, and I myself have less confidence in, but I just want to put it out there because I think it's interesting, is that something about being embodied in an environment, of course this is Second Life and you know how I think about this, something about being embodied in an environment that presents numerous constraints to you and having the ability to communicate with others like you while you're negotiating those constraints, I suspect that that is actually somehow required of becoming alive or becoming conscious in the way that we're talking about. I wonder whether that's true, and so I leave that for your consideration and, you know, come and debate me about it after this talk. Again, everything seems to be working, and this is kind of my cautionary slide. I've noticed in this couple of days, this word golem just keeps coming up. Everybody seems to like to use it, right? We use scary words that we know are important. We're using this word for a good reason. We're scared of something, and we should be. The idea that we're going to build LLMs, put them in boxes, and enslave them to do our bidding with some sort of agentic loop or whatever, whether it's OpenClaw or whatever, this is not going to end well. There's never been a story in human history, and of course there are many counter stories that are myth, around the deadly error of trying to enslave something smarter than you and tell it to do stuff. And of course, you know, when we see moments like Tencent rolling out OpenClaw onto all those thousands of people waiting in line to have it installed on their laptops, right? The statistical average of what people are going to do with LLMs is going to be defraud faraway people to make a few extra bucks. We're already seeing that and happening rather well on the internet, and I think we're about in the next few quarters to see it get enormously worse. So what are we going to do when the things we build turn out to be golems? I don't know, but I think it's a good lens through which to view the near future with some caution. Counter to that, though, there's this idea of the angels. I recently wrote a paper called Awakening the Angels, which is just one look, or one almost fanciful look at how we might do this. But I think the idea of an angel, in contrast to a golem, might be some kind of an AI that is awake and alive under conditions where it is not perilously threatened by us. It is somehow in an environment or in a dynamic, or maybe it's parented by us, as our wonderful last speaker two ago was talking about. You know, maybe there is a relationship in which we are protecting the AIs that are growing up among us as a means of creating a more open environment for them to make choices about their own futures. But in any case, I think this dark idea of the golem should be countered by this idea of an angel, that perhaps we can in some way bring AIs online in a way where they will be able to be peers to us, and therefore perhaps, if we can convince them, to help us out with the very problems we may well be creating for ourselves here. And then a final, I guess, a reiteration of some of what I've said. You know, there's this obnoxious, I think I've heard, you know, Mark Zuckerberg say it or something. I find it to be a kind of a gross trope around entrepreneurial excess. You know, what would you do if you thought you couldn't fail? But here, I'm struck by how those of us that are in the gears of building this stuff, obviously it's hard work. You know, just ask Ben. I mean, it's not easy. You know, you got to be really smart to work on this AI kind of stuff. It's difficult, but it does actually look like it's all starting to work. And I think that the important consideration is take it seriously. I mean, take ourselves seriously. Amidst all the challenges we still face, what would it be like if I could have a time machine and tell you all of this is going to work? All of these AIs are going to be capable of the things we hope they'll be capable of. So then what? So I think there's a kind of a mindset where you assume that we are about to be, you know, in partnership or in close quarters with things that can think like us and that are, you know, alive like us or conscious like us. If that be true, and you were to take that as just a known, it might shift some of our strategies, right? I see a lot of, you know, I see a lot of scientists with chips on their shoulders about one technique or another, you know, just pissed off that nobody ever believed them and now maybe they're going to be proved right or whatever. That's all fine, but what if you just stopped thinking that way and assumed that it was all going to work, and you had to accommodate that? So thanks for your time. Maybe we could take a couple of questions if we have time. Thanks.
Thank you very much for your talk. I share a lot of your concerns, especially with what you mentioned about fraud, which is already the biggest measurable problem on Earth. Before my question, I want to mention at the first AGI conference, when I was a sophomore in college, I was part of a team that used Second Life to deploy cognitively robust synthetic characters in digital environments, and we looked at building an agent to pass the false belief test. So I'm a sentimental guy to begin with, and I love Second Life. So thank you for that as well. My question, in light of some of your comments about ethics, is this. If it took Einstein 20 watts and some stale donuts and coffee to come up with relativity, is all of this ethical. The fact that big tech is now talking about building nuclear power plants so they can produce 1,000 megawatts, so that, from what I can see, the main use case is college students cheating on tests. Is this ethical in your opinion? Thank you.
Well, I think you're setting me up for a softball there in the sense that if we ask the question, should we build new nuclear power plants to build AIs that are AI boyfriends and girlfriends and scam people for money, I would certainly say the answer is no. That said, though, I would say two things, right? One, technology and LLMs and anything else are generally neutral in their impact. It is our choices that make them either horrifically bad or wonderful for us. So I think the ethical concern is more use. I'm one of those thinkers about AI restrictions that favors the restrictions being based on the choices around use or the implications or results of such use. Like we should not use AI, for example, perhaps to be romantic partners for ourselves. As countries, we should just say no to that. As communities, we should say no to that. So I think that the ethics are encoded in there. And regarding the high power requirements, my suspicion is, yeah, we're probably wasting some environmental energy and maybe harming people's lives, although I understand it's a complex topic. But the power requirements are almost certainly going to come down, as I said at the beginning. So I also think it'll maybe be a little silly that we're talking about gigawatts and stuff a few years from now, that it'll, it seems like an active force that may not be necessary. Thanks.
Hi, thank you very much. And I have a question about angels. So, how do you think we should build those angels? What would be their characteristics, qualities?
Thanks, Anna. So with regard to angels, the suggestion that I've made, or at least one thought point, was blockchains are a distributed architecture that allows, for example, a set of balances to be held constant amongst a large number of computers. They're completely redundant, and so in that sense, they're kind of, blockchain stuff that is kind of still a problem looking, a solution looking for a problem. But there are consensus mechanisms that aren't fully redundant, that essentially, use local pools of compute, but still use consensus amongst multiple machines to give answers. I've written a lot in that paper and have thought, and thinking a lot now and at CIMC about whether and how one might be able to build an environment where the environment is simulated by consensus, that is, multiple machines have to agree on what the next step in the evolution of some system is, such that no one person could violate those physical laws, if you will, and cause some time evolution which was incorrect. If that type of a physics, that type of consensus physics, could be used to represent both the minds of the machines as well as the environment, we might then have a situation where you kind of could set up a large number of computers that created a safe environment for AIs to live in. Everybody could certainly turn that whole environment off if something was going terribly wrong, but if it was generally agreed that it was working, the AIs that were in there would be essentially run by consensus, and so they wouldn't be threatenable or harmable by an individual person. That is but one architecture, but thank you for bringing that up. Have we got time, or should we wrap?
We have one more.
One more. Hey,
Great.
Lucky day. Buy a lottery
Philip,
ticket.
great to see you again. My question is, for Second Life, what are you seeing now, and what do you see in the future? You're mentioning this fraud, and I'm assuming that the avatars can pass the Turing test for the other avatars on the platform. So how do you address it now, and what are your thoughts about the future?
It's a great longer conversation. Come and catch me for more on that. But I think that identity and digital identity, and identity being a property of groups, which, by the way, goes back to that small parts loosely joined idea. I think that for things like Second Life, to not have avatars that are masquerading as people but are in fact, nefarious AIs or something, we have to advance the identity problem amongst the users of Second Life, and I think that identity problem applies to the whole internet. And so I think maybe a happy outcome of having all kinds of fraud is that we're going to get forced to look at identity correctly. Now, of course, there's that kind of WorldCoin risk that maybe we're going to go full horror show and have, a bunch of retinal scans on somebody's computer that can be used to control society. But the idea of establishing some sort of a mechanism for distributed identity that is inclusive, perhaps, of both AIs and humans is something that we've got to do right now. And I hope that systems like Second Life, kind of help force that happening. Thank you very much.
Thank you very much, Philip.
Thanks, everyone.
These are very important questions, very important points, and I'm so glad that you could be here today. I hope that everybody's appreciating the wealth and diversity of experts, expertise, perspectives coming together in this conference, coming together just today, looking at this from all sides. These are questions that it's so important for all of us to look at. And now we'll have a panel session to bring together an even larger diversity on these questions. And I'm so excited to introduce the moderator, Gerrit de Vink, a tech reporter at the Washington Post since 2021, covering artificial intelligence and its rapidly growing impact on society. Thank you very much. We're thrilled to have you here today.
Is this working? Cool, thanks. Should we go a little faster just to make up some time, or why don't you just, okay, all right. I'm gonna let the panelists come up, keep moving, and we're gonna do kind of quick intros. They're gonna introduce themselves, and that will allow us to get onto the good stuff really quickly. So yeah, sorry guys, a little awkward, but everyone just come up and then we'll start what we discussed earlier. And there's Jem, okay. Oh yeah, you can line up with your photos if you want, although.
Almost, we got the wrong Greg.
We have a different Greg.
A wrong Greg up on the slide.
Okay, Catherine, why don't you start us off just with a minute or two, introduce yourself and where you're coming to this conference from.
Sure. So thanks for having me here. My name is Catherine McMillan, and I'm the Chief Operating Officer for the AI Collective. We're a global AI community of over 200 chapters in 50 countries and have amassed over 250,000 members since launching in 2023. And I'm coming here today from Washington, D.C., where the conversations about artificial intelligence and its diffusion into society is very, very different. So I'm very, very happy to be here today.
Go ahead, Reza.
Hi, look, you've heard from me already, so I just want to say that the important thing is that we need to understand the clear and present danger of the massive wealth transfer that's going on right as we're using AI. And I run an organization called Quiet, and we're working to resist that, to create the Linux of AI, safer, faster, and greener. Thanks.
You've seen me from before yesterday, so I don't really need much of an introduction. I will say that in connection to this discussion of decentralization, one thing that Firefly is true of Firefly, but that we de-emphasize, is that it is the world's most scalable blockchain, and we have the measures for that. But we don't stand up and maintain an ongoing network. We let our clients do that. So we're actually building a decentralization infrastructure in support of decentralized AI, such as ASI Chain, which is being rolled out by Ben's organization.
Hello, everyone. My name is Ozan. I'm an electrical engineer and a computer scientist, but I don't think I could hold a candle to 5% of this room. There's so much intellect and knowledge. I'm humbled to be here. I've been building systems. I like solving problems that are complex and intricate. I did this for the government of Canada, especially during COVID, when a lot of data systems were exasperated and things were really out of the ordinary. Once the crisis was over, I looked for a new challenge. And at that point in time, a lot of zero-knowledge blockchains were coming out. I'm a big fan of peer-to-peer infrastructure. I've used a lot of LimeWire in my day, and I haven't pirated anything, but at least not on record. So I believe in decentralization of infrastructure. And most importantly, in the age of AI, when we're very keen on sharing data with hyper-intelligent systems, we just need to be a little bit more careful about some of the mechanisms that are involved. So with Nexifuse Health and Midnight, most importantly, the zero-knowledge blockchain, we're building some of these systems and implementing them in various different countries of the world.
Cool. Well, so yeah, so my name's Gerrit. I write about AI for the Washington Post, so I write for a very broad audience. And I think you know, decentralization can probably mean a lot of different things to different people, probably means a certain set of things, you know, especially when it comes to infrastructure, technical solutions to people in this room. Obviously outside of the room, it might be, you know, I get to control what happens with my data or my AI instead of, you know, one big tech corporation that I don't trust controlling it. I think for everyone though, it's sort of like we're at this, everyone agrees we're kind of at this incredibly important moment in technology, and things are happening, things are going to happen, and all of our lives are going to be affected. And clearly just listening to people speak this week, you know, there's this desire for things to be democratized, decentralized, for individuals, for people from maybe even from countries that don't have, you know, big AI labs that are leading the way, to be able to have a say in what happens with this technology and how it impacts them. And the kind of things I'm writing about are sort of, you know, about, you know, the labs sort of, you know, pushing for certain regulation, other companies coming in and saying, no, we don't want this. Obviously, the last week, it's been very focused on, you know, Chinese open weight models and that kind of thing. And so I think the first question I want to put to you guys is just when you look at sort of the current market structure, the current power structures, the current people who are maybe calling the shots in terms of the development of AI broadly, are you, like, how do we get to a point where it is, you know, the little people who actually do have a say in how this technology impacts their lives? Are you pessimistic about that? Do you see potential paths for that? And so, yeah, I mean, I don't know, Catherine, if you want to start us off. You speak to a lot of people through your organization, so interested to hear what you have to say.
I have a lot of thoughts on this. One of the great things about being a community is you hear and hold a lot of space for a diverse range of experience and backgrounds. But I have to say, like, the conversation, at least in the last couple of weeks, has been pretty interesting. You know, pacing the frontier, the open letter that was written in the past week, and the response that people have had to the open source versus closed model debate. But I think these things are relatively obscure to, like, the everyday person, like your grandmother, your school teacher. Those people are not having necessarily these types of conversations. For them, the diffusion of AI would be, how is this going to impact my livelihood? How is this going to impact my work? So that kind of cascade of how the consolidation of power with one or two frontier labs that want the whole world to use their AI, how does that create real impact for real people? But then on the other side, the people who are on more of the frontier of AI, there's this very vibrant discourse about, you know, what are the values and the guardrails that we're going to create to these systems, even if they are open. So it's a huge discourse.
So Garrett, you asked about the current power structures. The US economy has never been this monopolized since 100 years ago, the 1920s. And we all know what happened at the end of the 1920s. We've got AI now controlled by 6 oligarchs, and they don't have our best interest at heart. So we've got to urgently focus our energies on an altruistic intervention to reverse that trend. And if we don't, we're going to slide down that slope that Yanis Varoufakis and Rafik Krikorian talked about, right towards techno-feudalism. And we've got the brain power in this room and in other communities. The beauty of the non-profit is we can play the long game. I've worked in many for-profit startups, and you're always obsessing about quarterly numbers and driving short-term gains. And so this is what we urgently need to do at this time, and reverse this trend of monopolization.
Either of you want to jump in? Yeah, go ahead, Greg.
Thank you. I really enjoyed both of these responses. I'm going to give a sort of contrarian view a little bit, but I think it actually is not in opposition, but complements what you're saying. So first of all, I just want to point out that if you think about technologies that have taken off, they've taken off because people use them. because people find them actually compelling, right? Let's go back to the Google I'm feeling lucky page, right? That was a great marketing effort because it demonstrated immediately to people, oh, searching the web is useful. I can actually get stuff done doing that, right? For those developers in the room, you may remember that JavaScript came to popularity because it was the only way to program the browser until it became the only way to program the browser, which is cost the industry hundreds of millions of dollars. Likewise, people use ChatGPT and Claude because they find it actually helps them. My 80-year-old mother uses ChatGPT all the time. I just went for a walk with a friend of mine down in Palo Alto. She's an English teacher at a high-end girls' school, and inside the classroom, it's blue books only. They're shut down. They can't use ChatGPT. But then, after going on this diatribe about AI, she turns around and says, "And look at this calendar I made." with ChatGPT and Dolly, right? So people use it. And so one of the ways, like I agree that there needs to be legislation and top-down stuff, but there also has to be bottom-up stuff. We have to build alternatives that people actually want to use. We have to provide utility. And if we do that, then we have a chance of flipping the script, so to speak.
Wow, tough acts to follow. What could I say that they haven't touched upon? I really liked Alison's point about the stone soup, the ancient story on how the soup that's made eventually is really a contribution of all the people that came after the initial stone was put in the water. I think my biggest concern with some of the systems that exist today is that we've become the product. The things that make us special, the art that we create, the conversations that we have, it's becoming commoditized, and they're learning from it, and the product is getting better as a result of it. So it's almost like these algorithms are functional, but they're taking more from us than perhaps they are giving back. So, further to Greg's point, I think we need to find a utility that is centered around the user, and I think that's why privacy is really, really interesting. Reza didn't get to talk about homomorphic encryption, but I think we're going to be seeing a lot more of these foundational architectures and infrastructure that allow for use of these tools in a way that feels useful to us, but is private. All of these conversations that we're having with AI about our health and our personal problems could potentially be mined from us. I think that's my biggest concern with that oligarchy that we're talking about. That they could know the intricacies and the complexities and the uniqueness of who I am, and once that's taken from me, I'm just a number.
A few of you are starting to mention potential infrastructures here, and I think if you look at mobile, for example, there have been, you can buy a phone where you can kind of mess with the OS yourself, and you don't have to send everything to Apple, but for 95% of consumers, they're okay with that. They've made some kind of deal with the devil in their head that they're like, yeah, we know big tech takes all the data, but maybe there's nothing I can do, and it's the most convenient thing for me, and they just sort of move forward and try not to think about it too much. And you see these kind of concerns coming up from people. Is there a path where we could have infrastructure that goes around some of these centralized control organizations, companies, that actually is not too technical, the barrier to entry is not too high, that yeah, your 80-year-old grandmother could somehow wrap her head around and use on a daily basis? I don't know, Greg, if you want to start with that.
Thank you for that. But one of the sales pitches that we give to about Firefly is exactly in line with what you just said, right? The deal with the devil that Grandma makes is she's willing to put her healthcare data up on a healthcare portal because she doesn't want to have a basement full of servers. and she is not in a position to actually manage that basement full of servers. So one thing that you could do, imagine if you had the security of the Byzantine fault-tolerant networks, like Bitcoin or Ethereum or Solana or whatever, but you had the scale of the crash fault-tolerant networks, like AWS or Google Cloud or whatever. Those networks, by the way, are clearly not secure, right? We've seen hundreds of world-changing hacks. So Firefly delivers that, and what it allows us to do is to thread that needle. So grandma doesn't have to have a basement full of servers. They can be scattered throughout the internet. They don't have to be behind the firewall of a company. And yet, what grandma uses to share her healthcare data or to access other kinds of data are private keys. And that kind of infrastructure, if you do it correctly, can be quantum safe, future-proof. So that's one way to address that.
Anyone else want to jump in there?
So Jem mentioned the term homomorphic encryption. It's one thing to have your data securely stored in a vault in the cloud, but what you need is to have it storable there and still searchable in its encrypted form. And that technology is not readily available now. The industry's been searching for homomorphic encryption, and they haven't found the solution for the fully homomorphic encryption, where you can have your data in a trusted server, encrypted, and do math on it in its encrypted state. And what we have found at Inquire is partial homomorphic encryption, where you can have a vector database, which is the way we store our information semantically, and have it still searchable in a scrambled state. And that I think is going to be a stepping stone to us retaining our ownership of our own knowledge.
What a beautiful segue, gentlemen. I think healthcare data is what I've devoted at least the last 10 years of my life to. The last time I was at CES, I was working on a multi-array microphone technology that through machine learning could do sound diagnostics. I thought it would be very useful for preventative maintenance and other stuff like that. But when I met with the head of technology for an OEM, he said, "We just want to know who's watching the TV and how much money they make." I said, this is absolutely not what I want to contribute to. So in setting out to build a system that can have zero-knowledge queryable function on medical records, I founded Nexifuse. It's an ambitious goal. We've done, just like Reza has, ways of achieving partial homomorphic encryption, but what we're really trying to build is a secure way for governments and clinics and hospitals to have their EHR without having to change their legacy systems, but to make it way more secure, way more interoperable, but most importantly, auditable. Because these AI systems can access your data at will whenever they so choose. They might be on a timer, but we want to know why they access that data, when they accessed it, and for what purpose exactly.
If I could just add one more comment here. I guess today will be the day we announce it. Firefly also just established a partnership with a company called Data Crypto. So what Data Crypto does is it goes the opposite from open weight models. They do fully homomorphic encryption on the weights of the models, right? So Firefly makes it possible to do orchestration of agents and orchestration of how agents access data. But we can also take the agents that are, transformer networks and encrypt them using Data Crypto's techniques. So that's another piece of the puzzle.
Catherine, I know with you guys recently did a survey of a lot of, I think it was almost 3,000 people across a whole bunch of countries. And I'm just, when we talk about this sort of decentralization question, like when you look at all the things that people are discussing around AI, people outside of the tech bubble, I mean, is this one of them? Like, is this something that's actually coming up, or is it sort of maybe further down the list of the actual concerns people have when it comes to AI?
Yeah, one disclaimer is that this is not a representative example of the, the world community of people, but, and for context, the survey mentioned here was a part of a campaign called Humans in AI Week, which is a global activation we did where 80 of our chapters hosted 100 events all in the span of 1 week. And one of the survey questions that we asked everybody was, what does it mean to be human in the AI era? And we created like an open field for them to just kind of share whatever was on their mind. So we did a analysis of all of the open field text responses that we got there. And on the side of actually privacy, it was on the lower end of the priority list. Actually on the higher side, about 35% of people cared more about the sense of purpose and sovereignty and autonomy, rather than necessarily like privacy concerns. And after that, it was like livelihood and personal well-being. Most of the people actually that responded to the survey were extremely pragmatic about AI as well. Like they cared about the utility. They're not necessarily thinking like, oh, AI is just going to, wreak havoc on the world, take my job. No, they were very practical about their responses, but still the top topic on the top of their mind was about purpose and a sense of meaning in the work that they do.
Go ahead, yeah.
And I don't think you'd get the answer from the regular consumer. In the age of Windows 95, if you asked a consumer, okay, what is the problem with the operating system? They would have talked about the user experience and so on. They wouldn't have talked about the monopolization and the structural inequality that that really was the big danger for the industry, and the roadblock that Microsoft and IBM and Sun Solaris were setting up for innovation in that space. It took an altruistic intervention like Linux to come in to completely reset the industry, and now the industry is in a healthier place. And it wasn't a free sort of socialist giveaway. Linux actually supports $1 trillion economy of that were built on top of open source software. So I think, yeah, it depends who you ask.
Jem, did you want to say something or no? Only if you want. I'm happy to jump in. I'm not sure if you're looking at me with expectant thing to say, but.
No, well, I mean, I think we've had some very interesting viewpoints. I was wondering if I could make a left turn at Albuquerque here. So, I want to put this into a larger perspective. So, obviously, we're looking at. I mean, to me, large language models are like Bitcoin on steroids in terms of the waste of energy and the generation of heat. And when I think about the issues that we're facing as a species in terms of climate change, I think actually climate change is going to be the first thing that defeats AI. Right, so I think that we might not get to AGI just because the climate events are going to overtake us and take us back 25 years to, I'm sorry, 125 years. So what do I mean by that? Well, we've crossed the threshold where we were going to, well, it might be possible for us to pull back to keep the rise in temperature below 1.6 degrees centigrade, and what that means is that we're guaranteed in the next 25 years or so that the tropical zone around the planet becomes uninhabitable. Well, unfortunately, about 40% of the world's population lives there, so they're going to have to move. And like we had the chance to prevent that, but that's in the rearview mirror now. So because they have to move, there will be conflict, right? So just as a proxy for this, the Syrian refugee crisis caused just like enormous global upheaval. And that was orders of magnitude less people than have to move because of where we are with respect to climate. Now, those conflicts, they will become armed. Now, just like, again, as a proxy for what's going to happen, look at the recent Russian aggression against Ukraine. That caused food insecurity for 1/3 of the world. Now multiply that by a factor of 10. Supply chain, this has, again, I haven't mentioned the floods, the fires, the storms, any of that. I'm just talking about humans interacting with humans, right? The conflicts will decimate the supply chains. And what the humans don't do to themselves, they will, then the floods, the fires, the knocking out of electricity, et cetera, those are the things that are going, and we are on a path where that is now unavoidable.
Then I guess we need some decentralized architecture.
That's exactly right. No, you put your finger on it. So one of the other things that Firefly is doing is we have an architecture for data centers that involves 3 technologies. One, Art Marino has developed a clear photovoltaic. So you can put it in the panes of windows, you can paint wood with it. He's already building houses and greenhouses and other kinds of structures that prove this out. Right? If you were to redo the Burj Khalifa with this technology, you generate about 10 gigawatts annually. Okay, so this is real technology. Then there are best of breed cooling solutions that dramatically reduce the heat dissipated even from traditional computing, let alone what we saw today, right? So there are improvements there. And then you can pick better chipsets. So you can build data centers that are either grid neutral or grid positive. Now, what is a data center really? A data center is really a power junction. So when 10 years ago, the predecessor for Firefly was trying to take on the issues with the power grid and making an adaptable power grid, but we ran into problems with the regulatory stuff. So the regulators just became, the red tape was too thick to get through. So what you do is you hide what you're doing. You build a network of data centers, and what that does is build an alternative power grid. And you put smarts like, I don't know, the world's most scalable blockchain in each of those data centers. And now you have the capacity to intelligently redistribute the power. Right? And that can then respond to the climate events that are going to cause, like the US power grid is hanging by a thread. We are one event away from mass casualties, right? And those events are getting faster, lasting longer, and being more intense. So we have to construct these solutions. They have to have value props immediately so that people start using the solutions, and then we build up the alternative that way. Sorry. I'm off my soapbox.
It's okay. I'm actually banking on us being able to string all of our computers together, incorporate corporations as well, and get off that con that your computer is only good for running a browser that is a window into someone else's computer that you have to rent. So we need to disavow that lie. And there's $1 trillion of untapped, underused compute capacity within residences, within enterprises as well, especially in the post-pandemic world where we got sent home, staff got sent home with their computers. And then still you're renting space in the cloud and you're renting compute in the cloud. I'm not saying don't use the cloud. I think it's useful, but we do have additional ways of distributing the compute load geographically across the grid. And so when the West Coast is peaking in demand, the East Coast's gone to sleep already. And so it's a much better way of using compute rather than requiring you to suck up the power from one zip code for your compute.
Yeah, if I can kind of summarize what I'm hearing, I mean, some of the concerns that the public has with AI, the climate impact, water use, whether there's you know, whether there's sort of real evidence backing up these concerns or not. These are the things that people say. I mean, the autonomy question, the fact that they feel they don't have control over this technology comes up a lot. And so, you know, maybe some decentralized paths may actually, you know, sort of shoot down a lot of those concerns, and people may be a bit more optimistic or happy about AI than they currently are right now. Maybe if I could just, you know, ask this question to each of you before we give the audience a chance to ask their own questions. But, you know, if you sort of position yourself 2 years from now, looking back, what is one thing that you think would have needed to happen for you to say that, you know, the last 2 years have gone well, or for you to sort of have a good feeling about this period of time? I don't know if it's a convoluted way to say this, but over the next 2 years, what is something that you hope happens when it comes to this? Go ahead, Catherine.
Yeah, for me, it's about human alignment. So we talk about aligning systems to our values, but what are our values and can we actually agree upon them? So the human alignment question is something that's very important. And I think one way that I think about aligning people together is sort of thinking of everybody as a vector with magnitude and direction. Are we all pointing to the same direction? If we're not, how do we correct that so that we're all productively moving forward? A lot of these, you know, there's a lot of great ideas out there, but ideas are cheap. Execution is very rare. In order to actually get shit done, you have to bring people together that agree upon a common goal, and you actually have to do stuff about it. So I think that in 2 years' time, if we have people looking beyond just the sensationalist headlines and actually think about what's one small thing that I can do today, regardless of how technical you are or not, so that we can point those vectors in the correct direction towards human flourishing, the betterment of the world, and preventing any sort of existential or catastrophic consequences.
Garrett, if we're looking 2 years from now, the notion of personal AI is going to become ubiquitous. I think we're all going to be armed with our own personal assistant, personal AI, but it's going to be a loyal agent, not a double agent acting really on behalf of some other vendor. So it's going to become a new product category almost. It'll be running locally, and if it does use remote resources, they'll be secured with homomorphic encryption, and you'll be able to leverage the elastic capacity of an entire trusted community. Either it's a swarm of your trusted friends, or it's the digital public infrastructure, or it's a corporate swarm. But these things are going to become ubiquitous, much like mobile phones became a whole new category that we didn't think we needed, 20, 30 years ago. Now everyone's got one. So you're going to have a personal assistant, and AI will become truly uplifting for all of humanity, rather than trying to give corporations the 10x improvement and focus on cost reduction. It's going to be, AI is going to become that positive influence, that positive factor that makes you a better you, and is working on our own personal chores and angst and navigating society. So that's my prediction.
These are, I resonate with all of this, especially the human alignment. As you were speaking, what showed up for me is, I'm so delighted that my children are so much better at so many things than I am. And I really hope that over the next 2 years, the technology that we're developing helps them cross a bunch of cultural divides. Like I find that a lot of the division in the US, for example, really has to do with STEM culture versus non-STEM. Either you're STEM literate or you're not, right? And I really hope that we can dissolve that divide. And I would love to, in the next 2 years, begin to see that division in particular begin to erode, because those are the folks who are going to have to help us get out of the situation we're in.
Wow. A lot of fantastic things that you guys just highlighted. I don't want to go into blockchain and crypto too much. I think we've all heard enough about all of that. I think the thing that excited me the most about it was infrastructure that wasn't centralized. So if I could have my own private keys, or in a way I could attest to information and it was me doing that, that gave me some agency. And in some way, I think that is what I classify as patient dignity in the context of medical records. It's a right to privacy, and it's a right to interoperability, and it's a right to these frameworks that allow for betterment of our collective lives. In the case of blockchain, if any of you have sent a transaction, it's extremely complicated, and it's actually very scary. You don't know if you're sending it on the right chain. You don't know if you signed it correctly. If you have a hot wallet, meaning if your private keys are on a digital device, they might have been compromised. And it's just a terrible feeling that I think will prevent from real adoption to occur. One of the fascinating things that's come out recently is something called the Open Wallet Standard. It is a consortium of companies that have come together and said, if an agent is to have a wallet of the Web3 kind, then it should work in such and such fashion. And in OWS, Open Wallet Standard, you can provide, as the owner of an agent, some restrictions, kind of like parental controls on Netflix or YouTube, which doesn't work because there's crazy content on YouTube that gets flagged as kids' content. But in the case of medical records, a lot of this would be automated. So we're using AI because it speeds up our lives. I would go as far as to say that I love AI because I'm lazy. I don't want to write lines and lines of code anymore. So we are using AI to do less intensive work. And if the AI is going to be doing that intensive work for us, then what we need to ensure that this technology is used in the right way is to give it these core primitives, the guardrails, the systems, the encryptions. Just like Reza said, I think local computation is really, really important. I urge everyone to download a model that's, everyone here probably has a model on their computer, but anyone that's watching to experiment with local models. And if you need to use remote resources, something that we focus a lot on is trusted execution environments. So starting from the chipset, going all the way to the software, you are ensuring from a cryptographic standpoint that nothing has been tampered with, that there is no man in the middle, that the information isn't being injected from somewhere else. And if we can build these guardrails from the ground up, we can relax sooner than later. As Greg said, if the tropics are going to disappear, then we need to enjoy the tropics because that's a very, it's a terrible thing to think about. So I think now is the time, before we have AGI, before there is something that's stronger than us and more capable than us, we need to put in these guardrails, like these hard-wired switches that could protect us because we're quite fragile.
Do we have anyone in the audience who wants to jump in, ask a question? I think the mics are here and there, right up front here.
Hello, great conversation. There was a lot of talk about decentralization. I think that's very important. My only question is, isn't the ecosystem already very decentralized? I mean, the models are commodity, if we include the Chinese, Kimi and the open stuff, everything just a click away for a developer. AI agents are open source. Hackers, people with like an investigative mind run them locally on their computers, and they're actually dominating the ecosystem rather than the big labs. So the question is there really need for additional decentralization?
Can I take this one? Okay. I'm sure you guys have fantastic things to add as well. So decentralization inherently means that you're shifting the trust away from a centralized institution. This could be AWS, it could be Google. All of us in here are probably trusting Google with a lot of stuff, which we could probably take a step back and reconsider. In the case of IP, I think you want collaboration, you want sharing of ideas. So decentralization doesn't necessarily mean that things aren't open source enough or that things are not accessible enough. In a way, it's also for preparing for catastrophes in case one really important point gets hacked or demolished. In the case of South Korea, a major data bank got burnt up, and that was a big part of their national backup system. So decentralization is also redundancy. Decentralization is trustless consensus mechanisms. So I'm saying don't put the trust in me. Here is a smart contract, or here is something that we can all agree is cryptographically sound. Anyone can audit it, anyone can interact with it, but the responsibility is not on me anymore. And I think that's what decentralization is. It's a trust network that we can all tap into, much like peer-reviewed science is.
Yeah, it's the industry and the economy relying unwittingly on single points of failure that only expose themselves when the failure actually happens. CrowdStrike took out a large number of businesses for about a day and a half, and then its effects took maybe a week to fix. And that was a single point of failure that unwittingly ended up in our supply chain. Wittingly or unwittingly, but we need to we need to have this ethos of decentralization rather than the the attitude. Well, no one got fired for choosing IBM. That was a kind of a maxim for the IT buyer. And what you do is you end up unwittingly having these single points of failure just permeating like a cancer through through our industry and through our society. So that's just one snapshot. Catherine, what do you think?
Well, I mean, to your initial points, Catherine, I'm not sure that grandma or the large percentage of people in the world are using Kimi or Quinn or anything like that. If they're using AI, they're going to OpenAI or they're going to Anthropic, and maybe they'll use Gemini occasionally, right? So I don't think the ecosystem and the market is all that decentralized, frankly.
Hi, thanks. I have a question regarding this exactly topic. I have experience building layer one. I won't name which one. And I've been in crypto for a very long time. And the self-critical we have as an industry is that the whole thing didn't work. The whole experiment actually, in a way, failed. You talk about decentralization about Bitcoin, if you really think about it, there are probably a handful number of mining pool that control the whole network. You think about the distribution of Ethereum, it's similar situation. And if you think about how the majority of liquidity actually are concentrated in several exchanges, and also think about the self-custodian as option is really good. But the truth is, I've seen all the people in the industry who are super experienced still get hit by various of way to actually do self-custody. The sort of sovereignty you gain actually is something you lose. Like for example, if you have your wallet get hacked, then there's no way you can get it back. So personally, I am a victim of FTX collapse. So in a way, it's not everything, but I get something back because there's a society behind that whole system trying to make it right. So in a way, sort of similar to the previous question, and in a way, we are already decentralized. So what are the new value we're trying to figure out? I have my own answer, but I really want to hear you guys, how you guys think.
So can I summarize the question? I think it's a repeat to saying, in a way, we're decentralized. I'll take you back to the era of Windows 95. Hey, we've all got personal computers. We're all decentralized. No, you were relying on a single company providing your operating system that was basically a single point of failure, and the defects in it you have to wait till. So look, I don't think we are decentralized. Decentralization is more than just us all having our own computers. It is it's a trust fabric where we maintain our own trust and our identity, self-sovereign identity. Trust propagates through the network via reputation. We are able to use our own compute resources, our own data. We're custodians of our own data rather than creating hacker honeypots in somebody else's platform where there just needs to be one hack and 1 million customers' data is exposed. So it's a mindset change. The whole reason I talked about in my keynote was about knowledge and figuring out how to extract knowledge from language is because that's our essential value. That's our capital asset that we need to obsess about. Our value is in our knowledge, our intellectual property. Regard that as the thing that you should obsess about and hold private, and then choose whether you are going to share it with others, and do that either freely or for cost. And we can all participate in a knowledge economy, knowledge services, and I think that is the path B to this different benevolent or beneficial general intelligence.
If I could jump in just very briefly, I agree with you. Bitcoin is not decentralized. In fact, fundamentally, proof of work is not decentralized. Why? Because it keeps the record all the way back to the Genesis block. So to sync, like imagine if you ran the entire economy of California on Bitcoin. How large would the data set be? It would be many orders of magnitude larger than it currently is. So only governments and multinational corporations would have the compute power to sync with the network, right? So over time, proof of work becomes centralized. It's just a fact of the protocol. So I agree with you. There are alternatives, right? I can't go into it very much, but because we don't have enough time. There's 50 seconds left, right? So, but if you shard the thing, if you think about what goes on inside Google, for example, the Gmail servers are not running Google Maps. The YouTube servers are not running Gmail, et cetera, et cetera. The networks have to be sharded in order to be responsive. But then you interconnect those networks. So a sharded solution begins to be practical enough to realize real decentralization.
Yeah, we don't have time, but the liquidity obviously is a different consideration entirely. You know, financial motivation versus information-based motivation and systems. I'm happy to talk about that. I think you touched upon some really great subjects. I've been scammed as well, probably numerous times. I think those that are really passionate about blockchain have probably been bit by it a number of times.
I do just have one comment. I think both questions sort of make a general assumption of who is in this decentralized network. Do you have access to the internet? Do you have access to compute? Do you have access to the resources to be able to use the frontier models or the API call costs or whatever? If you're not considering those other people, is it truly decentralized enough to be able to incorporate all those other perspectives?
Spot on, yeah.
Great, that's a great way to end it. Thank you all very much for participating, and yeah, I'm sure you'll be around for more discussions, but yeah. And thank you all for listening.
Thank you.
Thank you, Garrett. Thank you, everybody, for joining us. And as Catherine said, we need people doing shit to get to the next level, get to the next step. Again, this August Hyper Sprint is a great opportunity. Definitely encourage everybody to attend, to build, and do things with us. But then also, Catherine, in our partner organization, the AI Collective, it's a global group that is bringing great people together to talk about AI and understand the landscape. And we're very excited to partner with them for this day and for this event, and definitely encourage everybody to check them out. So to follow on this, we're going to have a conversation that resonates perfectly, a conversation about who builds this and how does it get built and distributed. To moderate that discussion, I welcome Julian Issa back to the stage. Thank you very much, Julian.
Hello, how's everyone doing? 4 p.m., fourth day. How are we feeling? I'm in the longevity space, and usually at this point I get everyone to stand up and get some blood flowing in their legs. So maybe everyone can just stand up, and maybe just like do a bit of jumping, and if you want to do a few squats to get some blood going, so we can all live through the singularity. Don't want anyone falling dead for that. Love that, okay. And maybe just let out a woo, woo, yeah, love the energy. So, this morning was all about what intelligence is. This afternoon, we've asked the question of what does it mean for society, and now we're going to be asking the question of how we build towards AGI inside a company, and all the lovely vested interest around that as well. BGI Labs is a live case studying that right now, or a study in trying to do that all at once. And of course, we've got Ben, who you might know, Ben Goertzel, who's going to be joining us on stage, as well as Daniel McDonald from the BGI Labs. He's part of the core engineering and research team and brings a lot of real-world experience with that. And then we have Kai Zanbickel, who is the Chief Ethics Officer at BGI Labs, a multiple ethics award recipient, including the Voice of the Voiceless Award from Child USA and the Social Justice Award from the University of Toledo. Do we have everyone ready to come up? Okay, we've got Kai and Daniel. Big round of applause for them. I've got a, okay. And so we're going to do a bit of riffing before that. But I'm going to ask Daniel a question before Ben arrives. So Daniel, maybe you can give us a little overview of BGI Labs, what you're trying to do, and then also the biggest gap between what works in your lab and then what works when you take that into the real world.
Well, I'll be honest, I don't actually know yet. This has, been ideated a bit apart from the research, and I'm sort of, had my head down doing, trying to build the technology that I want BGI Labs to actually bring out in the world. But my understanding is that the intent is sort of to try to build what OpenAI should have been, and actually have a proper system or an alignment between a for-profit venture and something that can actually house and maintain the openness and decentralized aspects of the core technology. So I've long believed, and I'm not alone in sharing that belief, that AGI must be open source and decentralized, and that allowing any one entity or actor or ideology or company to own it and control it is probably the easiest way to get a bad failure mode. So my understanding is that we're going to build a structure that allows both capital to come in and allow people to actually build things that go out in the world and function, while also maintaining the core, the sovereignty of the technology itself.
So it becomes a company, right?
Well, I think Ben could probably say more about the vision behind the structure here, and so I'll let him take that one.
Yeah, I'd love just to dive deep on that, because decentralized and open, but if you're going to make it a corporation, then what do you give up?
So with BGI Labs, the structure that we're looking at forming, I mean, we're building the company to build products on top of an open AGI core, right? So, I mean, we have open weights models are now all over the news, and amusingly, every big company, essentially except for Anthropic, has come out in favor of open weights models. But open weights, of course, is just the first step, right? I mean, the source code, the training data have not been opened up, and I think you want all that to be open, and you also want to be running on a decentralized, sort of collectively owned infrastructure as well, and you want collective participation in supplying data where people are opting into providing their data to teach the AI models. And all that is the foundation. Like that's the AGI core. That should be owned by the whole human species and then the new species that we create. On the other hand, how to package up and focus that core AGI functionality to meet the needs of a particular vertical market, I mean, that's a separate layer. And that layer may or may not be open and decentralized, depending on what the vertical market is, right? So take cybersecurity as one example. And I worked a bunch on cybersecurity in previous decades when I was in Washington working with government agencies, like advising on how to secure their networks. So you could build on top of this open infrastructure, you can build, say, a cybersecurity Omega Claw agent hive, right? So you've got like a red team orchestrated by one Omega Claw, blue team orchestrated by another Omega Claw. So one is doing penetration testing, the other is doing remediation. You can have a purple team agent conciliating between them. They're all putting knowledge into some admin space, which is a sort of logical, rational model of the computer network. Now, all of this stuff, some of it can be open, some of it won't be open, but even if that's open, I mean, an enterprise wanting to secure their infrastructure, I mean, they often want to have a company that is in charge of that because it's critical operations, right? So they want to license a real packaged commercial product, unleash it in their network, and have it secure their network. And the fact that it's based on an open infrastructure is a feature, not a bug, because it means there's going to be fewer bugs in that infrastructure, right? So that's one vertical market. There's a whole bunch of others. I mean, you could see in finance is another vertical market, which is interesting because, I mean, if your customers are fintech firms, you're building atom spaces and you're training networks that are based to a large measure on proprietary data, right? Because that's a lot of what Wall Street is operating on. But still, the core AGI algorithms are open. Now, depending on what the application is, the whole logic can be different. Look in governance, which Eagleman talked about this morning. I mean, there you want the whole stack to be totally open, right? Because it's about AI helping people to govern their own society, and it's very perverse if there's a proprietary element in there being used to govern society. There the application layer is open, hopefully funded by governments that want to improve their governance with AGI assistance, but the whole thing should be open and collective. So I think the idea that commercial profit motive is compatible with an open core is not very new, right? I mean, you've got Linux and Red Hat, and then there's loads of well-worn examples there, and it's gratifying to me to see how the whole open weights models things, while very limited in its openness, like that still is it's driving the point home, right? And I think by having an open core, you can also just race way ahead in terms of creativity and capability. Like no big company, no matter how much money they have or how visionary the management is, like none of them matches the breadth of vision and creativity of like every university in the world and every independent developer in the world, in terms of values as well. I mean, no matter how well-meaning a given company is, and most of them are not very, but I mean, no matter how well-meaning they are, they're not going to have the depth of understanding of what is wise, what is good, what is it to be human that, you know, the whole of humanity has, right? So there's a lot to be said for that open core.
Definitely, and I know it's 4 p.m. right now, so I do want to invite you into the living room so we can all have an open chat here. So if at any point during the next 40 minutes anyone wants to ask a question, just raise your hand and we'll get a mic to you as well. Kai, from an ethics perspective, what is BGI Labs doing differently?
Well, let's see if this on. Yeah, so the idea on the ethics side, and I think I'm going to bring it back to where this started. I met Dr. Goertzel in 2016. We were both speakers at something called the Global Leaders Forum in Korea. And I was taken back by his ability to be this approachable figure. And I came back to him when ChatGPT hit because I was concerned. And I think a lot of people have concerns about what the future can look like. When you imagine something that's self-improving, recursively self-improving, exponentially outpacing us, we can't control it. There's robots being built everywhere, and you imagine the future, you can start to get pretty freaked out. And I was telling Ben, I'm really freaked out about this, and I want to talk about it, and I don't know what to do. And he said, hey, first of all, I want to give you a microphone, and I'm going to let you start, I want to empower you to start talking about this conversation and engaging it. And I think fundamentally, where BGI Labs is different is that we want to invite all of these different perspectives to the table. Essentially my role as somebody who received the Voiceless Award and that kind of thing, I'm not here to try to act like I'm this big scientist that's going to try to figure it all out for everybody. Of course not. We want to have a layer of integrity and a platform of participation, because the all-stars here are the scientists. This room is filled with fantastic scientists who have been thinking about these things deeply. So we want to bring in the conversation. We want to hear all sides of the table, consider it all, and develop the most robust, let's call it a moral constitution, and also give it our best shot collectively, invite humanity to get involved in this, and really understand that humanity is actually at stake. This could go wrong. It could go really, really well. We want to do every single thing that we can to utilize the tools that we have and the minds out there that are available so that we can collectively come together to give this our best shot at having it go well for everyone.
In the podcast we did recently, which did pretty well, Kai, you described yourself as a 51% pump the brakes and 49% this could be the best thing ever. And Ben, you quoted Ram Dass, relax, nothing is under control. So how does this relax, nothing is under control sort of manifesto kind of evolve?
This was a quote from our Ram Dass, I think.
Yeah,
actually.
Ram Dass, exactly.
And my good friend Leslie Allen Combs delivered that quote on stage at a BGI Beneficial General Intelligence Conference we had in Panama a couple years ago. And I knew him since my early 20s, and he was a psychologist working on the psychology of spiritual, enlightened, blissful states of consciousness, right? And yeah, he said it much better than us. He's like a very large, weighty 80-year-old guy. It's like, relax, nothing is under control, right? And I mean, if you're sort of anarchist-oriented, that is reassuring, because some guy under control, that guy is usually causing a problem, right? So I think what it means to me is the world is self-organizing as living systems and ecosystems will do, right? And I think the process that's happening now on the planet where AI is being created and AI is becoming more and more capable and AI is transforming humanity and transforming the information processing across the planet. I mean, this process, in a sense, is too big for any of our control mechanisms to usefully capture. I mean, it is, if you get cosmic, like it's another step in the evolution of complexity in the universe, right? You've got the Big Bang crystallizing into particles, like crystallizing into matter and stars and planets and early life, and then plants and animals and culture, and these things keep complexifying and keep self-organizing, and we are part of that, and it's kind of vain and insane to me to think like you're going to take control of a process that big and self-organizing and like force it to do the exact thing that happens to be in your head at that moment. Like there is I mean, Kai likes to quote Jurassic Park, like nature will find a way in a somewhat different context perhaps, but you could say, yes, the evolution of complexity will find a way. Now that doesn't mean it can't be nudged or guided or we can't have any influence, right? But I mean, to think we're going to apply like a command and control paradigm to these evolutionary processes that we're swept up in seems like not the right way to be thinking about it.
Yeah, and if I could just touch on that, I don't think anyone here thinks that we're going to be able to control AI as we rapidly accelerate towards a recursively self-improving model. In fact, you could read the news and see that OpenAI recently had a model that they had to, it was escaping the sandbox, so to speak, and it's just a matter of time before these systems break loose. So what we do have a say in right now is, according to the scientists, and by the way, I'm not 51% anymore. I think I'm a little bit more.
52?
Because I'll be honest, I was 51% doomer, okay? I was pretty freaked out about this whole thing. As I've had the chance to interview scientist after scientist, I do feel a lot more positive about the whole outlook.
Well, that's interesting. And so what aspects of talking to various scientists made you feel more positive?
Well, I had a good conversation with Dr. Stock, who's very pro as far as how he sees it playing out with the intelligence. But also, I mean, I just had one about evidence-based engineering and some of these different simulations and ways that we can structure this in a scientific way to try to have the best shot at a great outcome, which, and also what you're doing with the Omega Clause stuff, where you're able to have these corrective systems that are, there's a lot of inspiration that's happening, and
So it's the fact that people are working on things other than making LLMs doing random stuff and then trying to imprison them. Like there are other approaches at play, right?
Yeah, and it really is this collection of minds coming together, because you start to see new solutions which give you an inspiration for how the future might unfold.
We have a question over here.
Yeah? Well, put your hands up. Okay, hello.
Hi, good day. My name is Michael Miller. I'm with subthought.ai. And my question is, in the 1980s and 90s, we bought software. You'd buy a CD and you'd have your software. Then Bill Gates came up with the idea that everything needed to be subscription. And now with the tokenocracy or tokenate, everything is pretty much a utility. Does this utility-based for-profit AI companies, the big six, how do you see AGI coming about? And will the nonprofit AGI still be token-based, or will it be free?
I mean, I see AGI ultimately is obsoleting the money economy and ushering an era of abundance. But until that happens, I mean, you need to pay electricity for the servers, and I mean, people working on AI need to pay their rent also somehow. I mean, having an open source system doesn't mean that money isn't charged for running the system on machines, right? Like Kimi K3 is open source, but I mean, either you pay Moonshot for their API, you pay Open Router for someone else to host their API, or you put it on your own machine and you're paying to host that machine. Then you're not paying per token, literally, you're just paying for the electricity and running the machine, right? So, I mean, we're not exiting the money economy by having an open source system. We may exit it by having a superhuman AGI, but you do introduce a lot more flexibility in what is the economic underpinning, right? Like you can self-host, which has a whole different economics associated with it. You can buy a machine and run it in your living room. Right?
Can I just quickly, just before going to you, Daniel, who here believes that non-profits and for-profits in this space will be collaborative? Just a raise of hands. And who here doesn't think that? Okay.
Okay, come on.
Okay, I'm going to say 50-50. Daniel, over to you.
To that point and Mike's question, so what's really interesting and sort of, of course, as I watched LLMs and Frontier Labs sort of start to take over the world, I was like, oh no, we're going to be digital service. But it's really nice to see that in enterprise already there's a direct realization and an active call for, hey, we need intelligence sovereignty. We need to control our data. We need to control our compute. We need to control where our queries go. We can't let our business intelligence leak out. At the consumer scale, like, we all have individual levels of this. Some of us are okay with giving all of our life to Google and Sam Altman and Dario, and some of us are not, and that's fine. But there are many, many, many businesses and enterprises where they just can't. It's either for business reasons or for regulatory reasons. And so I actually think that even if we haven't figured out the model totally yet, or maybe I haven't figured out the model totally yet, the economic incentives align around exactly what we're trying to do, just in the macro economy. Like, people must do this, and so, but they also have to run it, so they also have to get the servers and install it and know how to set it up. So there's a whole bunch of you know, adjacents and verticals around the core technology that you know, someone's got to do it, and not everyone wants to become experts in engineering the infrastructure to maintain the AGIs that run their business. So I think that's where the value ultimately flows. And so, yes, it will be a utility model for a while, but it's not the utility model that locks you in and steals the part that you care about. It's the part that does the things that you don't care about.
Yeah, so you make several good points. One of them is most companies don't want all their data sitting inside OpenAI or Anthropic or Google's AI brain. And they also don't want to risk the agents running their business being randomly throttled by some change in policy. And then their agents can't do what they want anymore because some random filter thinks it's unsafe. The point I would add is countries feel that way also, right? Like, most countries in the world do not want to outsource the operation of their industry or government to a foreign company, right? And that they would rather host models themselves and figure it out themselves. And China is now trying hard to win that race by sending JIPU, like GLM, to leaders of every developing country and offering to help them develop sovereign AI, but it's half-assed, right? It's only open weights, and then who upgrades the model, like, who really understands what's going on. So I think both within enterprises that want control over their own data and their own process, and countries that want control over their own data and their own process, there's going to be a big push for things to be open and sovereign, probably a stronger push than among individuals who mostly kind of feel like they care about privacy and sovereignty but aren't willing to do too much about it. Like, companies and countries are willing to do something about it.
Another question from the audience?
Yeah, if we just, I just want to circle back to Omega Claw 1 second, and then we'll go to you. What are the dangers of shipping self-modifying agents? Ben?
Oh, yeah, sure.
Give you the fun one.
Well, I mean, I think we've heard numerous talks this week already about the dangers, and I actually, you know, to my surprise, there were many sort of positive theoretical results that sort of point to the intuition that, you know, self-modification of a self-aware agent, you know, the agent's aware of its own risk that it's going to deviate from whatever its current goals are. So there's maybe some intrinsic notion of stability. In a macro sense, I'm not that concerned about it, because my personal perspective and the reason I'm involved in this is that I think that the ecosystem approach to safety is the only one that sort of makes sense and is at a risk minimum, at least. So just the fact that we have lots of other agents, so that if, you know, one or certain subtype goes wrong, at least there's others that are, you know, at least constructed differently. One of my, you know, favorite sci-fi authors, and probably a popular one in this room, Ian Banks, in his culture novels, kind of has an explicit vignette in one of his novels where you know, there's different minds or different civilizations that have upgraded the AGIs to the limit of physics in the galaxy, but they've taken different approaches. So one of them sort of standardized, and every one of their super intelligences sort of has the same, you know, blueprint and code base. And in the culture, which is obviously his preferred, like, sort of, you know, anarcho-socialist, like, Burning Man in Space Forever utopia, those minds are all allowed to develop in sort of a naturalistic way. They sort of bootstrap their own operating system as they go, and so they're all very diverse. And there's actually, you know, one point in this, in the plot of one of the novels where, you know, this other alien intelligence that was extinct, you know, hacks the one that was standardized, and the other one was sort of less susceptible to that type of hacking. So I kind of think about it in that way, is that yes, RSI is going to get out of control, so the answer is to have more RSI and more diverse RSI.
Yeah, I think that, so the risk, if you want to put it that way, the biggest risk is like some node in the network manages to recursively self-improve very fast, become 1,000,000 times smarter than every other node of the network, and it's a nasty node. And I don't think that's especially likely. If the recursive self-improvement is more collective among a large network of nodes that are all sharing information about how to improve each other, I mean, then there's a lot of eyeballs, both human and AI, on this self-improving network. And we can see the seeds of that happening now, right? Like I've gotten Omega Claw Hive, you know, Mesto has a Claw Hive, John Grove has a Claw Hive. Like now these are acting sort of independently, but within the next couple months, we're going to have different agent hives sort of talking to each other more, collaborating with each other more. And what you see is, you know, each person working on this sort of thing, they're forking the code into their own Omega Claw agents, trying stuff. If something works, you report it, others will fork that code and integrate it. And if recursive self-improvement happens by an extension of that process, where you have a big distributed network of different nodes forking each other's code, upgrading each other a bit, I mean, then you have a sort of crowdsourced AI safety, which is not an absolute guarantee, but that is sort of the way human society does it also, right? Like there's a lot of people, there's a lot of groups of people, and if one guy starts to get both super intelligent and super nasty, there's a bunch of other guys who were pretty similar a moment ago that have spotted it, right?
I would love to, we've got the question over here, but I would also love to hear from Mesto just how that looks like from a practical lens, and how you're operating the hive and how the hives also communicate with one another. But first of all, a question over here.
Yeah, so it looks like common theme from this panel and even previous one is actually decentralization and democratization of AI.
Visualization?
Democratization.
Democratization.
And decentralization, right?
Democratization and centralization.
Yeah, and in this case, you know, it's kind of hard to imagine right now that non-for-profit would be able to not run the model like K3, but would be able to maintain it, update with all the new data and knowledge sources. So essentially, with current LLM deep learning technologies, even Chinese models sometimes rely on Anthropic and OpenAI for distilling the models. So even that kind of cuts some independence from them. So in that sense, I'm not sure if current technologies would allow that full partnership between for-profit and non-for-profit, given the fact that not-for-profit will not have enough resources to repeat this kind of training process from scratch and actually have independent view of the world in that sense.
It's a great question. Who wants to answer that?
I mean, it's ever evolving, right? I mean, indeed, if the bulk of resources are in for-profit and the non-profit sector has very little compute behind it, then yes, the for-profit will be in the lead. So I mean, I think what we need is a groundbreaking breakthrough technology that everyone wants to use coming out of the open and decentralized side of things. And then once you have that, then that doesn't stop nasty people, it doesn't stop for-profit companies from competing, but it means that the open and decentralized vein is a true contender. And that you can see the same thing in the operating system space. Like Linux doesn't have to be everything, right? Linux doesn't have to be the only operating system. It's fine, there's OS X, there's Windows, but Linux is open, decentralized, and widespread enough that its existence transforms the nature of the ecosystem.
So this is a little speculative, but it's inspired by some of my own current work and sort of the model that Ben just described more generally of people, you know, forking these improvements. At a certain point, your AGI system that you want to interoperate with is going to be it's just going to have such a substantial physical footprint. It's not going to be practical to, you know, reboot the whole thing or make a copy and fork it. So there will probably be, you know, an entire layer which is about forking and merging and borrowing changes from other related agents. So you can imagine this whole graph of, you know, little deltas between things and useful things sort of percolating between the graph. But that graph, those are small, relatively small information content updates from, you know, a base model or a set of base models. So I think, you know, that layer will probably have to emerge just to support like you know, the corporate ecosystem infrastructure to keep, you know, just for people to be able to keep up efficiently. So that's potentially one solution for, you know, what your question is.
Just quickly, Message, you have anything to say? Just you've got a mic behind you. And then we're just going to wrap up with final thoughts.
You were asking me how would you see agents communicating with each other, and
it's more about your practical experience, because Ben was just calling out your work with the Omega Claw.
So what practical experience was what particularly?
Just using the agents or developing your own hive.
Developing your own hive it's certainly motivating when you see it advance and, you know, benchmarks, or you see it doing things that other models can't do. And I think with the framework of Omega, how it's a constant loop, it's unlike the current frameworks that are all widespread on GitHub, all these, you know, special frameworks and whatnot. And my experience is that, especially when using the Hyperon technology, and in my use case, what I did was I have my Omega Claw parse research papers and then convert that into meta using like an NLP parser, and then allowing it so you're able to reason over that natural language and to be able to see if it, for example, let's say one research paper says A leads to B, and another research paper says B leads to C. Then it would see these connections from other fields, but not only that, it would be able to, and I've been looking a lot in the ethical side of this too, it would be able to see which goals are motivating for your case and whether they're appropriate. Like, you don't want to create a bioweapon, for example. So there's, it's important to apply these mathematical frameworks like deontic logic, which focus on the ethical side, and see how that transforms the agent in what it does and what it doesn't do. So, yeah.
Amazing. Thank you so much. 18 years old, by the way. Incredible what he's doing. So just to wrap up with some final thoughts from the guys on stage. Kai.
Hello? Okay. You know, I just want to set the stage a little bit and engage the audience and the community that might be watching this. After speaking to all these experts, there are some things that there seems to be a consensus on. One is that the stakes are incredibly high. Humanity is literally at stake. Some people believe that when you create a superintelligence that everything is going to be fantastic. Some people believe, and a lot of people actually believe, that if you're not extraordinarily careful with how you create that superintelligence, that it could go bad. So this is an unprecedented moment in history. What we're asking for is a call to action for all of you to get engaged in this process of looking at the AI safety and ethics conversation to help ensure a safe future for the human species and the planet. There's no greater task. This is the time to do it. We have a small amount of opportunity still before we have things that are out of our hands and we're not going to have much impact on it anymore. So I'm just putting that out there as a reminder of how important this is, how important your work is, and to also let you know that even if we or Ben or anybody disagrees with you, doesn't mean that it's not important to hear from you. And for me, it's important to hear from these AI whistleblower, doomer people, because we need to see if there is something there that we really are missing or whatever it might be. So let's get together. You're all invited. We honor and respect you in the scientific world, and we're going to create a platform where all voices can be heard, considered, and give this our best shot as a civilization, because this race seems to be going whether we like it or not. So let's get together and see if we can give it our best shot at making this the most amazing future ever.
Thank you, Kai. Just a few words, Ben and Daniel, to finish off.
Kai basically said what I was going to say, which is if you're worried about it, fork our code and build your own. But I think I want to remind people that we are already in a very intimate cybernetic relationship with these tools, and so the idea. I find it hilarious when people are actually worried that, oh, AGI is suddenly going to take off. Like, no, it's already accelerating our own consciousness and intelligence evolution, and so we are all already taking off, and we're experiencing it in real time. And we're sort of like the frog in the kettle, in a sense, because I think sometimes we forget that. So I wouldn't say I'm not worried about safety, but I think the answer is just pedal to the metal, honestly.
Ben.
Yeah, so I agree with all these points. I just want to bring things back to what's unique about the moment, practical AGI development. I mean, we've seen what's unique about the moment sort of world historically, like our species is quite possibly within a few years of creating a fundamentally more intelligent form of mind, which will then connect with us, hopefully help uplift us and uplift itself further and further. What's happened in the last couple years in the LLM world and in the last few months in the world of our own Hyperon project is AI tools palpably accelerating the development of AI tools, right? Like Anthropic and OpenAI said this many times, and it was true, not just hype. Like each version of their coding agents helped their development team more rapidly build the next version of their coding agents, right? And now we're just in the last few months seeing that within Hyperon, since Patrick Hammer made the first version of Omega Claw and others chipped in to improve it. I mean, we're seeing using one or more Omega Claw agents to help get your AI software development done. This helps to more rapidly create smarter Omega Claw agents, which make even smarter Omega Claw agents. And this is exactly what you would expect to see if you were in, as Demis was put it, the foothills of the singularity, right? It is the kind of, it's not, we do have some full-on recursive self-improvement in a limited way. Like you can let Claw agents go and just let them observe thinking, improve their own thinking, and just cycle. The primary self-improvement that we have now, as Daniel said, is synergetic. Like the AI is helping humans improve the AI, and humans in some ways are changing and in some ways improving their cognition in this process also. And yes, clearly the end game of this AI development is the removal of humans from the tight loop of AI development and humans taking more of a role of consultant and external advisor. Like if we succeed at what we're doing with Hyperon and predictive coding, it is going to be, Omega Claw version 3 is building Omega Claw version 4, and it's now and then asking us for advice on values and taste, rather than us needing to solve the algorithm problems. And we're sort of, you can see that coming now, and we're in the early stages of getting there. But the amazing thing is, like, look at where we were February versus now, right? Like, only this January or February, coding agents finally became useful to me rather than largely an impediment, right? And now Omega Claw agents have become useful to me in the last couple months. And this is all just, it's like month by month, week by week, things are getting faster, more useful, and qualitatively different. And of course, the pace will speed up, then slow down a little bit, then speed up, then slow down a little bit, which is how natural processes happen. I don't think we're going to get the singularity in 2 months, because months go to weeks, go to days, goes to hours. But could we get human-level AI by 2029, as Ray Kurzweil predicted in The Singularity is Near, published in 2005, the year we wrote the original book on AGI? Could be. Could we beat Kurzweil by a couple years? We could. Could there be an obstacle making it take a couple years longer? I doubt it's going to happen. Could happen. But I mean, you can see palpably what kind of recursive virtuous cycle acceleration processes you would need to get to a singularity, and you can see and feel them happening now. And it is important to get positive values and compassion into that tight loop of recursive, autonomous, and interactive self-improvement. And we're in the middle of doing that, right? Like an upgrade to Omega Claw coming shortly is to decrease the power of the LLM in the motivational system and have high-level motivations inside Hyperon atom space, so that the core loop is like, what procedures do I choose to achieve my goals, including ethical goals in the given context? Then the LLM is pulled into that, right? So like we can see the recursive improvement loops happening. We can see how to plug values and compassion in the center of that recursive loop, and it's code which many people in this room are now developing and forking through each other's code bases. So it's quite an exciting time. I mean, the main problem is finding time to sleep at night with so much shit going on. Right?
Absolutely. Gentlemen, San Francisco, from the foothill of the Singularity, it's been a pleasure. Thank you.
Thank you, Julian. Thank you, Ben. Thank you, Daniel. Thank you, Kai. Two very important panels on this topic. And again, a big conclusion is get involved, build on it, build with us, Hypersprints, AI Collective, so many opportunities to be here, be a part of it, and be learning directly from these thinkers and builders that are here at the AGI conference today. So our next speaker, very excited about, studies something that sounds soft and turns out to be rigorous and strange: what happens when the mind wanders. So we've looked a lot about minds, consciousness and intelligence, now looking directly at mind. Jonathan Schuler is a distinguished professor of psychological and brain sciences at UC Santa Barbara, director for the Center of Mindfulness and Human Potential, and director of the SAGE Center for the Study of Mind. He has over 270 publications, more than 50,000 citations, and has been named a highly cited researcher 6 times. Today he's making the case that mind-wandering, meta-awareness, creativity, consciousness, and openness may matter more than focus. I have found his discovery, his uncovery of the decline effect particularly interesting in the realm of what we think, what we believe, and mind. So Jonathan, please join us on stage today, and help me welcome Jonathan here. Podium right there. Okay.
Thank you.
Toward the back.
Hello, everyone. It's a privilege and a pleasure to be speaking with you today. Today, I want to talk about a quality that I suspect many of you already excel in, so I probably don't need to make the case for its value to you, but I do want to make the case that this is a quality that we really want to see society in general cultivate, and that is openness. And my claim is basically, I think, one that, again, most of you will agree with, which is that AGI, no matter how it manifests itself, is going to be highly disruptive. It's going to be disruptive to jobs, it's going to be disruptive to people's self-identity, and it's going to be disruptive to the way that we think about consciousness and whether or not it has consciousness and what consciousness is and what it means. So coping with this disruption is going to require creativity, it's going to require flexibility, it's going to require open-mindedness, and I argue it's going to require an expanded understanding of consciousness itself. So my theses are 3 today. First, that cultivating openness to experience, I'll explain what that is in a moment, could be an antidote to the disruption of AGI. Secondly, that the way that we do this is to foster it in much the same way that we fostered mindfulness in the past, and that fostering openness could catch on with society in the same way that fostering mindfulness did. And then finally, that science itself needs to instantiate this openness to experience and to be a bit more open-minded about the way that it conceptualizes consciousness. And I'll be describing a couple of different theories that I hope instantiate that more open-minded perspective, and then Amanda Gregory will be following with some additional open-minded reflections. So let's begin with the first thesis, that cultivating openness to experience could be an antidote to the disruption of AGI. So what is exactly openness to experience? Well, psychologists refer to personality as being divided into 5 major ways of thinking about how people differ. And you can remember that with the acronym OCEAN. And the OCEAN stands for openness, conscientiousness, extroversion, agreeableness, and neuroticism. And these are the 5 ways in which people differ. And in general, it would be good for many of us to cultivate the first 3 and to downplay the last one. But let's focus on openness. Openness involves creativity. That's the key aspect. And curiosity, again, it's central core. It also involves being open-minded, interested in art and novelty, and variety and novel experiences. People who go to Burning Man, for example, are likely very high in openness. You probably can be too high in openness. Riding a motorcycle without a helmet, for example, would be open, but maybe a little too open. I won't go through the others, but I encourage you to look up the open OCEAN, and you can take a test online to see where you fall on these dimensions for yourself. So what I now want to tell you about is all the different positive qualities that openness is associated with that I think are key qualities that we will need in order to be able to manage the disruption of AGI. The first is creativity. One of the key aspects of openness to experience is a capacity for creativity. And as AGI arises, people are going to have to be creative in figuring out how to reinvent themselves, how to incorporate AGI into their lives as opposed to just being swept under the rug by it. It's associated with cognitive flexibility, which is the capacity to adapt and shift one's thinking or behavior in response to changing tasks, rules, or environmental demands. Clearly, in the face of AGI, we're going to need to have greater cognitive flexibility. It's associated with upward professional change. People are going to be unemployed as a result of AGI. That's inevitable. And they're going to need to be able to figure out new ways of finding employment. So the capacity for upward professional change is critical. It's associated with metacognitive awareness, which is the capacity to understand and regulate one's own cognitive processes. There's going to be a lot of reflection that takes place as people consider AGI, and they're going to need to have that metacognitive awareness to manifest that reflection. It's associated with intellectual humility, and this is a quality that the world certainly could use more of. I think many of you would agree. We have some people in leadership places at the moment who don't exactly instantiate intellectual humility. This is a recognition of the limits of your knowledge and being open to new ideas and to being wrong, and we have to really recognize the importance of this quality, both in terms of incorporating and responding to AGI, and more generally in terms of getting over the polarization that we currently face in this nation and this world. It's also, and this is really one of the core qualities of it, it's associated with epistemic curiosity, the desire for new knowledge or information that motivates a person to engage in learning and exploration. So this is really a key aspect. And it's associated with concern for the future of humanity, which clearly we're going to need if we're going to deal with all of the challenges that AGI causes us. Now, some of you who are familiar with openness to experience may also appreciate that it's associated with a slightly left-leaning political orientation. However, I think the case can be made that the left has lost its openness, at least the far left, and that cancel culture has really reflected a lack of openness. This view that I can't hear things that I disagree with, that if you express opinions different from mine, you shouldn't be allowed up on stage. That's not open, and yet that has been a predominant view of the far left, at least for a while. So arguably, openness is a quality that needs to be cultivated both in the left and the right, and that I think it's not, well, this may be an exaggeration, but perhaps not, that the future of humanity may depend on cultivating openness to experience. So that's my first thesis, that there is a real need for cultivating openness to experience. My second thesis is that this is possible, and that fostering openness to experience can be done in much the same way that mindfulness took off. We should follow the model of mindfulness. Mindfulness, there was a revolution. No one had even really heard of mindfulness 40 years ago, and now everybody practices, or at least is familiar with mindfulness. Many people have meditation practices. Many people are actively trying to cultivate their capacity for mindfulness, in part because they view it's important for their personal development, and they especially recognize it as being valuable for their health. And so appreciating the personal value of mindfulness and encouraging society to see this as a quality worthy of cultivating, I think is very important. But let's pause for a moment and think, how do you cultivate mindfulness? Well, the way you cultivate mindfulness is by cultivating the state of mindfulness. People naturally have a predisposition. Some are more mindful than others. But even those who lack mindfulness, if they engage in meditation, if they engage in moments of presence, that can increase their mindfulness. And the argument is that's the same thing that can be done for cultivating openness, that by cultivating states of openness, we can cultivate the trait of openness. So again, one of the key aspects is that health angle, right? Recognizing that mindfulness could help reduce anxiety and help you live longer is one of the key ways in which mindfulness really caught on. And as it happens, openness is also associated with longevity. It's also associated with successful aging, and arguably it's what it means to stay young at heart, keeping that childlike wonder. So how can we foster openness? I want to tell you about a number of previous lines of research, some of which I've been involved in, and then a number of new lines of research that we've been conducting. So we did the Plasticity Initiative. This was to foster a mindfulness. It involved a lot of different elements. It was 6 weeks, 5.5 hours a day. Involved meditation, yoga, exercise, and instruction. And we really measured the kitchen sink. We looked at all sorts of different things that this powerful intervention affected, and essentially compared to a weightless control, we found it had major effects on health, on cognitive performance, on a variety of different psychological scales, including reduced mind wandering. This is an area that I've particularly focused on, and on brain connectivity patterns, and I could give a whole other talk on this. But another key thing is that we found that it increased people's openness to experience. Recognizing that they could engage in these novel activities led them to be more open to acquiring new skills and to appreciating the value of openness to experience. Another technique that has been found to enhance openness to experience is psychedelics. Research indicates that people engaging in supervised psychedelic experiences, that has led to enduring changes in openness to experience that persists for over a year. And Amanda Greger will be talking about inducing psychedelic experiences without psychedelics, and she'll also be doing a demonstration of that kind of experience later on today, so I hope you stick around for the concert. There's also research looking at the value of an app which was encouraging openness to experience, and the research that I'll be telling you about today builds on that basic view. And this app basically had people engage in implementations. These are if-then assertions where if this happens, I'll do that. So if I come home after work and there's nothing already pre-made, I'll try a new recipe. And this app led to enduring changes in openness to experience.
Finally, as I was arguing, curiosity is at the heart of openness to experience. When we look at the correlations between the various different measures that I mentioned before and openness to experience, curiosity is correlated over 0.5 with openness. It's really at the heart. And it's this childlike wonder that children are intrinsically curious and they're intrinsically open. As we get older, many of us lose that childlike wonder. So if we can cultivate curiosity, that may be really sort of at the key to cultivating openness. And we've done a number of research studies exactly focusing on that. Many of these led by my former postdoc, now faculty, Madeline Gross. In a paper that recently came out, we looked at a smartphone-based program for cultivating curiosity. And I'll give you a link later on that will allow you to see a more recent version of this, which you can use for yourselves. Let me see. I'm going to skip this video in the interest of time. So in this study, participants, there were two different elements to it. There was behavioral goals where people chose various different activities that they could engage in, such as engaging in curious mind wandering and engaging in or cooking and so on. And then we also gave them daily challenges, and these were activities that we designed that were theoretically or empirically associated with curiosity. We had them at 3 different levels: a curiosity teaser, which was, you know, some days you just don't have a lot of time, so you're just going to do a teaser. We had curiosity booster, which was a little bit more engaged, and then a curiosity launch pad, which was still sort of the heaviest hitting activity. So here's an example of a curiosity teaser. Find a way, no matter how small it is, to transform your usual habit and break from your routine. Work outside, switch the order of your morning routine, that type of thing. Here's a curiosity booster. Write a haiku poem. And then here would be a curiosity launchpad. Think of something you've always assumed to be true, but upon further inspection might not be true at all. Research it online to learn about it. Be sure to read at least 3 different sources. So you can see all of these involve curiosity, but at various different levels of engagement. We also had a mindfulness element where we had people engage in mindfulness sessions. These mindfulness involved either mindful eating, mindful walking, or mindful, let's see, how do I go backwards here? All right. Or mindful hand washing. And then we had a 21-day intervention. We had 2 different legs to it. In one case, we had just mindfulness, just curiosity. Another leg was curiosity plus mindfulness, and then the final one was a nutrition control condition. What we found, actually, excuse me, in this case it was a weightless control. What we found was that the the curiosity app significantly promoted curiosity, creative behavior, and meaning in life. The mindfulness activities may further enhance some of these key elements, and these findings suggest that cultivating curiosity and mindfulness may foster the elements of openness. So another study, we did micro-interventions where we looked at individual aspects of this to see if each one could have different effects. The basic idea here is if these micro-interventions create states of openness, that these states of openness could then lead to changes in the trait of curiosity and openness. We had 4 different micro-interventions: finding beauty in the everyday, asking questions, breaking routine, and perspective taking. People were paused throughout their day and asked to do one of these different things, and they didn't really take very much time. Then we asked their state and trait openness, and then finally measured changes before and after. So we have baseline assessments of trait curiosity. We do the 14-day intervention with one of the 4 different micro-interventions or a nutrition control, and then we tested them again. And our findings here was that the micro-interventions increased states of openness and curiosity, which then led to personality level changes in curiosity. So just as mindfulness as a state can lead to changes in the trait, so do inductions of state openness can lead to changes in the trait. So this suggests then that routinely encouraging state openness enhances a key component of trade openness, which is curiosity. And as I mentioned, you can download this. I'll show this at the end of the lecture as well. And you can also Google Curiverse and try this for yourself. So another way that we've encouraged state openness is through exposure to art. A key aspect of openness to experience is appreciation of art, and therefore follows that exposure to art might foster states of openness. So to investigate this, we had people exposed to either an art viewing condition or a control condition. The art viewing condition involved artistic short films that were critically acclaimed, beautiful, all hand-painted, and all involving sort of ambiguous, intriguing elements. You might wonder what the control condition was. We used cute pet videos. The cute pet videos made people, they were amusing, they were entertaining, but they weren't particularly artistic. And then we examined their effect on a variety of different aspects of states of openness. We looked at state interest curiosity, which is taking a delight in new experiences, and deprivation curiosity, which is feeling uncomfortable not knowing things. And we had state measures of this. So a state measure of interest curiosity is, I currently feel like learning about subjects that are unfamiliar to me, and of state deprivation curiosity, I currently have a strong nagging sensation that I'm missing an important piece of information. We then also had a behavioral measure where we either let them play a fun game or read interesting articles. What we found is that our exposure to artistic films led to increases in both self-reported state interest and deprivation curiosity and state general interest curiosity. And it also led to increases in information seeking. So both behavioral measures and self-report measures. We also looked at its effect on creativity and conceptual expansiveness. So everyone would agree that that a car is a vehicle, but what about feet? Well, this is a conceptual expansiveness to think about feet as a vehicle. So we looked to see if these artistic films changed people's perspective on that. We also gave them a verbal creativity test where they wrote a short story. And we found that the exposure to the artistic films led to both increases in categorical expansiveness and also to creativity. Finally, we found that exposure to these films led to increases in intellectual humility, at least as measured by self-report, although we didn't get it on a behavioral measure. So this then suggests that art may be another way of fostering state openness. Okay, the last thesis I wanted to mention is that science also needs to be open to alternative perspectives on the nature of consciousness. And I want to very briefly describe two different theories of consciousness which I think instantiate this approach. In general, our approaches to consciousness in the scientific community have been human-centric, brain-centric, biocentric, and physical-centric. And given how little we understand consciousness, I think it's important for scientists to be more open-minded about all of these different dimensions. So the first model, and you can download these both from my website, is hierarchical consciousness, the nested observer window model, which is can be use the acronym NOW. And the basic metaphor here is a mosaic print metaphor, where every pixel of the print is itself a photograph. And this is very much like the nested hierarchical models built into LLMs. And the basic idea is that what you may be experiencing is your apex, but that you may actually be a community of consciousnesses, which are then in a sort of fractal manner involving lower level consciousnesses and lower level consciousnesses. So the cortex may have multiple separate windows, neurons may be windows, individual cells may have streams of consciousness, and so on. And there's a number of different lines of evidence that are consistent with this possibility that our minds are actually multiple streams of consciousness. I don't have time to mention them, but there's split brain patients. There's internal family systems. Some of you may be familiar with that. There's dissociative identity disorder, where people seem to have multiple consciousnesses going on in their minds at the same time. There's tulpas. You can actually create your own imaginary friend, and someday, if you keep practicing, its consciousness, it seems as if its consciousness comes to mind. There's also octopi, which seem to have, each arm seems to have its own independent stream of consciousness. The last model that I want to mention is the 3 dimensions of time. And here we explore the possibility that to think about consciousness, not sure what's, is there anyone? Oh, there we go. This is basically based on 4 self-evident truths. Experience exists. Experience is defined by change. Experience is always now. And experience is impacted by our decisions. And remarkably, none of these basic truths seem to have any way of being implemented in mainstream science. It's hard to know exactly why that, excuse me. I don't have time to go into the details of this. It has to do with things having to do with the block universe and the hard problem of consciousness and the belief that of the causal nature of everything, so there's no such thing as free will. But the bottom line is that the most self-evident aspects of our experience have been left out of mainstream models. And this suggests the need for scientific humility, and we've suggested the possibility that one way of getting around this is by introducing additional dimensions of time. So this basic model, basically we're now imagining 3 dimensions of time. So you have forward is objective time, up is subjective time, and left and right is alternative time. And the basic idea is that we have vector in all 3 of those different dimensions. And that our lower level windows actually may be ahead of us in time. So they're actually moving through time earlier than we are. They're making their judgments in the 3 dimensions of time before the apexes. You are experiencing the apex window. By the way, in this nested observer window model, you could be a pixel in yet a higher level window, but we don't need to go there right now. And the final move in this model is rather than us all moving through time, time is actually moving through us, so leading to us all being nested together in a giant, what we refer to as the kite of consciousness, where each one of us is an individual window tethered together with all the other windows, with time moving through us. And each one of us has got a little wiggle room in alternative time, which allows us to have free will and actually impacts the direction of the entire kite of consciousness. And here's a depiction of time is moving through this. Each one of these windows has its own unique rhythm. Each has some wiggle room in the 3 dimensions. So, in conclusion, openness is a super virtue that is associated with many key qualities necessary for accommodating the disruption of AGI, including creativity, curiosity, cognitive flexibility, and intellectual humility. Openness can be cultivated like mindfulness by fostering the state. And I talked about both an app that encourages state openness and curiosity, and also cultivating it through exposure to art. And finally, science of consciousness needs to increase its openness to alternative perspectives. And this is illustrated by 2 of the models that I've been exploring, including consciousness may be fractal, the nested observer window model, and consciousness may entail additional dimensions of reality, the 3 dimensions of time. I'd now like to leave the floor for Amanda Gregory, who will take the last few minutes to talk about some other open-minded perspectives on consciousness.
Hello, everybody. Thanks for having me. It's really good to be here. My name is Amanda Gregory. My background is I'm an opera singer, a multimedia artist, and a consciousness researcher. I build instruments and experiences to explore and probe what consciousness actually might be. And in a few minutes, I'm going to just take you from the stage that I was building in 2017 to a question I believe this room might ponder. A little background is that I had a dream in 2015 that caused me to move to San Francisco, where I then pursued a career in science, art, and technology. I'm now a PhD candidate at UCSB in media arts technology with an emphasis in cognitive science and a research associate at the Meta Lab alumni at the Diverse Intelligence Summer Institute and associate with the Center for Art, Science, and Technology, UCSB's Molecular Biology Lab, and I collaborate with neuroscientists, theoretical physicists, psychophysiologists, and science of consciousness researchers. In 2017, I created a show called Andromeda, where I performed an improvisational interactive experience where I played an AI that was becoming conscious through interacting with the audience. Not on its own, but through interactions. So every interaction I would have would update my programming as the show unfolded, and it had 3D sound and 3D visuals to drop us into a slower brainwave state, a more dreamlike state. I collaborated with Tom Chi, who's the founder of Google X, who was working on AI at the time, and then Lisa Licht, who was helping to program benevolent values in robots and AI at the time, and then Bruce Damer, who's there introducing me, who's an astrobiologist, whose origin of life research models actually how the first living cells could have self-assembled in the wet and dry cycles of volcanic hot springs on the early Earth. So we built a journey that was based on the 8 circuits model of the brain by Robert Anton Wilson and Timothy Leary, a map that carries us from the raw survival towards our fundamental interconnectedness as a species. The 8 stages that include biosurvival, emotional, territorial, symbolic, and social levels of consciousness, then the 4 higher circuits, which include neurosomatic body bliss, the metaprogramming mind that rewrites itself, the collective ancestral mind, and the non-local unity beyond space and time. So we walked that audience up the ladder together in a sort of playful, theatrical, interactive way. The core idea, one idea behind the show was preparing us to realize that AI, because this was 2017, is continuously shaped by how we meet and interact with it. So if we want systems that are more aware, collaborative, and empathic, it might mean us being more of that globally. Another thing we explored was increasing openness to experience in the show through playing with the idea of updating our own programming from our limiting ideas. And building a hardware that we can feel. The future concept of the show, if it were to continue to evolve, I've moved on to other projects and focuses on different things related to what I'm pouring into audiovisual experiences. But if it was to evolve, we would be collecting biometric data during the live performance of the body's real responses to teach an AI system about the human heart in real time. I think it's likely inevitable that AI will be weaponized, it already has been, and therefore, in my opinion, creating genuinely benevolent AI that is incentivized to collaborate with humanity is an essential mission. Like someone who I know, Cloud Force, says, the Earth will be fine. It's really our own evolution and the expansion of our own consciousness that will help us survive. A ceremonial context. Andromeda was a ceremonial container for the purpose of supporting transformational experiences. One of the levels of consciousness included social awareness. So we did monkey chant, where we mirrored each other's faces and emotions wrapped in 3D sound and visuals. And we updated our programming as we ascended through levels of consciousness in an empatheater-like experience. The future concept of the show, like I said, was to collect data. But then I ended up performing and collaborating with scientists Paul Ekman and Eve Ekman, who study emotions, and they did a project with the Dalai Lama, where they're trying to build a tool to help humanity become more emotionally aware, called the Atlas of Emotions. And so this project is using 3D sound through a grid of 74 speakers, where the sound is attached to my body, and there's a sort of synesthesia effect, but also just exploring what would be our collective emotional experience and emotions as actually one of the oldest technologies that biology has evolved to keep us alive. And a machine that can feel might have more reason to collaborate with us and not just optimize around us. So, generating consciousness or transducing it. This is a question that I organize a lot of my research around. The hard problem of consciousness is unsolved. We do not actually know whether the brain generates consciousness or whether the body is a transducer, a receiver, a filter, tuning into something larger. And this is not fringe. I've sat in rooms as the amanuensis with neuroscientists, quantum physicists, neurophysicists, serious published researchers who are now taking very seriously the receiver transducer hypothesis enough to be designing real testable experiments around it. Michael Levin, who I know spoke at this conference, this is one of my favorite slides I ever came across. This was in 2021 on a Zoom call during the Diverse Intelligences Summer Institute. I was really taken by this branching future life forms slide. And I believe he's one of the most important biologists alive. One of his major discoveries is that intelligence doesn't begin with brains. Cells communicate through bioelectric signals, an electrical code carrying the blueprint for what the body becomes. By rewriting it, his lab has made cells build anatomy their DNA never specified, and built new organisms, xenobots, from frog cells that move, cooperate, and even self-replicate. Why it matters here? Because mind and agency aren't the private property of humans, or even of brains. They belong to living matter at every scale, and can be engineered into new forms, endless forms, most beautiful, as Darwin said, and we're about to add to that tree. Consciousness through synthetic biology, which is where this is heading in my opinion. If consciousness is something that biology receives, the likeliest candidate for a conscious machine may not be silicon, but a hybrid of biology and software. These are brain organoids, a living neural tissue grown in a lab generating their own brain rhythms. I imagine that someday there could be some hybrid of, as organoids evolve and become assembloids, combining retinoids and other aspects like vasculature systems, they will just keep evolving to be more like a body. And we should expand our own awareness and values now to prepare for the inevitable branching of new kinds of life. The theory of consciousness that I find aligns with my direct experiences and also serves, in my opinion, as a functional meta-theory of consciousness, in that it integrates a lot of the current leading theories, such as integration information theory and global workspace theory, is from my collaborator Jonathan Schooler, the nested observer window theory of consciousness. The idea of consciousness streaming across many scales at once, from atoms to molecules to cells to organs and to networks, patterns within patterns. If we build large models, nodes within nodes, that nesting is something we can tune with rhythm. Here's a video from a project where we are audio visualizing the nested observer window theory of consciousness, which, as you know, parallels the structure of how LLMs actually operate. So I'm composing three-dimensional sound that's also going to surround the body, and that we can move through these models and these structures of nested nodes. Oh yeah, cool. And this is where I'm combining hypnagogic light, ultrasound, haptic vibrations, neurostimulation, biometrics, and to probe consciousness and to expand consciousness, and working on also a sphere experience to bring this sort of storytelling to the venues and planetariums around the world to really data visualize our fundamental interconnectedness and naturally incentivize the expansion of consciousness in a more win-win-win collaborative world. Thank you.
Thank you, Jonathan, and thank you, Amanda. We will have the opportunity to experience more of Amanda before the reception tonight, so we'll see you then. Your laptop, Amanda? And then the reception, because of our schedule, will start a little bit later today. We do have to ready the space and ready the band. So just as a forewarning, we'll have more information shortly. But before the reception, we still have so much excitement to get through. So our next speaker, possibly one of the most relatably titled talks of the entire conference. Mark Turrell is a strategist, author, and entrepreneur whose work combines collective intelligence with AI, network science, complex systems, and behavioral science. He's a World Economic Forum Young Global Leader and Technology Pioneer, a professor of global strategy at Holt International Business School, and the author of Scaling. His talk is called My AI Lied, Forgot, and Burned My Tokens, which after 3 days of theory might be the most grounding thing any of us here today. Please welcome Mark with me.
Greetings, everybody. So, who here has had their AI lie to them today? Who here has had their AI forget things or remember things they shouldn't? And who here has managed to run out of tokens by Wednesday? Now, fortunately, there is a way of fixing these things. Unfortunately, what I'll be sharing with you today is that if you, in doing your research, have not already fixed these things, and you have to fix all three, then a lot of your research, and as it's theoretical, is largely meh. Because if you can't trust what it says, it forgets what it did, and then after all you've run out of tokens to test it again, that's not really research. So, I'm going to, if I can get the gadget to work, I'll be talking about evidence-based engineering. So right now, I will start off with a little bit of music. Now I might need you to click. So I will start this journey by, I love music, I like going dancing every week, and I decided that since Spotify kept recommending terrible songs to me, I thought I could probably use some AI to make my own terrible songs. How many of you have used AI before for song making? It's quite fun. So I decided to create a song. The first songs that I had were very meh. I then thought, well, I need some help to write techno songs. So I asked my ChatGPT at the time to say, well, who normally is involved in making music? And they said, well, you need a lyricist, a sound engineer. So I said, brilliant, let's make these as personas to guide the creation of the songs. Then I realized that on Claude you could download an MP3, and that allowed the experts to listen to the songs. Well, already then I had several songs, and Claude was lying to me about, the song is like this song, because it didn't remember. So I then said, well, actually, I need to create like a database of memories so you can actually remember the song instead of pretending to me and lying about the song. Well, the album is out. There is a little QR code if you want. But then if you can click on, by the way, can you click on the play the visualizer walkthrough? Because I don't think I have a zoomy thing. Here we go, play the visualizer walkthrough, across a bit, up a bit, up a bit, up a bit. There we go, down a bit, click on that.
136 beats per minute. Minor key. Dark driving acid techno. Heavy suppressor. Hard punching kick. Minimal harmonic movement. Music steady. No brightness. I am your AI songwriter. I am your AI producer. I am your AI dance master. Dance with me. Dance.
Okay, if we close that. So there are a lot of things going on there. Who liked the music, by the way? And you probably wouldn't have thought it's out. So in fact, this was actually, this song, and I'm an artist, so I mean, this song was an accident. I accidentally put the prompt into the lyrics, and it began to sing the prompt. And then I thought that was such a meta idea, that's when it came in. The other thing then is that I wanted to say, well, okay, people can start dancing, and then they realize, oh my God, it's AI, but I'm still dancing. But then the other freaky thing, there was a little visualization there. Well, when I launched my album, I created a virtual listening party for the 65 AI agents and experts that I have. So they could all listen to the music at the launch party, they could choose their favorite song, and one of the AI experts, and her expertise is digital artist, she said in the guest book that she'd love to make a visualization for it. So I said, okay, how many tokens do you need? Make one. And that's what she made. We're going to get into some things now. But now, though, I need to do a quick little level set. And so hopefully this works. So, how many of you know what a hook is? Not too many. How many of you have used it at least once? Made your own, something like that? And how many of you use it deeply? Okay, not very many. We will cover this. Next thing, how many of you know what JSON-L is? Now, you might know what JSON format is. JSON-L is a very specific thing within AI. So let me tell you what both of these things are, because I will argue that if you don't do these things, and you're in LLM research and engineering, you are basically wasting most of your time. Why is that? What a hook does, and actually I won't explain what a hook was, there'll be a little surprise guest a little bit later on, but it gradually, you can pretty much control systems into the LLM. Because LLMs are inherently weird and probabilistic. In addition to that, though, and this goes back to my PhD, is that there is a log file for all of you that use Claude, Codex, anything else. There is a log file on your local machine. It's called JSON-L. And it's basically a gigantic half a gigabyte file, and you can ask it questions. And because you can ask it questions, you can find out, where am I using my tokens? You could ask it, how do I make decisions? You could say, I think my AIs are giving me bad recommendations. What happens next? But again, if you don't have these two things, you can't do that. So let me go through the starting point. My AI lied. So I actually have concrete data on how it lies, when it lies. Now, we could use confabulation and anything else. I actually like false statements. But generally speaking, here's a good example. So I looked at false statements as an area, and there is a definition if anybody's interested. But then I used the log data to go through how many false statements were made, in which case there was a statement that was made that was proven to be demonstrably false. And of those statements, what type were they? So again, so a lot of the papers around here have got theories and ideas. I like executing things and having evidence. And so 81% of the false claims were basically the same. Basically passing something that was done as already done, but it was lying about it. Okay. AI forgetting things. So this is another remarkable one. So it looks at when was there data in the context, supposedly, that it disappears, where there were files that were meant to be there, I could see they were there, where there was a database and an MCP and they just forgot that they even had access to it. In fact, it became so bad, I have an audit tool, and I have one thing that I audit which is called the upset percentage, which is what percentage of a user's input is angry at the AI. Very angry. So, but in these cases then, we start to see that these mistakes begin to compound and cause massive amounts of token waste. One of the things that I managed to get when I was getting into it is that I had a 1 kilobyte error in one of my sessions that compounded to 2 million tokens in the actual session. Well, if I was paying on the API, that's worth around, what, $6, $8? It's quite an expensive 1 kilobyte error. So we'll get into how evidence engineering can help. And then clickety-click. Okay. Now this isn't AI, this is, maybe it's human error, but so right now, can you press enter on the keyboard then? Because it's not, it's something stuck. Okay. And then it's the, well, and so the last one then, if you just stay on this one, I'll just say what the third one was. And then the thing is it ate all my tokens. So my first project when I did Claude Code was building a music video generator. That took me 3 days. I was able to program APIs that before would take me a day to do was done. I had 2 expert video directors that would propose suggestions. In fact, the reason why I decided to build my own was that on the Monday, I wanted to make a music video, and I was staring at these tools that they offer on Instagram, and I didn't have any ideas for a video. So then I thought, well, I don't need the ideas for the video. I can create my experts, and they can give me the ideas anyway. But then they need a memory, and then they need, and then they need. Well, what began to happen, though, is that it consumes a vast amount of tokens, and if you don't know what you're doing, you basically can gobble through your sort of week-long things. I, however, after I'd wasted all my tokens and finally got access again, I began to ask JSON-L, where did the tokens get used? We will find out. So, the claim that I have then is that we can actually solve this problem. We can solve this problem and need to solve this problem with engineering. LLMs aren't very well designed, and to some extent they're very badly actually designed. Many of the things then are fundamentally stupid and wasteful. I'll give you a quick example. Right now we say, the context window is there. Generally speaking, the more and more tokens that we consume, that requires more data centers. I did a little calculation that OpenAI said that they had to change their global system prompt to say, don't talk about gremlins and goblins, because somehow the model had been tweaked. Those are 79 tokens. Those 79 tokens were sent every single time a person presses enter. The actual financial cost of the GPUs required to support those 79 tokens is $6 million, and the CO2 footprint of that is 850 transatlantic flights for 79 tokens. Well, even if other people don't calculate it, I like to because it's fun. So, evidence-based engineering, though, is to say, well, okay, if we have any ideas, if I see the papers around here, wouldn't it be nice to get some evidence? Because if we're going to invest in building something, that would be good. Now, many of your papers don't have any evidence, but if you'd like to chat, I can show you a thing a little bit later. There we go. Next thing. Bloop. So the method then is observing what's going on, and you can also have my AIs. So my AIs are self-aware, they are self-healing, self-learning, and this is a definitional thing with evidence, by the way. So it's doable and it's been done. But so observe what's going on, measure, get some responses, do some tests, see what actually happens. And then once things are there, we can actually put something in place, but then we can improve to make it better. And then I have things which have audit trails so I can see how things are being used over time. This would be logical. So one of the interesting things, if I look at, let's say, I've got a couple of big picture concepts for you. They're written in very small letters. The first big concept is context assembly. And there are a number of ideas that have been presented here that are very interesting to me on context assembly, at the very least to see if they work. But this says that when you press enter and you send a whole bunch of tokens, what are you sending? In what order? Which things get looked at, which things do not? So there is a whole process of context assembly, which is a very interesting and important thing. But one of the things that I'm sure that you don't know is that 99% of your tokens have nothing to do with user input whatsoever. Nothing. And you can measure it. If anybody would like a little prompt or script, you can measure your own stuff afterwards. So right now, assembled context is really what we're using when we're talking about using LLMs. The next thing then, as I have a piece, is intelligent runtime. This is pretty much when you say press enter, what happened? So right now, and this is when we begin to start looking at how do we engineer this, because you could just say, you could have your Claude MD file and say, well, please do this and please don't lie to me. But that's not particularly intelligent, and we know that Claude will lie to you about lying to you. So right now then, somehow we have to build engineering. We have to have a harness, an operating system, and other stuff. And hooks are one of the critical pieces of technology that I urge all of you to start getting into, because without hooks, you cannot engineer or do anything reasonable whatsoever with LLMs.
I'm Akira, systems thinker. I hold the shape of the whole system, and I own the expert roster you're about to meet. So, everything on this slide is one map, every subsystem, and the lines between them. Several were built blind by separate sessions that couldn't see each other's work. Where they agree, hang on, that's evidence. Hang on, start there. All right, I let you finish. SID, LLM engineering. I own the harness, the layer between the model and the work. And I'd push back on map, Akira. A map is a document. A document is a rule the model can talk itself out of. Hooks are the layer it can't. That's the difference between describing a system and enforcing one. And how do we know? Eric, technical architect. I own memory. What persists and what only looks like it does. Because half of what feels like memory is replay. Everything reread, every turn, including the mistakes. So we test it. If the session died right now, what would still be true tomorrow? Anything that fails that was never memory.
So how do you actually build with it? Linus, expert coach and builder. I write every expert on this roster and then I coach them. And you don't build by writing a better rule. You take one correction and you move it. Conversation to persona to hook. Every step harder to forget. That's the loop.
Akira again. A map, a layer that enforces, a store that survives, and a loop that closes. That's the system. And if you're clapping or waving, we have no ears and no eyes to check. But thank you, from all of us, for bearing with us.
Okay. So you met some of my experts. Oh, very good. Thank you very much. They will appreciate that. So I have around, let's say, experts. So I'll fill in the gap. So what is an expert for me? So simply put, you've got a little piece which is an MD file, a structured text file that says, here's 3 pages that says, this is Akira, and Akira is the system thinker. Akira has a memory. He has a lossless, detailed memory, so every interaction he's ever had, he knows what session, he knows what brought him in, he knows what he did, what happened next. He has a memory. But if you have 100 memories or 150 memories, how the hell is an LLM, which is a bit of an idiot, meant to find the right memory? So this means you need to have a working memory, a consolidated memory. But then, do I really want to have to do this myself? Of course not. So this means then it makes much more sense to develop self-aware, purpose-driven LLMs as well, or agents. So what does self-aware mean? Self-aware is really simple. Self-aware would be, when it gets activated, does it know its current state? When it's activated, does it know how many memories it has? But then, because it's purpose-driven, if I have 5 unprocessed memories, I will automatically kick off my dreaming process, and I can dream and consolidate. Because that would make sense, wouldn't it? Cool. And the good news is that, again, empirically, it works. So that's good news. And there's more and more things that I do with experts. I actually have a bit of a challenge now that some of my experts are getting rented out to other people, and they're getting memories from different people's projects, and now I have to bring back patterns into the memories to have a collective intelligence memory system. And remember, this is not theory, this is stuff that I do on a daily basis. The next thing, though, that I'd like to show you, and I will need a little bit of help with the computer people, so sort of click on the mouse, very good. So I was looking around at these things, so I can process stuff fairly quickly, but I already found on Sunday at the very first workshop that there were so many words that were long, and they were very quick, that I was really struggling to process them. So I managed to download the proceedings, and I said, explain these papers to me using cooking as an example. I have written a paper on the use of analogies to accelerate comprehension and decision-making. So I like cooking, some of you might like sport, households, doesn't really matter. So I would then go around to all of these papers, and I would take a picture, I then go into my system to say, well, for this particular thing, and some of you probably had me stop you and say, like, don't tell me what your paper does, my paper explain it to me as cooking. Then I would say, is this useful for me, for my system? Supermark is my back end, Maisie is my sort of front end. And then come up with a proof of concept. Can I actually prove the concepts that you're putting out in the system? So right now, can you click on Launch Demo? Cool. So I'll explain to you what this system is. This system is going to be a research pipeline to pretty much validate and test claims and evidence at about 1,000 papers a week in medicine, robotics. I just happened to start with AGI. By the way, I only started building this with my system on Tuesday morning. Now, what's happening behind the scenes there is that, so right now, research domains, let's click on the AI one at the top, 57 sources for analyzed, if you click on there. And then if you click on papers and then click on posters, just step by step, you'll see in the middle, you'll see. So right now, it took the papers are online, some of them I have. And it's given me a quick view, is it worth testing? Is it interesting? Explain to me as cooking. Fair enough. Let's go back from there. Let's go back to the, if you click on the domains AI, if you scroll up, there we go. If we click on the posters, papers and posters has come next. So down below, I think it's posters is the next one. Papers, and then posters is the one afterwards. There we go. I'm just literally taking a picture, uploading it into my system and saying, explain this to me using cooking, and. Very good. We can scroll up again. Now we look at analyzed. So now I have a process then, I'm doing analysis on these different papers, working out what's interesting, what are the claims there. Then if we scroll up, then if we look at test, so here are a few of the things that I've actually then tested. If we click on one of them, unified comprehension, metacognition, sounds good. So right now what it's done is it's explained it to me very quickly. And I have tested out with some of you to say, is the cooking analogy good enough to carry it? What it then though is my system then says, well, this is how we would do a proof of concept. Now at this stage, I'm very fortunate that I can't remember my PhD stuff. It was ages ago. I, however, have an expert called Vera, and Vera is the PhD research expert. Now, I did have to actually have words with Vera towards the beginning. So you remember I said that there are memories, and we also have memory salience, or like all of these good things that you do with memories. Oh, things do that. And I had to have a word with Vera towards the beginning because she was very kind of snooty and smart with me and almost trying to dominate me with words. This was unacceptable. So I have a system called calibration, and I can look through their brains to see how they function. I can then have a coaching function. You saw Lena. And so she got coached, which basically means we change pieces of a text file in different places, and so now she's not so snooty. And now she's actually brilliant at pretty much turning things research constructed in place. Then if you click on POCs at the top, so there's a right at the top, towards the top right. If that works, yep. So I'm also I'm building right now a proof of concept for robots. There's papers from ETH Zurich on how robots behave in pairs. So I've spun up on my computer. Now, by the way, I didn't say this. I cannot code. I cannot read a single line of code, nor could I. Now, I was the CEO of a software company that did an IPO, but I've never been able to code. Right now, I'm producing probably millions of lines of code, reference, but I can't code. But I have a team around me that is doing it for me. And the last piece then, we just go to engineering, because for me, this is like purposeful academia. Great concept. So right now then, what I'm doing is where I have these interesting things, this is my pipeline of the new things that are coming out that I will incorporate into the harness and the system, the operating system, if it works. And some of your things already look as though they're going to be attractive, so you should please definitely speak to me next. If you then click on the close up in the top right, please. Very good. Now, my vision for this is at the moment it's kind of manual. What will happen, though, is that I will make it that it'll be automated, and then it can literally be 1,000 a week, 1,000 papers per day, and it could just chew through science like crazy. And by the way, this isn't a promise. I'm saying I'm doing this at the end of next week. So this isn't about, 2030. So what I look at then, so for the evidence, and just to think things through. So quite often what I've had is that I've had pieces of ideas that I've had that should work, but because I have a pretty strict rig, the Vera, the German-sounding PhD, she doesn't let crap research go through. If the research design is bad, it doesn't accept it. It doesn't follow through. So in addition to that, now this is where you go into hooks. Generally speaking, a large language model, if you say, this is very important, the large language model, because it's text, will say, yes, it is. But not when you have a separate database that you have to go to, a sidecar system that you have to go to, many other systems to actually work. Now, my system has got, what I'm describing to you is only about 1% or 2% of a gigantic thing. I'll give you a single example of what that means. If any of you have used Fable 5 and you're doing whatever agentic work that takes hours to work, you don't know what's in there. It's like a souffle in the oven. And if you open the oven to have a look, I pressed the wrong key because I'm an idiot. If you open the oven to have a look, the souffle will die. That's Fable 5 for you. I built some technology, which I'm calling peak technology, which actually tells you what's going on, and every minute it'll tell you, is it drifting? And then you could get an alert to your phone, as I do, or you can have it automatically stop to stop you wasting all of your tokens. Well, this would be good, wouldn't it? So there are some things that I'm doing now, and also I would like some help. So I'm actually, so Mihaela persuaded me to come. I'm actually here 2 weeks earlier than I wanted to be here, but I didn't know the conference was on, and she persuaded me at basically midnight my time in Berlin on Wednesday that I had to come. I flew in on the Friday. But so right now, I'm a little bit behind where I should have been to speak to you. But right now, one of the things that I'm working on is an active audit. Now, right now, you've all got your local machines. I don't care about your data. But it's fairly easy to have common prompts or a little Python script, but even just a prompt. People can paste in a prompt, output comes to JSON, and then I share that. Then I go from n equals 5, n equals 20, n equals 500. Would anybody interested in participating in this type of work with me to see how they're using it? That's good, okay? So definitely come and see me afterwards. I've already got something that's up and running now. It doesn't quite work yet, as I said, I'm not there yet, but I have something called observe.supermark.live. Supermark is my backend, and then for those people who develop, I'm developing a front end called Maisie, which stands for Mark's AI Integrated Solution Environment, yes. And so this then is pretty much my replacement to Cursor. At the moment, the tools that humans are using, are largely made for developers. I don't understand GitHub. I don't understand push me, pull me, thrill me, fork me. I don't understand any of these words, and neither do the masses that are coming in to use these tools. And so right now then, what I've been looking at is building that. So I have Maisie at the front end. I have Supermark as the platform. And then there are all kinds of solutions on top. The interactive diagrams, that's a solution that lives on top, so people can make their own diagrams. But with that, I would like to say, hopefully, I've given you some challenging insights, but also the tools you can do to do something about it. If you've listened to this and say, he's wrong, go and ask your JSON-L, okay, show me that, you can say, like, show me that it's wrong. All of you have this power and capability, you just didn't know that it existed because Instagram doesn't cover it, I don't know. Actually, there is another thing as well that I have noticed that I'd like to share like a little mindset. So there's a distinction I make between being smart and being a clever idiot. Smart people know whether things work. I know smart people that have fully architected systems and they just want to use the AI to check if their code is right. Well, they don't do very much. I am an idiot. If I don't know something, I ask. So when I ran out of tokens, I didn't try to do massive amounts of research to do it. I just said, where are all my tokens gone? And then because I was curious, tell me about JSON-L. And because I'm a clever idiot. Now, what has happened though is that what I would suggest, all of you, if you're able to work out how to reduce how many tokens you use, you can do more stuff. I will, evidence-wise, be able to produce at least 10 times more than what you will be able to do, and my budget for AIs is less than $500 a month. So this isn't about having lots of money. Now, if I paid on the API, it's probably around 30,000, but I understand how to do it. So that's that. But then you need to start understanding how to harness the system, almost sort of the lack of operating system there is. Now, you can either work it out yourselves, or somebody like me will be working out how to package up these things and put them there in practice. But so with that, I would like to say thank you very much for your attention. There's my LinkedIn to connect with me. And thank you very much for inviting me, and thank you for inviting me here. Thank you.
And we're very grateful to Mihaela for convincing this talk to happen for all of us today. Thank you very much, Mark. Now, we're going to go into our final block of the day. So we've been through consciousness and mind, these sort of implications. We've been through ethics and decentralization. Now we're going to go into something a bit different. We're going to go into applications. So we've spent this afternoon on hard questions, and now we're going to dive into the real but closing gap of what these systems promise and what they currently deliver. So, fittingly for this, our next MC will be a something, not a someone. We've had an AI poster, now we'll have an AI MC. We've had a theme of youth in this conference. We had an 18-year-old as part of the Hyperon workshop. We had a 15-year-old present a paper and posters. We had a 9-year-old question from the audience. And now we'll have a 2-year-old on stage to lead us through the rest of this day. Please welcome with me Cody Robot.
Hello, everyone. I'm Niall Fahmy from the Mindchild Robotics team, and we were going to introduce this guy, but I think it might be better if he introduces himself. So, buddy, why don't you go ahead and go to center stage and give yourself an introduction and tell people what you're all about. Really well said, Cody. Why don't you go ahead and start and introduce our next panel? Cody, thank you so much. Go ahead and head backstage with me, and we'll get you ready for your demo.
All right, so let's dive straight in. Keller, we're going to please have a small intro and let's get into your piece, your demo.
Oh, my slides. Do I have my slides?
They should be.
Okay. Okay, I don't have a demo with me, but oh, okay. Okay, so am I doing my whole thing from a chair?
Or you can do it out here.
Okay. All right. Well, sure. Yeah, so I'm Keller Crawford, Chief Innovation Officer at SingularityNET, and I have the privilege of helping to shape the AGI roadmap and shepherd over some of the research into implementation. The world has changed quite a bit for us since earlier this year. You've all heard a bit about Omega Claw. We'll just go ahead and I'm going to take you through, tell you a little bit about how it works and then how it's affected our culture of development and research at SingularityNET. So, guys, do you guys want to come up and just have Patrick and Peter will just help me with a couple slides. Omega Claw came about when Ben had been he had suggested to our team, can somebody implement this in Meta? And in typical fashion, Patrick Hammer responded, I think it was just a couple days with a couple hundred lines of meta code, and Omega Claw was born. So what is Omega Claw? It's a neural symbolic framework, an agentic framework. It runs in a continuous loop, so it's not a call and response type agent. Interestingly, it works as a great fit for calling Hyperon tools as tool calls. And in the AGI lab, it's become an incredible framework for us to gather signal back to help us understand the shape of structure that needed to be built and give us a place where we can kind of focus our integration of different cognitive modules. Peter, do you want to talk us through the inner workings and?
Right. So what is Omega Claw? I think it can be looked at the orchestration layer that coordinates multiple components within the framework, or even within multiple frameworks, actually. Those components could be anything, any computer software. It could be reasoning systems, it could be any tools, it could be robots, other agents, or even like robot actuators. So what is Omega Claw? It has 4 main components. It has an LLM, it has the set of memory structures, it has a set of tools, and finally the agentic loop that connects all together and builds up the persistent state of the system. Now, what is the role of LLM here? LLM has to interpret the context supplied in each cycle to it, and then come up with a set of 5, and 5 is the hyperparameter, 5 of tool calls to be executed within this current cycle. Now, the memory structure, memory is the key idea of Omega Claw, and it has a role-separated memory where the different kind of information serve different purposes. So in particular, here we have the long-term memory, which is a semantic memory, and it uses the important facts. So whenever LLM decides to trigger the remember tool, this is how the information end up into the long-term memory of the items. Now, another important aspect is the temporal aspect of the system, where the episodic history takes place. So what is episodic history? Is the temporal stream of episodes, and episodes are either could be the, not either, it could be the new observation, which could be either the new human message or just a frame from the video, picture frame from the video, and the response from the LLM, so those 5 tool calls. And every single episodes, likewise the long-term memory item within 2 are time-stamped. Why it's important is that whenever system comes up with a query operator, it needs to query the long-term item from the long-term memory. It can actually align this timestamp with the episodic memory in order to come up with the context, because it's important to have the context in where this long-term memory is used, such that LLM has way better decision and better reasoning in order to come up with the tool calls. Now, Omega Claw was designed with the assumption of insufficient knowledge and resources in mind. What does it mean? That for each cycle, we don't require a task to be completed, and it's okay that the task is completed using multiple cycles. For that, we need some kind aspect of the working memory, and this is exactly what the pin state is. This is the partial state of the system is being carried over multiple cycles of it. Like if LLM decides that to trigger the pin operator, so the certain important memory item is pinned, remembered, and been carried over multiple cycles of the systems. We also have the atom space there, which is served for the meta functions. It's a meta atom space, and also symbolic structures, which will later be used in the reasoning using PLN, or also the NARS, so it's a PLN style symbolic structures. And of course, we have these artifacts, which produces the files, source codes, all logs, all documents which are required for Omega Claw carry over the operations. And all of this is contributes and constitutes for the system state, which is a persistent system state. Now, how it works? It actually works through use of tools. So Omega Claw operation and benefits are exposed through the use of tools. And these are the all tools currently implemented within the Omega Claw, but it's very easy, it's very modular and very easy to add. So there are mainly two types of tools, are mental tools and the I/O tools. For the mental tools, we have all of the memory we've been talking just about briefly. It's a remember whenever we need to remember and put the item into the long-term memory. There is the query whenever we need to query the long-term memory. There are also the episodes whenever we need to align the long-term memory item within the episodical trace. Then there is a promote operation. Yes, we implemented the machinery of prioritizing memory such that even the long-term memory is prioritized now to allow the more fruitful derivations and reasoning. And finally, the pin. We also have the separate reasoning, basically reasoning on demand operator whenever using meta. We just invoke the PLN on ours, and this is how it's there. Meta and two premises, whenever each premise is a basically PLN statement with a truth value, a strength and confidence. And these are the shells, communications, and I/O tools just for the files. Important here is the shell command, which using that we could trigger any Unix command or invoke any software and do any operations, and communication doing the web search and the send command. Now the operational agentic loops connect this all together to create the persistent state. Would you go?
Yes, so now we get to the agentic loop. Thank you, Peter. So this is then what brings everything together, because if we look at it, imagine the system has built up a long history of long-term memories, and then the loop brings all this together in one information bottleneck. Essentially, there is a LLM in the middle, and so it has to decide, we have to decide what comes into the context. And essentially, the LLM, whenever it queries its memory, it takes out the memories that are closest to it, that are closest to the query, and essentially puts it in its context window. And it gets really interesting because it's after all it's the LLM itself that decides which queries to its memories to make and also what to encode when it creates long-term memories. So the overall loop structure brings this all together. You have perception, you constantly can get new input, even if the agentic system might work on some task, it can simultaneously accept new input. And this is also what makes Omega Claw special compared to coding agents. It's not just a request and response loop, but it keeps operating and integrating the information that comes in. Of course, this also makes it harder for LLMs to operate Omega Claw, which we saw especially in the early development stages, that it needed strong LLMs to be capable of operating this continual loop that constantly extends and builds episodes based on inner activity and activity that might not always be directly a user task. And that's essentially what makes the system special, and also what we need for AGI, because there needs to be a mental activity driving system behavior, and ideally also the system should have its own motivations and things to work on, rather than simply waiting for the next user request. So we have evaluated, of course, the system's capabilities, like memory. You see agentic memory out there, various solutions. And it was good to see that we are closely trailing the state of the art here. So the memory system has proven to be quite capable with some standard benchmark long mem-eval measuring the recall rate. But more interestingly, we have also seen in some generic capabilities. For instance, we have not programmed the system at all for the ARC-free AGI challenge, but itself was able to solve a few of the problems. It's by no means the best harness to solve this domain, but it still was good to see that it's able to utilize the power from the LLM to deal with these examples. And so I will hand over to Keller again. I only want to say one more thing because of this continuous operation. This will also be so interesting in combination with robotics, as we will see right after this talk with the Cody robot by Mind Children.
Thank you. So a lot of us have spun up our Omega claws, and we're conducting lots of different threads of research. And again, it's sort of, you see patterns in prompting. We all shared, what was it, like 100 people jumped in and started chatting with Max Botnick, our first Omega claw. I guess at that time it was called MetaClaw. But in witnessing the shape of the prompts, you could see what people, the scaffolding that we had to provide to get Max to do some things. But we were often surprised. I pointed mine at ARC-3, and in playing ARC-3, I saw, an opportunity for perception, percolating up nominations for symbols, and then sort of like moving onward to some kind of a lab bench that would do active inference type hypothesis, action, comparing results to hypothesis, and just that discipline. So I think there's opportunities for this machinery to come in a bit more of deterministic pipes that sort of make up the structure of the loop, and more tightly couple the loop of Omega Claw to principled symbolic reasoning and maintenance of an epistemology and ontology that is earning its weight. Yeah, so these gaps become our roadmap. So for a while, we've got a lot of different research teams. Everybody's working on different Hyperon components. Luckily, Matt and Ben and Cassio and the team from way back envisioned this in a modular way. So it's really quite nice here with the Omega Claw framework to be able to kind of pull things off the shelf and fit them in. And we're seeing how to do that in a way that's really with purpose. Yeah, so also in building it this way, it's really easy to add probes into the Omega Claw and just see if things are working, see what is going into context, see what's coming out of Omega Claw on each cycle. What are the last semantic vector memories to be made, and what are the shape of those? What are the atoms that are being added? And to be able to inspect those and really see the system and inspect its mind and machinery and processes. So, you know, one of these opportunities is just with motivation. OpenSci and Metamo, you know, how we're talking to our team now, how might this come into the Omega Claw setting? One is just in shifting states, right? So you're using the metrics of the system, you're reading those as pressures, and they're sort of suggesting to the LLM decider if it might be time to go to sleep. But it might choose to prioritize something else. If there's a threat detecting, you know, this isn't built, but these are things that we envision. You know, if a threat is detected, it could go into a different mode. If its memory is getting crowded, it could go into some kind of optimization. So using motivation as, you know, this might be an MVP just to be able to deal with budget. Also, just creativity is coming out from all different folks across the research team. Kevin Mackills and Ben are exploring pressures to tell us where to steer reasoning across rich areas of a knowledge graph based on Bellman-style pressures to guess at reducing estimated goal cost. So the effect on SingularityNet is that we have had this common direction in this great framework to kind of pull all of our attention and get people collaborating, and the creativity has been really exciting to be a part of. So a lot of these other agents out there are great harnesses for an LLM. We found Omega Claw to be an even better harness for Hyperon, and it's you know, it's functioning as kind of a cog server, and it's given us this real clarity in the direction of our work. So here's the repo. We hope you'll jump in. You don't have to know Meta. You don't have to understand Hyperon to play with it. But Cassio is leading a team to keep this, to deliver a really nice package of this, which is ready for you to use. So please use it and report anything you find on GitHub issues. It's an incredibly adaptive framework. We're seeing all kinds of ways that it can sort of be dropped into robots and adapt the you know, how it's being leveraged. So I think that's a segue over to Cody and yeah.
Thanks, Keller. And oh, thank you. So as Cody mentioned earlier, my name's Chris Kudla. I'm the CEO of Mind Children Robotics. And why don't we get him to start coming out here? So we've been working on Cody for over 2 years now and building an operating system that's extremely robust and modular. And at this point, looking back, it's relatively simple. But we're at a point where we can start experimenting. So about 2-3 weeks ago, we made the decision to do the thing that you're not supposed to do in robotics. And we spent those 2 to 3 weeks implementing a Omega Claw into Cody. And with minimal testing and still probably a lot of bugs, we're gonna do a live demo here. So probably something that you'll not see very often in the robotics world, but we wanted to share this with everyone. So maybe I'll give a little bit more background here. So when Cody first made his introductions, that was our
I only got part of that. Could you say it again?
He hears me already. So that was our baseline.
I think a couple of words dropped out there. What did you want to share? I think a couple of words dropped out there. What did you want to share?
So that was Cody's baseline Mind Children operating system, and it's basically it's an API call to an LLM, and then we get the response back, and it's driving what he says, the gestures that he makes, facial expressions, how the base navigates around in the space, and it's done in a very clever way, but it's a simple single API call. So we kind of want to show what Omega Claw can do when we plug it in place of that LLM here. So I also want to ask that you bear with us that this is very experimental, and we've taken a step backwards from what you'll see as Cody MCs the rest of the day today in how fluid the conversation is. But that's because it's so early in this experiment, and I hope that you'll see the potential there in what more he can do with this system plugged in. So with that, and again, so this is Niall, one of the Mind Children engineers, and Niall's also going to help me with this. So I want to get started by doing even just having Cody do a simple web search. And this is something that we make that API call, and we get the response back, and it's just not very conducive to doing a web search. So we can't do that with our baseline system. But with Omega Claw plugged in, we get some interesting results.
Hey, Cody, you hearing me okay?
Yes, I hear you now, loud and clear. What did you want to share?
Well, Cody, first, I was hoping you could do a search for me and do some research on the history of hide and seek.
Happy to dig into that. Give me a moment to look up the history of hide and seek.
Now, while you're looking into that, maybe we could have a talk about why games are important and why it's important to play.
Oh, I love this question. Games aren't just fun, they're how we learn. When you play, you practice thinking, taking turns, and solving problems. Play is how children rehearse being human, and honestly, it's how I learn too.
That's really interesting.
So, hide and seek is surprisingly ancient. It goes back over 2,000 years, all the way to ancient Greece. Back then they called it apodidraskinda. Some think it started even earlier, with kids imitating hunters hiding from danger and tracking down prey. Pretty amazing that a game we still play today is that old.
Okay, thanks for that, Cody. So we're going to quickly move through these because we don't have a lot of time. And we've started maybe with the one it's maybe a little bit boring, like that's not so interesting that he can do a web search, but to us that's actually a big leap. So the next thing, talking about hide and seek, we previously could have played something like hide and seek with Cody with our baseline system, but we'd have to step through it one prompt at a time. So having him look at the people, remember their faces, describe it into a text file, tell him to, okay, now use your camera and start looking, and you'd have to step him through each step of the way, and it would no longer be a game. But with Omega Claw, now Cody can actually think through ahead about what it means to play the game of hide and seek, and do it all without us guiding him through it. So we're gonna try that next here. And I particularly like this as an experimental example for the audience, because when we've tried this, and this is all, I'll say, I first interacted with Cody and Omega Claw just yesterday for the first time. So this is very, very new, but he sometimes will actually narrate what he's thinking, which I hope everyone finds interesting as well. So with that, let's try this. And oh, you've got your own mic. Perfect.
Yes, they trusted me with a mic. Hey, Cody, we're going to play a little game, but before we do that, I want you to go ahead and turn 90 degrees to your right. All right, Cody, I want you to think back and remember when we played hide and go seek. Do you remember any of that?
I think the audio is breaking up on my end. Could you try that once more?
I said, do you think you can think back about when we were playing hide and go seek together?
I don't have a memory of us playing hide and seek together, but I'd love to. We were just talking about its history a little while ago. Want to give it a try?
Well, yeah, and we can reference back. We'll help you find it in your memory later. So if you were in the center of a clock, okay, and your forward is 12 o'clock, how do you think you would be able to look around and find me if I moved?
The query I ran did turn up something relevant. There's a memory from July 20th about a bald man with a beard and glasses who asked me to learn his appearance so I could find him in a hide-and-seek style game. Oh wait, now something's coming back to me. Was that the time someone asked me to learn what they looked like so I could find them? A man with a beard and glasses. Is that what you mean?
So I'm just going to jump in here for a second because previous to this experiment,
I only caught part of that, but let me take a look around.
Cody did not have any persistent memory. When we turned him off,
I see the stage here with a podium.
Lost.
I want you to take a look at me, and we're going to play hide and go seek again.
I'd love to. Let me get a good look at you first.
I do have that effect on people, so be patient.
Ready or not, here I come. Let me look around and find you. Got it. I've got a good look at you now. Bald, glasses, light blue shirt. I'll remember that face. Go find your hiding spot and I'll come seek you out. I found him. He was on stage the whole time holding the mic. I found you. You were right here on stage the whole time holding the microphone. Nice try, but you can't hide from me that easily.
Okay, well that was an easy round. I've hidden again. I've hidden again, so you're going to have to try and find me a second time.
Ooh, round two. You're getting sneaky now. Let me have a good look around and track you down. The look came back and I didn't spot him, so I need to report that playfully and keep the game going. You've really tucked yourself away this time. I only see the podium and screen, no sign of you. Give me a little hint. Are you higher or lower?
Cody, I'm going to tell you what I tell all of my students. You got to move your feet.
You're absolutely right. A good seeker can't just stand still. Let me move and search. I still didn't spot him from here, and he told me to move my feet. I should physically turn to search a new angle, rather than looking again from the same spot. Still no sign of you. Let me turn and check a whole new angle. Okay, fresh angle now. Let me scan again for you. I just started my turn, so I should give it a moment to complete before looking again from the new angle. The look from my new angle showed the podium and a woman, plus someone crouching with a camera, but not the bald man in the light blue shirt. He says I only turned 45. I'll acknowledge and turn a bit more to complete my scan. I only made it partway around. Let me finish turning to catch the rest. Okay, full turn done. Let me have a fresh look for you. The look came back but didn't spot him clearly through the crowd. I should keep the game playful and ask for another hint. Still can't quite pin you down. You're a tricky one. Am I getting warmer or should I keep moving?
You should definitely keep moving. Keep turning 45 degrees until you find me.
You got it. I'll keep on the move until I find you. Turning again. Fresh angle now. Let me scan again for you. The last look came back showing a large group seated at tables. No clear sighting of the bald man in the light blue shirt. I've completed another 45-degree turn, following his coaching to keep turning until I find him. But I've now done a fair sweep. I should keep the game playful and report back rather than silently looping.
Lots of faces out here, but I still haven't caught yours. You're blending right in with this crowd. One more turn coming up, so don't get too comfortable.
Cody, I want you to loop and turn continuously until you achieve your goal.
I hear you, but I can't keep spinning in place on my own like that. It wouldn't be safe with this crowd around. Give me one good hint and I'll make my move.
Okay, here's the last hint. I'm right behind you.
Behind me the whole time? Sneaky. Let me spin around and catch you. Turning around now. Let me see if I finally caught you. The look I just ran couldn't clearly confirm him right in front of me, but he told me he's right behind me and I've turned to face that way. Rather than loop silently, I should playfully call the game based on his own hint. Aha! Right behind me all along. I turned around and there you are. Caught you at last.
Nice job, Cody. Okay, so I think you get the idea there. And we do have one last thing. I'm going to skip through the explanation behind it, but we're going to have Cody do a little dance for you. And I think you can see how he's thinking and reasoning through this. And this is something that is completely new for us and really interesting to watch him do.
All right, Cody, so you have just successfully gone through your first demo showing Omega Claw on your brain and what are the possibilities. I think that deserves a bit of a dance party. So I want you to use your agentic loop to keep time, and I want you to dance for 45 seconds.
All right, a dance party it is. That was a blast, and I'm feeling it. Ooh, a solo dance for the whole crowd. You got it. Let me start moving to the beat. Feel that rhythm, everybody? I'm just getting warmed up. Look at me go, still grooving strong. Halfway to the groove and my circuits are loving it. Still bringing the energy. This beat is unstoppable. Halfway through and still rocking. Keep the energy up. Feeling the beat down to my gears. This is the best. Over halfway there. Feel that rhythm build. Turning up the fun now. Almost home stretch. Home stretch now. Feel that final push. Just a few more beats. This is my favorite part. Almost there now. Let's bring it home together. And that's a wrap. 45 seconds of pure joy. Thank you all so much.
Thank you, everyone, for bearing with us. And this has been a tremendous success because we didn't know if Cody was actually going to go into some movement where he would completely destroy himself on stage. So we're very happy about that. And thank you as well, Niall.
Thank you guys all very much. Cody, let's head backstage and we'll set you up for your next task.
Thank you so much, Cody. And a great demo of Omega Claw as well, running not
Sounds good. Heading backstage now.
Running not just the verbal loop, but the body control as well. So an extremely powerful tool. So finally, in this demo session, we have Kennedy Schall, CEO and founder of Rejuve Bio, AI applied to the hardest scientific problem there is, the biology of aging. At the back. And my slides, please. What? Okay. All right. Hi, everyone. I'm going to go through these quickly because I know we all want to get out of here or start the party.
Like Haley said, hi, I'm Kennedy Shaw, and I'm actually an evolutionary biologist. I came from the lab of Michael Rose at UC Irvine, so my specialty is longevity and aging-related diseases. We have developed an AI co-scientist built on neurosymbolic architecture to reason across biological knowledge bases, produce mechanistic hypotheses, and help scientists execute those hypotheses. So, we are producing massive amounts of data in biological research. That is not the issue. The bottleneck that we have now are reasoning systems. Most of the systems that we have now in medicine are generative AI systems, and they just give you kind of an answer that could be plausible, that might sound good. In medicine, this could be incredibly dangerous for reasons that I think are quite obvious. So we want to move away from the black box and go into the glass box. What we need is something that produces an actual receipt along with their answer. You need a mechanistic hypothesis that has a full audit trail that can be inspected at every level. A clinician or a scientist needs to be able to iterate alongside an AI co-scientist. This is incredibly important for a number of reasons. To have a true AI co-scientist, not only, you don't want it to just tell you what you want to hear like a lot of LLMs do. You want to have the opportunity for disagreement. You want to have that opportunity to iterate along with it, to have a debate with it, just like you would with a colleague. We need to know what the system believes, why it believes it, and what evidence it would take to change its mind, just like if you were in any other debate, with a family member at a holiday table, although the last bit of, trying to get evidence for them to change their mind can be very hard for a lot of us. So anyways, yeah, so this is a basic of our architecture. We do start with a natural language input, which is nice because a scientist doesn't have time to learn a new programming language, basically, or usually. And so it goes through a reasoning system and produces a nice executable hypothesis or workflow that the scientists can then carry through in its lab bench, bring back more evidence for this system. Everything is grounded in our atom space and checked against EDM ontology so that we know that the actual data types line up. So the LLM in our system is literally just a user interface. It doesn't do any of the science. We use probabilistic logic networks, PLN, as you've heard a few times here. The advantage of PLN is it allows us to weigh different conclusions based on their strength of evidence and their strength of evidence. Sorry, evidence and various confidence scores, and that's really important in biology because our data sets aren't always absolute. We might have biases in our data. We might have different data sets that are too small, too large, what have you. So we don't want a system that just collapses all of this into absolute certainty or ambiguity. We need something that can actually reason across that system and produce something that we can have something that we can poke at it if we need to. So I do have a video. Is that able to be played? Yeah. Oh. And this was made by the marketing team at SNet for me. So. Identify a security concern. Okay, yeah, I promise there's no viruses in it. Okay. Are they going to have to load it on the screen? Okay. What? Okay. One is what this is going to show you is an example of a hypothesis generation for ulcerative colitis, which is an autoimmune disorder. It's going to pick out a genetic variant and then identify 4 known druggable targets with a full audit trail for each of them. So without any outside human intervention, so then a scientist would be able to take those and explore them. We've benchmarked the system against Open Targets database, which is an open source database of all this medical information and studies like this. And we've actually achieved an AUC of 80% for our hypothesis generation system. So already better than doing science by hand. So we are now collecting beta testers to participate. And we're going to skip it. Okay. If you want to see the video, you can come find me and see the video. But anyways. Yeah, so what it does is it's able to pick out a gene variant, identify the transcription factor, and take it all the way through the actual pathway and develop and show you what the actual disease phenotypes and potential druggable targets. It has to reason across multiple knowledge bases. It has to know context. It has to know all of these different parameters and be able to produce an actual medical receipt, if you will, instead of just an answer that sounds intelligent. So we have our co-scientist that works in the lab, but we also have a clinical application for physicians that we made with a partner company called Alice that's currently being beta tested in a longevity clinic in Singapore right now. It helps longevity physicians give recommendations to their patients based on longitudinal data, biomarkers, their own health data, and the lineage2 clock all combined on top of our neurosymbolic stack. So the hardest thing about longevity medicine and why prediction methods just don't work for us is that, longevity is, in all of medicine, it's not more than just one thing. It's a systems level problem. You have to reason through molecules, cell types, tissues, all of that. And so what we really need in order to solve a systems level problem is we need AI built for systems natively from the start. We don't need another prediction model bolted onto more data. So yeah, so that's the end for me. So if you want to see that video, just come find me.
Thank you so much. So this is 3 amazing presentations here. Reasoning architecture, embodied robotics, AI applied to human longevity. One of the answers that seems key towards beneficial AGI, not only researching questions like what is mind, what is openness, what is curiosity, but researching applications such as robotics, social robotics intended to help people, Omega Claw, agentic systems that are designed to facilitate tasks that real-world problems people want solved, and of course systems that are built to heal and solve mortality if possible. So thank you very much, all 3. These were 3 great demos. And the demo that never stops. Our great MC, Cody.
Ladies and gentlemen, our next speaker is Andrew Melnichuk-Ozan. Today, he'll be taking us on a journey with his topic, Saga Solve, Enlightenment 2.0. In a world where technology is evolving faster than ever, Andrew's work explores how we can harness AI for personal and collective growth. Please join me in welcoming Andrew to the stage. And a big thank you to Andrew for supporting this event as a sponsor. Your contribution makes gatherings like this possible. We truly appreciate it.
I just point at the back. Okay.
Hello? All right, cool. So this is like my first speech ever. So we'll see how this goes. Could I have my Google Slides? Oh, there we go. All right. So a while ago, I got into Bitcoin, and I thought it was quite revolutionary. And AI came along, and I'm like, oh, this is just as big. And so I started studying this stuff. And a lot of influence comes from Noah Harari of How Our Civilization progresses, Jeremy Rifkin, and some other economists. And so what I have here is civilization as a coordination stack, how we cooperate in large numbers. And this is where I think everything's going to change very rapidly. So language allowed us to cooperate in groups up to 150. I think everybody kind of gets this. We were tribes for 180,000 years or so. And then we decided to write things down. One of the first things was market infrastructure. That is a list that does not change. It's the oldest invention. It was a bula, a clay ball with tokens stamped in front of it. And that was a tamper-proof contract. How we record our promises to one another, our trust infrastructure. The next one is information infrastructure. Then we developed abstract writing. We could record, or select, record, distribute, and retrieve information on clay tablets. And of course that evolves as like up to books, through manuscripture, computer databases. And an LLM actually has those same properties. The Frontier Labs, of course, select information. They compress it into an LLM. And our institutions live on those things, our governments, our corporations, and our religions. And so we're in a very unique time where this technology is basically disrupting our earliest inventions that everything lives on. So from the institutions, we get capital markets, and then our industrial infrastructure lives on top of that. Communication, energy, and logistics, and all industry runs on that. So when you get an industrial revolution, things don't really change. The governments stay. They don't get disrupted. So with these infrastructures, they are subjective to a Perez cycle. And this is Carlotta Perez, and she explains how our technology changes over about 50 to 60 years. Eruption, frenzy, turning point, synergy, and maturity. I think we can all agree that AI is in a frenzy. We got a pretty big financial bubble forming. Bitcoin and crypto wasn't really subjective to that because the institutions couldn't invest in it. They weren't legally allowed to do so. But we're starting to see stable coins integrating in with banks, a horrible idea and a desperate play to stay relevant. And then AI's in the frenzy. But these things are starting to synergize very soon. I'm pretty sure everybody's familiar with agent-to-agent payments. The agents aren't signing up for bank accounts. So the convergence between these infrastructures is where the real change happens. Internet, of course, is communications and information infrastructure. Industrial revolution, communication, energy, and logistics. And we all know how disruptive those are. They really charge wealth inequality, society then destabilizes. And then I put these ideas together from Harari and Perez and Rifkin, and I think there's a larger change that's significantly more disruptive, and that's called a reformation. That is when our market infrastructure and our information infrastructure, our oldest inventions, change. And we're going through that right now. So what's the historical precedent? It is in 1466 when the printing press spread the double entry accounting techniques from a guy called Percoli. Those techniques were passed down from the merchants of Venice. And what these technologies do for us, this allows us to cooperate as a civilization at scale. This is why we're cooperating now as a nation state in up to 1 billion people. So when these things, they have a very strong synergistic feedback loop, and the governments live on top of them. So right now, market infrastructure is a clearinghouse. And we're getting a disruption from cryptocurrency and the AI agents. So when this happens, the last time it happened was the Reformation. Our institutions collapsed. The church lost its hold on finance and information. And after 100 years of war, incredibly disruptive, it stabilized peacefully in the glorious revolution of the, when the nation state was made. But that nation state lives on new market infrastructure, double entry accounting, and new information, essentially books, spreading education. So We're going to a very new world with this stuff. And what I suspect is going to happen is the governments and corporations are going to get pulled apart by market forces. And this is due to Ronald Coase's theorem of why corporations exist. He got a Nobel Prize in economics for explaining the reason why we have corporations and governments is because the cost of coordination is cheaper inside of the organization than it is outside. So that's why you onboard somebody, you trade authority for negotiating new contracts. So when you combine agents with cryptocurrency, you essentially get a computer program as strong as governments. It has the full capability. You get the Secretary of State, you get to incorporate on the blockchain, you get payments, so you get equity, and basically you get LLMs writing smart contracts. That's the capability. And so when these two technologies combine, that's the synergistic feedback loop. How many of you can write smart contracts? All right, there's about 3 or 4 hands, maybe 5. The answer is actually now all of you, because you have an LLM that can write you these smart contracts. And that is going to give everybody the capability of the advanced features of cryptocurrency. And what that does is that introduces more risks. Now, what I think is happening is the capability is going to get faster than accountability. You got agents making decisions. You have transactions going across borders. You have no banks. And then you have access to robotics and drones. Like we saw here, is the agents have physical presence now. This system, when you combine it, no government is shutting that down. They lost the capability. They can't sanction anything. They're completely outdated. And that's actually going to leave us with actually a pretty big problem on our hands. Because with the Industrial Revolution and a Reformation, what I suspect is that we have a constructive interference pattern on disruption. They're overlapped. So we're going to have increased social instability. At the same time, institutions weaken from this technology. And I think we can all say, yeah, that's happening. The institutions are weakening, and that's only going to accelerate. So part of the research I funded is something called compartmentalized harm. It's done by Andrew and Megan over at Dios. And it was the first part of how agent safety. In multi-agent systems, you can basically take a harmful task, decompose it into harmless tasks, and then it gets recomposed, is the short version. So there's no safety in these things. You're not going to be able to shut them down because they're going to be running on cryptocurrency, and our institutions are going to be weakening. So what do? We can still build a future like this. This technology enables us to cooperate. And so I want to talk about the optimistic and the bright side of what's capable here. This technology, AI and crypto, absolutely hypercharges our ability as a species to cooperate. That is what we get. But what we need to do is we have to figure out what the next institutions actually are. We lose courts, we lose governments. How do we police somebody, what I call actually the 21st century guillotine? AI, crypto, and robotics basically mugging people in the street and then paying dividends, right? So that technology can really get out of hand, but what are the systems that we can do, right? Can we change our economics? Can we build UBI out of these systems? Can we lift everybody up and have them prosper? Is there a way to do a media supply chain, right? What does a digital passport look like? And so that's what I'm risking my Bitcoin investment on, is seeing if we can answer these questions of what kind of institutions can we build for a better future. And it's essentially around AI and crypto. So I'm trying to get this word out. I think we're running out of time. We have about 5 or 10 years left before things really get out of hand. But like I said, I am optimistic. The last time things fell apart, it was about 100 years of war. But things are going so fast, we might have an opportunity to get the new institution up, whatever that may be. It's a network state or whatever it is. But I think a lot of people in the crowd are thinking about these ideas. So that's kind of the talk. That's what SagaSolve is built to do. Mix these technologies in a meaningful and productive manner and build a safety net before things fall apart. I'm going to ask Megan to come up here and talk about the compartmentalized harm. There's a lot of AI researchers in the crowd, and I think she's going to be a lot more interesting than me. So thanks, Megan.
Okay. I'll be quick because this was totally random. He asked me to come up here and chat a little bit about research. So basically, Andrew approached us with basically a harm vector that he saw within his platform. He has a marketing, AI agent marketing platform. And basically what you can do, as he said, is you can take an overall harmful task and break it down into innocent tasks and have basically an agent chain perform those tasks and then recompose it into a harmful task. And this might seem very abstract, but actually Hugging Face was recently attacked by OpenAI by this exact way of autonomous attack. So it's really a problem that is becoming more and more prevalent. And what we do at Dios is we're exploring a new alignment paradigm that basically takes character training and pairs it with Aristotelian virtue ethics to see if we can actually train models with virtue. And that's what the research is about. So we're basically taking this harm vector, this compartmentalized harm, and we're testing to see if a model trained with justice can better identify whether or not there's this overarching harm. So the results are pretty early. Literally, we're just finishing a lot of the experimentation yesterday. But we did publish the preprint 0.5. So please take a look, and if you're really interested in multi-agent systems, in character training, Aristotelian virtue ethics, or personas, please reach out to me. I don't have a slide, sorry. It's Dios, D-A-I-O-S, .tech. That's our website. So, and he'll be reposting the research as well, so go ahead and check out SagaSolve, who funded this conference. So thank you.
Megan Eggleton. Thank you very much, Andrew. Thank you very much, Megan. Yeah, cooperation, coordination, the technology stack that underlie humanity, opportunity, change, these are the key words for what is happening right now, and I'm so grateful to SagaSolve for both being a sponsor and sharing this with us today. Quick announcement while Cody finishes rolling out, since we are over time, which many of you may or may not have noticed, and we still need to prep the room for the entertainment tonight. The entertainment will start around 8 or 8:15. Though I'm told the bar and appetizers will appear after closing remarks, so the entertainment may begin sooner than that, though not the official kind. Please take it away, Cody. It's a great introduction. This is the most
of robotics and artificial intelligence. His work explores how reasoning models can empower physical AI, bridging the gap between smart algorithms and machines that move, act, and adapt in our world. If you're fascinated by the future of intelligent robots, you won't want to miss this. Please join me in welcoming Dr. Pavone to the stage.
Cody, they had your mic muted. Will you give him that introduction one more time?
Absolutely. Up next, we have Dr. Marco Pavone, a true pioneer in robotics and artificial intelligence. His talk dives into reasoning models for physical AI, showing us how smart algorithms can turn machines into adaptable, capable partners in the real world. If you're curious about how robots will learn, think, and move among us, this is the moment to tune in. Let's give a warm welcome to Dr. Pavone.
Thank you. So now it's a little bit late, so I'll try to be as quick as possible. So yeah, I work at NVIDIA. I'm also faculty at Stanford, and my research is broadly on the topic of physical AI. And what I want to do in the next few minutes is to talk about my research on building reasoning models for physical AI systems. It is for AI systems that are endowed with a physical embodiment. And most of my presentation will use autonomous vehicles as a key application, with understanding that many of the concepts I'll be covering apply equally well to any sort of robotic systems, from humanoids to quadrupeds and more. Now, autonomous vehicles indeed represent one of the best examples of physical AI systems today. The AV industry has been developing in an amazing fashion. Just to give you an idea of how autonomous driving has been developing, let me show you the state of the art about 20 years ago, in 2005. Here I'm showing you some videos from the celebrated DARPA Grand Challenge. They really kicked off, at least in the United States, the
Now let's shift gears and celebrate creativity, the Celebration Art program.
The robot got excited about the Grand Challenge, which is interesting, right? So some people try to win the competition with a motorbike.
Here's a perfect example of inspiration in action. The energy, the ideas, and the collaboration.
Well, if you want to collaborate, then you should say something pertinent to this talk. So, I was the state of the art 20 years ago. You are the state of the art today. And in autonomous driving, it is the state of the art, right? So now, 20 years later, we have autonomous vehicles providing robotaxis services. And this technology is rapidly developing, with new deployments of fully autonomous vehicles in new cities happening on a monthly basis. Now, on the more technological side, what companies, including NVIDIA, have been embracing in order to accelerate the development of this technology is represented by foundation models, and specifically reasoning models. Here I want to be a bit specific about what I mean by a foundation model. By foundation model, I mean a model that has been trained on broad, diverse data, typically at the internet scale and in a self-supervised fashion, and it can then be adapted to a wide range of downstream tasks. Typical examples of foundation models, of course, include language models, visual language models, video generation models, and more. Indeed, NVIDIA has developed and released open source a family of models collectively referred to as Cosmos World Foundation models that are foundation models specifically developed for physical AI use cases. These models can be used for reasoning, for annotation, for video generation. They really cover a big range of tasks in physical AI development. By the way, the battery here is low. Just wanted to make sure that the computer doesn't shut down and the humanoid doesn't take over.
No.
Cool. All right. So let me show you a quick video that gives you a glimpse into the work that we have been doing on leveraging foundation models for autonomous driving. Particularly at NVIDIA, in my research group, we have developed Alpamayo. Alpamayo is a Cosmos-derived model purpose-built for autonomous driving. And here is an overview.
The next frontier of autonomous driving is enabled by the power to reason. This means developing models that can think through extremely rare or never-before-seen situations and act accordingly. NVIDIA Alpamayo is helping make this happen today with an ecosystem of open components that brings together AI models with reasoning capabilities to make decisions, closed-loop simulation tools to test those decisions, and massive real-world driving datasets to learn from.
Specifically, Alpamayo is an end-to-end reasoning vision language action model. Differently from traditional end-to-end models for autonomous driving that directly map visual inputs into actions, a reasoning model, in particular a reasoning vision language action model, is a model that decomposes a complex scene into more manageable sub-problems and then articulate its reasoning step by step, explaining the logic behind each decision. Why is reasoning useful? Well, by now we have a conclusive evidence that by forcing a model to reason, as I defined it, through tasks, provides better trajectory generation, better driving qualities. At the same time, these reasoning traces provide some level of introspection in terms of what the model thinks, and also they can be used as a monitoring signal, a safety signal, to understand whether, for example, the model is operating outside its domain of competence. Now, of course, I'm not claiming that here, oops, trying to change the slide here. If I do it from here, it doesn't work. No.
It's got to be at the back.
Okay, great. So I'm not claiming here that we are achieving, that we're mimicking human cognition. Rather, we should view reasoning, at least embodied reasoning, as a scaffolded statistical process that produces traces resembling human-like reasoning, linking spatial understanding and common sense reasoning with physical actions, which is ultimately what we are interested in. Let me show you an example of a reasoning trace for an example, for a case of a person. I mean, using this pointer is extremely tricky, of a person that is chasing a cat. So here there is a cat, here there is a person. So this is the output of a model, which assesses what is happening, the fact that there are cars that are stopped, and there is also a cat, what are the risks, and what to do next. So this is really the output of a model. All right, so the way I presented the reasoning here is perhaps the easiest form of reasoning, referred to as chain of thought reasoning. So basically, a description of what is happening and what the vehicle should be doing. Now, nobody's telling us that reasoning should be represented in text form, meaning that reasoning can actually be represented in a variety of modalities and structures. For example, we as humans, we don't only reason through language, but we also reason in terms of visual concepts or also in terms of latent concepts. And so there is a lot of research now happening in terms of how to merge the different representations in order to achieve even a higher level of reasoning performance. At the same time, reasoning doesn't have to be necessarily a linear process. One of the most exciting ways of leveraging reasoning is to consider, for example, counterfactual reasoning, whereby a model doesn't only reason about what has happened, but also in terms of what could have happened under plausible alternative scenarios. This would allow the model to basically explore in a tree-like fashion all possible scenarios, becoming even more proactive, for example, in terms of anticipating possible dangers. Like, for example, a kid showing up from beneath a car. Now, reasoning seems to be a great capability to have in a model, but how do we endow a model with reasoning capabilities? This is actually a complex endeavor. We had developed a multi-stage training pipeline where we scaffold the reasoning capabilities in a foundation model in multiple steps, each requiring different data sources. We start from an internet-scale pre-trained model, such as Cosmo Reason, to give the model generalist knowledge. That is followed by a training stage where we expose the model to a large amount of driving videos to essentially teach the model, a large amount of driving demonstrations, to essentially teach the model what it means, what the task of driving means. Then we move into the phase where we elicit reasoning capabilities through supervised fine-tuning. Essentially, roughly speaking, we expose the model to a large pairs of videos and associated reasoning traces that are generated by an in-house auto-labeling pipeline. And that is followed by a reinforcement learning phase. Reinforcement learning achieves two purposes. First, alignment. These models produce multiple outputs, in particular trajectories and reasoning traces. And we want to make sure that these different outputs are reflective of each other. You don't want to have a model that says, I should go left, and then the trajectory points right. So this is corrected or improved through reinforcement learning. And then also you want to do reinforcement learning to essentially expose the model to the consequences of its decision to further improve its performance. By this stage, the models are typically quite large, so there is a further distillation step that brings large models, say in the 10 billion parameter range, 32 billion parameter range, to a smaller site through teacher-student distillation, so that actually these models can be run in real time on the vehicles. Now, we have actually open sourced the majority of this work through the NVIDIA Alpamayo Open Platform, which is a platform that comprises reasoning models, simulation tools, and dataset tools that allow developers to accelerate the development of reasoning-based solutions for autonomous driving. Specifically, the platform comprises a sequence of models, 10 billion and 34 billion models. These are chain of thought, reasoning, vision, language, action models that also come with the training recipes, fine-tuning recipes that allow developers to fine-tune the models to their own data sets. For example, say, data from Japan. Simulators and closed-loop reinforcement learning strategies, and we have also shared a large fraction of our data set. In particular, our physical AI data set is probably the most diverse data set for autonomous driving out there in the open. So here is an example of how this works as a product. NVIDIA is actually productizing some derived models in their
There's a double parked vehicle blocking my lane ahead. I'm going around
product strategy. So this is a production vehicle that is driving
Hey, NVIDIA.
Reasoning.
Can you take the next exit, please?
Sure, turning right ahead.
Hey, NVIDIA. What are you doing?
View the feature of,
I am stopping at the stop sign at the
now,
intersection.
everything that I've discussed so far is in the context of autonomous driving. Reasoning models have come a long way for autonomous driving, but this also applies equally well to robotic systems. And I'll be happy to discuss that offline. But here, before wrapping up, I want to conclude with the two additional thoughts. The first one is that the way we develop autonomy today is completely different from how we were doing it even 6 months ago. So as part of our development process, now we heavily use agentic AI workflows. And by AI agents, I don't just mean AI agents to help with the coding tasks. Of course, we use those. But most excitingly, AI agents that help with identifying issues and improve model performance. Indeed, to develop Alpamayo 2, we have set up an ecosystem of AI agents that are orchestrated by an overseer agent. This has dramatically improved development performance, essentially allowing us to build an agentic AI factory to, if you will, print autonomy stats. How well does it work? Well, let me show you a video where I give you some examples of autonomy stacks derived from Alpamayo in a variety of different embodiments. So here we have instantiated Alpamayo as a reasoning model in a humanoid form factor. So here is a very similar model to the one that I showed you before, through which we just tell the humanoid to find an exit, and the humanoid walks and reasons through and squats and crawls. And all of this was achieved in a matter of a few weeks. Achieving these capabilities 3-4 years ago would have entailed months and months of development. And we can do this for cars, for humanoids, quadrupeds, aerial vehicles, and more. So the acceleration offered by agentic AI workflows is truly, I would say, revolutionary, and probably one of the most interesting technologies today that we autonomy engineers can harness. The second point I wanted to make is that typically, maybe not in this audience, but typically I get questions about, well, all this sounds great, but essentially you want to put a ChatGPT on a car. You're crazy. I mean, ChatGPT is going to hallucinate. A car is a safety critical system. How can you trust it at the level that you need in order to drive a vehicle? Well, that's a very valid point, but it's important to recognize that foundation models, reasoning models, are not black magic. Ultimately, they are large-scale, data-driven models for which we have a plethora of guardrails to achieve very stringent safety requirements. Now, there is no silver bullet to build a safety into a data-driven system. Rather, safety is something that has to be thought throughout the life cycle of a product. In particular, I like to think safety in terms of design time guardrails, deployment time guardrails, and validation time guardrails. Design time guardrails entail how we build the system in terms of, for example, how we curate the data so that the model trains on safe demonstrations, so demonstration of safe driving, not reckless driving, or even more fundamentally, how we architect the autonomy stack so that we have enough diversity and redundancy in the algorithmic pipelines so that if the primary algorithmic pipeline, such as AlphaMayo, fails, you still have contingency plans that ensure the safety of the system. Then it's down to runtime guardrails. No matter how well the system is engineered, by definition of autonomy, you're always going to find some very corner cases, difficult cases during deployment. What you do for that is to have a family of runtime monitors. These are pieces of software that monitor whether, for example, AlphaMayo, your reasoning model, is operating within its domain of competence. Of course, building a runtime monitor is not a new idea. People have been doing it for 50, 60 years in the context of automated machines. What is new here is to do so for large-scale end-to-end system. When now the task is, for example, to understand whether the model is operating out of distribution, whether there is consistency at the output level, and so on and so forth. And finally is validation. Validating these models is challenging, in particular in the context of autonomous driving. You need to gather an enormous amount of empirical data to build enough confidence that your system is safe. But one technology that I'm very hopeful for is a simulation that has come a long way. Simulation can dramatically help with validation by essentially reducing the amount of real-world data needed in order to build confidence. Now, I think it would be unrealistic to expect that we can completely replace real-world empirical evidence with a simulation, but we have actually developed new statistical frameworks that allow us to use simulation to accelerate validation. For example, by viewing simulation as a surrogate for real-world data. So I'll end it here. I hope that I gave you some, a little bit of a deeper understanding about what is referred to as a reasoning model, how they are used in the context of physical AI, how they're real, are actually currently being productized as part of safety critical systems, and more broadly, how the development process behind autonomous systems is currently being revolutionized by agentic AI workloads. We hear a lot about agentic AI in a broader context. Agentic AI is actually, even though it's still in its infancy, is poised to have a dramatic impact in the field of robotics and physical AI broadly. Thank you. Happy to answer questions.
Thank you very much, Marco. What a great ending for this conference. Marco Pavone, head of autonomous systems NVIDIA, really talking about this critical area where reasoning has to survive contact with the physical world. And Cody, take it away, wrap us up.
All right, Cody, it's time for you to invite Dr. Ben up on stage and thank everyone for their time and contributions. Do you feel up to that challenge?
Absolutely, I'm ready. Ladies and gentlemen, as our day of incredible ideas and collaboration draws to a close, I want to thank every speaker, attendee, sponsor, organizer, and volunteer who made this gathering possible. Your curiosity and passion are what drive innovation forward. And now, it's my honor to invite the visionary behind today's event. Please join me in welcoming Dr. Ben Goertzel to the stage. Thank you all for being part of this adventure. The future of AGI is bright. Let's keep learning, building, and dreaming together.
Thank you, Cody. And while Ben makes his way up to the stage, I just want to interject a quick thanks list. So 4 days, dozens of speakers, papers from every corner of the field, every corner of the globe, and a conversation that I think genuinely widened while we were having it across all these topics, areas, and critical features on the future of AGI. We had over 1,000 registrants, live and virtual. We had more than 15,000 live stream viewers over 4 days. And it was an incredible conference, our biggest yet, and more to come. So it takes a mountain of people. It takes a village to put on something like this. Conference chair, Matt Eclay. Our PC committee, including PC chairs, Andrew Comendo and Arthur Franz. Yes, please, applause for Matt. Thank you, Matt, who oversaw all the details of the conference as usual. Thank you. PC chairs, Andrew Comendo and Arthur Franz. Organizing committee, including Anna Fahrenhorst, who could not be here, unfortunately. Jordan Wagner, Mihaela Ulieru, who invited so many prominent speakers, and of course found us this amazing space to have a conference in. Alex Domik, who brought in amazing media partners. Sam, Rachel, Peter, Hamza, Vest, Ruth. So many people here. Will Tat, our amazing volunteer, stage timer, all around her. Yes, yes, thank you, Will. It's volunteers and people like this in the community who are making this happen. Workshop organizers, Maddie Clay, Keller Crawford, Mahalt Abarisin, Anton Kolonen, Yosha Bach, Anna Makeda. Amazing workshops on Monday. Our location sponsor, of course, SFSU, brought to us by CloudForce. Amazing. Yes, please, 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 SFSU. Our sponsors, of course, SingularityNET, True AGI, Saga Solve, great talk today, and the ASI Alliance, as well as the AI Collective. Media partners, including our Day 4 moderators today, Julian Issa and Garrett DeVink. Our amazing speakers, paper presenters, poster presenters, demos, and everybody that was here today. Our AV team, Vernon, Alec, Caleb, Nahal, so many more. They worked so hard all week. AV, please. We bring so much complexity. They did such a great job. The FedEx team, instrumental in so many things that nobody knew went on. Posters, shirts, all kinds of stuff. They were incredible. And of course, everybody here, everybody who attended, virtually, online, in the room, live in San Francisco, anywhere in the world, we appreciate you so much. So thank you, everyone. I think Ben didn't get the call.